everyone, and welcome to our Machine Learning with Python full course. Have you ever wondered how Google finishes your sentences, or how Netflix knows exactly what shows you love, or how chatbots seem to understand you so well? Now that's the magic of machine learning. And in this course, you will learn how to make it happen using Python. Now you might be wondering, why Python? Well, Python is the go-to language for machine learning for a few really great reasons. First off, Python's simple syntax means you don't have to get lost in complicated code, making it perfect for beginners. Plus, Python comes with a ton of powerful libraries like TensorFlow, Keras, Scikit-learn, and Pandas that make building machine learning models a breeze. So whether you're just analyzing data, building models, or visualizing results, Python has everything you need to know to get the job done efficiently. Knowing machine learning with Python will be an essential skill in industries like healthcare, finance, marketing, and many more. Companies are looking for people who can use Python to build smart systems and create AI-driven solutions. And the best part is, the career opportunities are huge. In India, machine learning professionals can earn around 10 lakh to 25 lakh per annum, and in the US, salaries can easily top up to $120,000. Now, this course is designed to take you from a beginner to someone who can confidently build machine models with Python. We'll start by breaking down what machine learning is and dive into some key techniques and concepts you will use in real-world projects. So let's get started. Before we comment, if you're interested in launching a high-growth career in artificial intelligence and machine learning, this program might be the best thing you'll ever come across. The professional certificate in AI and machine learning offered by Purdue University Online in collaboration with Simplilearn and IBM isn't just another course. It's a complete career-transforming experience. Ranked 1 online AI and ML certification by Career Karma, this program is designed to help you master the most in-demand skills in AI automation, ChatGPT, GenAI, LLMs, deep learning, agentic framework, and so much more. So whether you're just starting out or looking to upskill, you'll get hands-on with 15+ real-world projects, explore tools like Hugging Face, TensorFlow, Midjourney, or even build LLM-based applications. So what are you waiting for? Hurry up and enroll now, and you can find the link below.
Hello and welcome to Machine Learning Tutorial Part 1. This is Part 1 of a machine learning series put on by Simplilearn. My name is Richard Kirschner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you today? Well, we'll start off with a brief explanation of why machine learning and what is machine learning. And then we'll get into a few of the types of machine learning. Machine learning algorithms, linear regression, decision trees, support vector machine, and finally we'll do a use case where we're going to classify whether a recipe is of a cupcake or a muffin using the SVM or the support vector machine. Sounds like a delicious way to explore machine learning. So why machine learning? Why do we even care about having these computers come up and be able to do all these new things for us? Well, because machines can now drive your car for you. Still very in the infant stage, but it's just exploding, as we see with Google's Waymo, and then Uber had their program, which unfortunately crashed. They know that this is huge. This is going to be the huge industry to change our whole transportation infrastructure. Machine learning is now used to detect over 50 eye diseases. Do you know how amazing that is, to have a computer that double checks for the doctor for things they might miss? That's just huge in the health industry. Pretty soon they actually do already have that in some areas where, maybe not for eyes, but for other diseases, where they're using the camera on your phone to help pre-diagnose before you go in and see the doctor. And because the machine can now unlock your phone with your face. I mean, that's just cool, having it being able to identify your face or your voice and be able to turn stuff on and off for you depending on where you're at and what you need. Talking about an ultimate automation, our world we live in. And as we dig in deeper, we have a nice example of Facebook. As you can see here, they have the Facebook post with Halloween. Comment yes if you want it. Order here. Nobody likes spam posts on Facebook that annoy them into interacting with likes, shares, comments, and other actions. I remember the original ones were all, if you don't click on here, you will have bad luck or some kind of fear factor. Well, this is a huge thing in social media when people are getting spammed, and so this tactic, known as engagement bait, takes advantage of Facebook's newsfeed algorithm by choosing engagement in order to get the greater reach. To eliminate engagement bait, The company reviewed and categorized hundreds of thousands of posts to train a machine learning model that detects different types of engagement bait. So in this case we're using Facebook, but this is of course across all the different social media. They have different tools they're building, and the Facebook scroll GIF will be replaced. Kind of like a virus coming in there. It notices that there's a certain setup with Facebook and it's able to replace it. And they have like vote baiting, react baiting, share baiting. They have all these are kind of general titles, but there certainly are a lot of ways of baiting you to go in there and click on something. So they fed all this data was fed into the machine, and then they have the new post. The new post comes up that takes over part of the Facebook setup. And that's what you're looking at. You're looking at this new post that's replaced, like a virus has replaced that. So what Facebook did to eliminate this is they start scanning for keywords and phrases like this and checks the click-through rate. So it starts looking for people who are clicking through it without even looking at it, or clicking through it and it's not something that normally would be clicked through. Once Facebook has scanned for these keywords and phrases, it is now able to identify the spam coming in. And this makes your life easier, so you're not getting spammed. It's not like walking through an airport, and in a lot of countries you have like hundreds of people trying to sell you timeshare. Come join us, sign up for this. Eliminates that annoyingness, so now you can just enjoy your Facebook and your cat pictures, or maybe it's your family pictures. Mine is family. Certainly people like their cat pictures too. Another good example is Google's DeepMind project AlphaGo. A computer program that plays a board game Go has defeated the world's #1 Go player, and I hope I say his name right, Kiji. The Ultimate Go Challenge game of 3 of 3 was on May 27th, 2017, so it was just last year that this happened. And what makes this so important is that, Go is a game, so it's not like you're driving a car or something in our real world, but they are using games to learn how to get the machine learning program to learn. They want it to learn how to learn. And that is a huge step. A lot of this is still in its infant stage as far as development, as we saw what happened with the, as I referred to earlier, the Uber cars. They lost their whole division because they jumped ahead too fast. So still in an infant stage, but boy, is this like the beginning of just an amazing world that is automated in ways we can't even imagine what tomorrow's going to look like. We've looked at a lot of examples of machine learning, so let's see if we can give a little bit more of a concrete definition. What is machine learning? Machine learning is the science of making computers learn and act like humans by feeding data and information without being explicitly programmed. And we see here we have a nice little diagram where we have our ordinary system. Your computer, nowadays you can even run a lot of this stuff on a cell phone because cell phones have advanced so much. And then with artificial intelligence and machine learning, it now takes the data and it learns from what happened before. And then it predicts what's going to come next. And then really the biggest part right now in machine learning that's going on is it improves on that. How do we find a new solution? So we go from descriptive, where it's learning about stuff and understanding how it fits together, to predicting what it's going to do, to post-scripting, coming up with a new solution. And when we're working on machine learning, there's a number of different diagrams that people have posted for what steps to go through. A lot of it might be very domain specific. So if you're working on photo identification versus language versus medical or physics, some of these are switched around a little bit or new things are put in. They're very specific to the domain. This is kind of a very general diagram. First, you want to define your objective. Very important to know what it is you're wanting to predict. Then you're going to be collecting the data. So once you've defined an objective, you need to collect the data that matches. You spend a lot of time in data science collecting data, and the next step, preparing the data. You got to make sure that your data is clean going in. There's the old saying, bad data in, bad answer out, or bad data out. And then once you've gone through and we've cleaned all this stuff coming in, then you're going to select the algorithm. Which algorithm are you going to use? You're going to train that algorithm. In this case, I think we're going to be working with SVM, the support vector machine. Then you have to test the model. Does this model work? Is this a valid model for what we're doing? And then once you've tested it, you want to run your prediction. You want to run your prediction or your choice or whatever output it's going to come up with. And then once everything is set and you've done lots of testing, then you want to go ahead and deploy the model. And remember I said domain specific. This is very general as far as the scope of doing something. A lot of models, you get halfway through and you realize that your data is missing something, and you have to go collect new data because you've run a test in here someplace along the line. You're saying, hey, I'm not really getting the answers I need. So there's a lot of things that are domain specific that become part of this model. This is a very general model, but it's a very good model to start with. And we do have some basic divisions of what machine learning does that's important to know. For instance, do you want to predict a category? Well, if you're categorizing things, that's classification. For instance, whether the stock price will increase or decrease. So in other words, I'm looking for a yes-no answer. Is it going up or is it going down? And in that case, we'd actually say, is it going up? True. If it's not going up, it's false, meaning it's going down. This way, it's a yes-no, 0, 1. Do you want to predict a quantity? That's regression. So remember, we just did classification. Now we're looking at regression. These are the two major divisions in what data is doing. For instance, predicting the age of a person based on the height, weight, health, and other factors. So based on these different factors, you might guess how old a person is. And then there are a lot of domain-specific things, like do you want to detect an anomaly? That's anomaly detection. And this is actually very popular right now. For instance, you want to detect money withdrawal anomalies. You want to know when someone's making a withdrawal that might not be their own account. We've actually brought this up because this is really big right now. If you're predicting the stock, whether to buy stock or not, you want to be able to know if what's going on in the stock market is an anomaly. Use a different prediction model because something else is going on. You got to pull out new information in there. Or is this just the norm? I'm going to get my normal return on my money invested. So being able to detect anomalies is very big in data science these days. Another question that comes up, which is on what we call untrained data, is do you want to discover structure in unexplored data? And that's called clustering. For instance, finding groups of customers with similar behavior given a large database of customer data containing their demographics and past buying records. And in this case, we might notice that anybody who's wearing a certain set of shoes goes shopping at certain stores, or whatever it is, they're going to make certain purchases. By having that information, it helps us to market or group people together so that we can now explore that group and find out what it is we want to market to them if you're in the marketing world. And that might also work in just about any arena. You might want to group people together, whether they're based on their different areas and investments and financial background, whether you're going to give them a loan or not. Before you even start looking at whether they're a valid customer for the bank, you might want to look at all these different areas and group them together based on unknown data. So you don't know what the data is going to tell you, but you want to cluster people together that come together. Let's take a quick detour for quiz time. Oh, my favorite. So we're going to have a couple questions here under our quiz time, and we'll be posting the answers in the part 2 of this tutorial. So let's go ahead and take a look at these quiz times questions, and hopefully you'll get them all right, and it'll get you thinking about how to process data and what's going on. Can you tell what's happening in the following cases? Of course, you're sitting there with your cup of coffee and you have your checkbox and your pen trying to figure out what's your next step in your data science analysis. So the first one is grouping documents into different categories based on the topic and content of each document. Very big these days. You have legal documents, you have maybe it's a sports group documents, maybe you're analyzing newspaper postings. But certainly having that automated is a huge thing in today's world. B, identifying handwritten digits in images correctly. So we want to know whether they're writing an A or capital A, B, C. What are they writing out in their handwriting? C, behavior of a website indicating that the site is not working as designed. D, predicting salary of an individual based on his or her years of experience. Boy, HR hiring setup there. So stay tuned for part 2. We'll go ahead and answer these questions when we get to the part 2 of this tutorial. Or you can just simply write at the bottom and send a note to Simplilearn, and they'll follow up with you on it. Back to our regular content. And these last few bring us into the next topic, which is another way of dividing our types of machine learning, and that is with supervised, unsupervised, and reinforcement learning. Supervised learning is a method used to enable machines to classify, predict objects, problems, or situations based on labeled data fed to the machine. And in here you see we have a jumble of data with circles, triangles, and squares, and we label them. We have what's a circle, what's a triangle, what's a square, and we have our model training, and it trains it so we know the answer. Very important, when you're doing supervised learning, you already know the answer to a lot of your information coming in. So you have a huge group of data coming in, and then you have new data coming in. So we've trained our model. The model now knows the difference between a circle, a square, a triangle. And now that we've trained it, we can send in this case, a square and a circle goes in, and it predicts that the top one's a square and the next one's a circle. And you can see that this is being able to predict whether someone's going to default on a loan, because I was talking about banks earlier. Supervised learning on stock market, whether you're going to make money or not. That's always important. And if you are looking to make a fortune in the stock market, keep in mind it is very difficult to get all the data correct on the stock market. It is it fluctuates in ways really hard to predict. So it's quite a roller coaster ride. If you're running machine learning on the stock market, you start realizing you really have to dig for new data. So we have supervised learning. And if you have supervised, we need unsupervised learning. In unsupervised learning, machine learning model finds the hidden pattern in an unlabeled data. So in this case, instead of telling it what the circle is, and what a triangle is, and what a square is, it goes in there and looks at them and says, for whatever reason, it groups them together. Maybe it'll group it by the number of corners. And it notices that a number of them all have 3 corners, a number of them all have 4 corners, and a number of them all have no corners. And it's able to filter those through and group them together. We talked about that earlier with looking at a group of people who are out shopping. We want to group them together to find out what they have in common. And of course, once you understand what people have in common, maybe you have one of them who's a customer at your store, or you have 5 of them are customer at your store, and they have a lot in common with 5 others who are not customers at your store. How do you market to those 5 who aren't customers at your store yet? They fit the demographics of who's going to shop there, and you'd like them to shop at your store, not the one next door. Of course, this is a simplified version. You can see very easily the difference between a triangle and a circle, which might not be so easy in marketing. Reinforcement learning. Reinforcement learning is an important type of machine learning where an agent learns how to behave in an environment by performing actions and seeing the result. And we have here where in this case, a baby. It's actually great that they used an infant for this slide because the reinforcement learning is very much in its infant stages. But it's also probably the biggest machine learning demand out there right now, or in the future, it's going to be coming up over the next few years, is reinforcement learning and how to make that work for us. And you can see here where we have our action. In the action in this one, it goes into the fire. Hopefully the baby it was just a little candle, not a giant fire pit like it looks like here. When the baby comes out, and the new state is the baby is sad and crying because they got burned on the fire. And then maybe they take another action. The baby is called the agent because it's the one taking the actions. And in this case, they didn't go into the fire. They went a different direction, and now the baby's happy and laughing and playing. Reinforcement learning is very easy to understand because that's how, as humans, that's one of the ways we learn. We learn whether it is, you burn yourself on the stove, don't do that anymore. Don't touch the stove. In the big picture, being able to have a machine learning program or an AI be able to do this is huge because now it's starting to learn how to learn. That's a big jump in the world of computer and machine learning. And we're going to go back and just kind of go back over supervised versus unsupervised learning. Understanding this is huge because this is going to come up in any project you're working on. We have in supervised learning, we have labeled data, we have direct feedback. So someone's already gone in there and said, yes, that's a triangle. No, that's not a triangle. And then you predict an outcome. So you have a nice prediction. This new set of data is coming in and we know what it's going to be. And then with unsupervised training, it's not labeled. So we really don't know what it is. There's no feedback. So we're not telling it whether it's right or wrong. We're not telling it whether it's a triangle or a square. We're not telling it to go left or right. All we do is we're finding hidden structure in the data, grouping the data together to find out what connects to each other. And then you can use these together. So imagine you have an image and you're not sure what you're looking for. So you go in and you have the unstructured data, find all these things that are connected together. And then somebody looks at those and labels them. Now you can take that labeled data and program something to predict what's in the picture. So you can see how they go back and forth and you can start connecting all these different tools together to make a bigger picture. There are many interesting machine learning algorithms. Let's have a look at a few of them. Hopefully this gives you a little flavor of what's out there. And these are some of the most important ones that are currently being used. We'll take a look at linear regression, decision tree, and the support vector machine. Let's start with a closer look at linear regression. Linear regression is perhaps one of the most well-known and well-understood algorithms in statistics and machine learning. Linear regression is a linear model. For example, a model that assumes a linear relationship between the input variables x and the single output variable y. And you'll see this if you remember from your algebra classes, y equals mx plus c. Imagine we are predicting distance traveled y from speed x. Our linear regression model representation for this problem would be y equals m times x plus c, or distance equals m times speed plus c, where m is the coefficient and c is the y-intercept. And we're going to look at two different variations of this. First, we're going to start with time is constant. And you can see we have a bicyclist. He's got his safety gear on, thank goodness. Speed equals 10 meters per second. And so over a certain amount of time, his distance equals 36 kilometers. We have a second bicyclist who's going twice the speed, or 20 meters per second. And you can guess if he's going twice the speed and time is a constant, then he's going to go twice the distance. And that's easily to compute. 36 times 2, you get 72 kilometers. And so if you had the question of how fast would somebody who's going 3 times that speed, or 30 meters per second is, you can easily compute the distance in our head. We can do that without needing a computer. But we want to do this for more complicated data. So it's kind of nice to compare the two. But let's just take a look at that and what that looks like in a graph. So in a linear regression model, we have our distance to the speed, and we have our m equals the VE slope of the line. And we'll notice that the line has a plus slope. And as the speed increases, distance also increases, hence the variables have a positive relationship. And so your speed of the person, which equals y equals mx plus c, distance traveled in a fixed interval of time, and we could very easily compute, either following the line or just knowing it's 3 times 10 meters per second, that this is roughly 102 kilometers distance that this third bicyclist has traveled. One of the key definitions on here is positive relationship. So the slope of the line is positive. As distance increase, so does speed increase. Let's take a look at our second example where we put distance is a constant. So we have speed equals 10 meters per second. They have a certain distance to go, and it takes them 100 seconds to travel that distance. And we have our second bicyclist who's still doing 20 meters per second. Since he's going twice the speed, we can guess that he'll cover the distance in about half the time, 50 seconds. And of course you could probably guess on the third one, 100 divided by 30, since he's going 3 times the speed, you could easily guess that this is 33.333 seconds time. When we put that into a linear regression model or a graph, if the distance is assumed to be constant, let's see the relationship between speed and time. And as time goes up, the amount of speed to go that same distance goes down. So now your m equals a minus VE slope of the line. As the speed increases, time decreases. Hence the variable has a negative relationship. Again, there's our definition. Positive relationship and negative relationship dependent on the slope of the line. And with a simple formula like this, and even a significant amount of data, let's see with the mathematical implementation of linear regression. And we'll take this data. So suppose we have this data set where we have x, y, x equals 1, 2, 3, 4, 5, standard series, and the y value is 3, 2, 2, 4, 3. When we take that and we go ahead and plot these points on a graph, you can see there's kind of a nice scattering, and you could probably eyeball a line through the middle of it. But we're going to calculate that exact line for linear regression. And the first thing we do is we come up here and we have the mean of xi. And remember, mean is basically the average. So we added 5 plus 4 plus 3 plus 2 plus 1 and divide by 5. And that simply comes out as 3. And then we'll do the same for y. We'll go ahead and add up all those numbers and divide by 5. And we end up with the mean value of y of I equals 2.8. Where the xi references it's an average or means value, and the yi also equals a means value of y. And when we plot that, you'll see that we can put in the y equals 2.8 and the x equals 3 in there on our graph. We kind of gave it a little different color so you could sort it out with the dashed lines on it. And it's important to note that when we do the linear regression model should go through that dot. Now let's find our regression equation to find the best fit line. Remember, we go ahead and take our y equals mx plus c, so we're looking for m and c. So to find this equation for our data, we need to find our slope of m and our coefficient of c. And we have y equals mx plus c, where m equals the sum of x minus x average times y minus y average, or y means and x means, over the sum of x minus x means squared. That's how we get the slope of the value of the line. And we can easily do that by creating some columns here where we have x, y, computers are really good about iterating through data, and so we can easily compute this and fill in a graph of data. And in our graph, you can easily see that if we have our x value of 1, and if you remember the xi, or the means value, is 3, 1 minus 3 equals a negative 2, and 2 minus 3 equals a negative 1, so on and so forth. And we can easily fill in the column of x minus xi, y minus yi, and then from those we can compute x minus xi squared and x minus xi times y minus yi. And you can guess it that the next step is to go ahead and sum the different columns for the answers we need. So we get a total of 10 for our x minus xi squared, and a total of 2 for x minus xi times y minus yi. And we plug those in, we get 2/10, which equals 0.2. So now we know the slope of our line equals 0.2. So we can calculate the value of c. That'd be the next step, is we need to know where it crosses the y-axis. And if you remember, I mentioned earlier that the linear regression line has to pass through the means value, the one that we showed earlier. We can just flip back up there to that graph, and you can see right here there's our means value, which is 3, x equals 3 and y equals 2.8. And since we know that value, we can simply plug that into our formula, y equals 0.2x plus c. So we plug that in, and we get 2.8 equals 0.2 times 3 plus c, and you can just solve for c. So now we know that our coefficient equals 2.2. And once we have all that, we can go ahead and plot our regression line. Y equals 0.2 times x plus 2.2. And then from this equation, we can compute new values. So let's predict the values of y using x equals 1, 2, 3, 4, 5 and plot the points. Remember, the 1, 2, 3, 4, 5 was our original x values. So now we're going to see what y thinks they are, not what they actually are. And when we plug those in, we get y of, designated with y of p. You can see that x equals 1 equals 2.4, x equals 2 equals 2.6, and so on and so on. So we have our y predicted values of what we think it's going to be when we plug those numbers in. And when we plot the predicted values along with the actual values, we can see the difference. And this is one of the things that's very important with linear regression in any of these models, is to understand the error. And so we can calculate the error on all of our different values. And you can see over here we plotted x and y predict. And we draw in a little line so you can sort of see what the error looks like there between the different points. So our goal is to reduce this error. We want to minimize that error value on our linear regression model. Minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. We keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. So to recap with a very simple linear regression model, we first figure out the formula of our line through the middle, and then we slowly adjust the line to minimize the error. Keep in mind, this is a very simple formula. The math gets, even though the math is very much the same, it gets much more complex as we add in different dimensions. So this is only 2 dimensions, y equals mx plus c, but you can take that out to x, z, I, j, q, all the different features in there, and they can plot a linear regression model on all of those using the different formulas to minimize the error. Let's go ahead and take a look at decision trees, a very different way to solve problems in the linear regression model. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of a tree represents a possible decision, occurrence, or reaction. We have data which tells us if it is a good day to play golf. And if we were to open this data up in a general spreadsheet, you can see we have the outlook, whether it's rainy, overcast, sunny, temperature, hot, mild, cool, humidity, windy, and did I like to play golf that day, yes or no? So we're taking a census. And certainly I wouldn't want a computer telling me when I should go play golf or not. But you could imagine if you got up in the night before, you're trying to plan your day, and it comes up and says tomorrow would be a good day for golf for you in the morning, and not a good day in the afternoon, or something like that. This becomes very beneficial, and we see this in a lot of applications coming out now where it gives you suggestions and lets you know what would fit the match for you for the next day or the next purchase or the next whatever, next meal out. In this case, is tomorrow a good day for playing golf based on the weather coming in? And so we come up and let's determine if you should play golf when the day is sunny and windy. So we found out the forecast tomorrow is going to be sunny and windy. And suppose we draw our tree like this. We're going to have our humidity, And then we have our normal, which is if you have a normal humidity, you're going to go play golf. And if the humidity is really high, then we look at the outlook. And if the outlook is sunny, overcast, or rainy, it's going to change what you choose to do. So if you know that it's a very high humidity and it's sunny, you're probably not going to play golf because you're going to be out there miserable, fighting off the mosquitoes that are out joining you to play golf with you. Maybe if it's rainy, you probably don't want to play in the rain. But if it's slightly overcast and you get just the right shadow, that's a good day to play golf and be outside, out on the green. Now in this example, you can probably make your own tree pretty easily because it's a very simple set of data going in. But the question is, how do you know what to split? Where do you split your data? What if this is much more complicated data where it's not something that you would particularly understand? Like studying cancer, they take about 36 measurements of the cancerous cells, and then each one of those measurements represents how bulbous it is, how extended it is, how sharp the edges are. Something that as a human we would have no understanding of. So how do we decide how to split that data up? And is that the right decision tree? So that's a question that's going to come up. Is this the right decision tree? For that, we should calculate entropy and information gain. Two important vocabulary words there are the entropy and the information gain. Entropy. Entropy is a measure of randomness or impurity in the data set. Entropy should be low. So we want the chaos to be as low as possible. We don't want to look at it and be confused by the images or what's going on there with mixed data. And the information gain. It is a measure of decrease in entropy after the data set is split, also known as entropy reduction. Information gain should be high, so we want our information that we get out of the split to be as high as possible. Let's take a look at entropy from the mathematical side. In this case, we're going to denote entropy as I of P of and N, where P is the probability that you're going to play a game of golf, and N is the probability where you're not going to play the game of golf. Now, you don't really have to memorize these formulas. There's a few of them out there depending on what you're working with. But it's important to note that this is where this formula is coming from, so when you see it, you're not lost when you're running your programming, unless you're building your own decision tree code in the back. And we simply have a log squared of P over P plus N minus N over P plus N times the log squared of N of P plus N. But let's break that down and see what it actually looks like when we're computing that from the computer script side. Entropy of a target class of the data set is the whole entropy. So we have entropy play golf. And when we look at this, if we go back to the data, you can simply count how many yeses and no in our complete data set for playing golf days. In our complete set, we find we have 5 days we did play golf and 9 days we did not play golf. And so our I equals, if you add those together, 9 plus 5 is 14. And so our I equals 5 over 14 and 9 over 14. That's our P and N values that we plug into that formula. And you can go to 5 over 14 equals 0.36, 9 over 14 equals 0.64. And when you do the whole equation, you get the minus 0.36 log root squared of 0.36 minus 0.64 log squared root of 0.64. And we get a set value. We get 0.94. So we now have a full entropy value for the whole set of data that we're working with. And we want to make that entropy go down. And just like we calculated the entropy out for the whole set, we can also calculate entropy for playing golf and the outlook. Is it going to be overcast or rainy or sunny? And so we look at the entropy, we have P of sunny times E of 3 of 2. And that just comes out how many sunny days yes and how many sunny days no over the total, which is 5. Don't forget to put we'll divide that 5 out later on. Equals P overcast equals 4 comma 0 plus rainy equals 2 comma 3. And then when you do the whole setup, we have 5 over 14. Remember I said there was a total of 5? 5 over 14 times the I of 3 of 2 plus 4 over 14 times the 4 comma 0 and 514 over I of 2, 3. And so we can now compute the entropy of just the part that has to do with the forecast. And we get 0.693. Similarly, we can calculate the entropy of other predictors like temperature, humidity, and wind. And so we look at the gain outlook. How much are we going to gain from this? Entropy play golf minus entropy play golf outlook. And we can take the original 0.94 for the whole set minus the entropy of just the rainy day and temperature, and we end up with a gain of 0.247. So this is our information gain. Remember, we define entropy and we define information gain. The higher the information gain, the lower the entropy, the better. The information gain of the other three attributes can be calculated in the same way. So we have our gain for temperature equals 0.029. We have our gain for humidity equals 0.152, and our gain for a windy day equals 0.048. And if you do a quick comparison, you'll see the 0.247 is the greatest gain of information, so that's the split we want. Now let's build the decision tree. So we have the outlook. Is it going to be sunny, overcast, or rainy? That's our first split because that gives us the most information gain. And we can continue to go down the tree using the different information gains with the largest information. We can continue down the nodes of the tree where we choose the attribute with the largest information gain as the root node, and then continue to split each subnode with the largest information gain that we can compute. And although it's a little bit of a tongue twister to say all that, you can see that it's a very easy to view visual model. We have our outlook. We split it three different directions. If the outlook is overcast, we're going to play. And then we can split those further down if we want. So if the outlook is sunny, but then it's also windy, if it's windy, we're not going to play. If it's not windy, we'll play. So we can easily build a nice decision tree to guess what we would like to do tomorrow and give us a nice recommendation for the day. So we want to know if it's a good day to play golf when it's sunny and windy. Remember the original question that came out? Tomorrow's weather report is sunny and windy. You can see by going down the tree, we go outlook sunny, outlook windy. We're not going to play golf tomorrow. So our little smartwatch pops up and says, I'm sorry, tomorrow's not a good day for golf. It's going to be sunny and windy. And if you're a huge golf fan, you might go, uh-oh, it's not a good day to play golf. We can go in and watch a golf game at home. So we'll sit in front of the TV instead of being out playing golf in the wind. Now that we looked at our decision tree, let's look at the third one of our algorithms we're investigating. Support vector machine. Support vector machine is a widely used classification algorithm. The idea of support vector machine is simple. The algorithm creates a separation line which divides the classes in the best possible manner. For example, dog or cat, disease or no disease. Suppose we have a labeled sample data which tells height and weight of males and females. A new data point arrives and we want to know whether it's going to be a male or a female. So we start by drawing a line. We draw decision lines, but if we consider decision line 1, then we will classify the individual as a male. And if we consider decision line 2, then it will be a female. So you can see this person kind of lies in the middle of the two groups, so it's a little confusing trying to figure out which line they should be under. We need to know which line divides the classes correctly, but how? The goal is to choose a hyperplane, and that is one of the key words they use when we talk about support vector machines. Choose a hyperplane with the greatest possible margin between the decision line and the nearest point within the training set. So you can see here we have our support vector, we have the two nearest points to it, and we draw a line between those 2 points. And the distance margin is the distance between the hyperplane and the nearest data point from either set. So we actually have a value, and it should be equally distant between the two points that we're comparing it to. When we draw the hyperplanes, we observe that line 1 has a maximum distance. So we observe that line 1 has a maximum distance margin, so we'll classify the new data point correctly. And our result on this one is going to be that the new data point is male. One of the reasons we call it a hyperplane versus a line is that a lot of times we're not looking at just weight and height. We might be looking at 36 different features or dimensions. And so when we cut it with a hyperplane, it's more of a three-dimensional cut in the data, or multi-dimensional. It cuts the data a certain way. And each plane continues to cut it down until we get the best fit or match. Let's understand this with the help of an example. Problem statement. I always start with a problem statement when you're going to put some code together. We're going to do some coding now. Classifying muffin and cupcake recipes using support vector machines. So the cupcake versus the muffin. Let's have a look at our data set. And we have the different recipes here. We have a muffin recipe that has so much flour. I'm not sure what measurement 55 is in, but it has 55, maybe it's ounces? But it has a certain amount of flour, a certain amount of milk, sugar, butter, egg, baking powder, vanilla, and salt. And so based on these measurements, we want to guess whether we're making a muffin or a cupcake. And you can see in this one, we don't have just two features. We don't just have height and weight as we did before between the male and female. In here, we have a number of features. In fact, in this, we're looking at 8 different features to guess whether it's a muffin or a cupcake. What's the difference between a muffin and a cupcake? Turns out muffins have more flour, while cupcakes have more butter and sugar. So basically the cupcake's a little bit more of a dessert, where the muffin's a little bit more of a fancy bread. But how do we do that in Python? How do we code that to go through recipes and figure out what the recipe is? And I really just want to say cupcakes versus muffins, like some big professional wrestling thing. Before we start in our cupcakes versus muffins, we are going to be working in Python. There's many versions of Python, many different editors. That is one of the strengths and weaknesses of Python, is it just has so much stuff attached to it, and it's one of the more popular data science programming packages you can use. In this case, we're going to go ahead and use Anaconda and Jupyter Notebook. The Anaconda Navigator has all kinds of fun tools. Once you're into the Anaconda Navigator, you can change environments. I actually have a number of environments on here. We'll be using Python 3.6 environment. So this is in Python version 3.6. Although it doesn't matter too much which version you use. I usually try to stay with the 3x because they're current, unless you have a project that's very specifically in version 2x. 2.7 I think is usually what most people use in the version 2. And then once we're in our Jupyter Notebook editor, I can go up and create a new file. And we'll just jump in here. In this case, we're doing SVM muffin versus cupcake. And then let's start with our packages for data analysis. And we almost always use there's a few very standard packages we use. We use import numpy. That's for number Python. They usually denote it as NP. That's very common. And then we're going to import pandas as PD. And numpy deals with number arrays. There's a lot of cool things you can do with the numpy setup as far as multiplying all the values in an array, in a numpy array, data array. Pandas, I can't remember if we're using it actually in this data set. I think we do as an import. It makes a nice data frame. And the difference between a data frame and a numpy array is that a data frame is more like your Excel spreadsheet. You have columns, you have indexes, so you have different ways of referencing it, easily viewing it, and there's additional features you can run on a data frame. And Pandas kind of sits on numpy, so you need them both in there. And then finally, we're working with the support vector machine. So from sklearn, we're going to use the sklearn model. Import SVM, support vector machine. And then as a data scientist, you should always try to visualize your data. Some data obviously is too complicated or doesn't make any sense to the human. But if it's possible, it's good to take a second look at it so that you can actually see what you're doing. Now for that, we're going to use two packages. We're going to import matplotlibary.pyplot as PLT. Again, very common. And we're going to import Seaborn as SNS. And we'll go ahead and set the font scale in the SNS right in our import line. That's what this semicolon followed by a line of data. We're going to set the SNS. And these are great because the Seaborn sits on top of matplotlibary, just like Pandas sits on numpy. So it adds a lot more features and uses and control. We're obviously not going to get into matplotlibary and Seaborn. That'd be its own tutorial. We're really just focusing on the SVM, the support vector machine from sklearn. And since we're in Jupyter Notebook, we have to add a special line in here for our matplotlibary. And that's your percentage sign or ampersand matplotlibary in line. Now, if you're doing this in just a straight code project, a lot of times I use like Notepad++, and I'll run it from there. You don't have to have that line in there because it'll just pop up as its own window on your computer, depending on how your computer's set up. Because we're running this in the Jupyter Notebook as a browser setup, this tells it to display all of our graphics right below on the page. So that's what that line is for. I remember the first time I ran this, I didn't know that, and I had to go look that up years ago. It was quite a headache. So matplotlibary inline is just because we're running this on the web setup. And we can go ahead and run this, make sure all our modules are in. They're all imported, which is great. If you don't have them import, you'll need to go ahead and pip, use the PIP or however you do it. There's a lot of other install packages out there, although pip is the most common. And you have to make sure these are all installed on your Python setup. The next step, of course, is we got to look at the data. You can't run a model for predicting data if you don't have actual data. So to do that, let me go ahead and open this up and take a look. And we have our cupcakes versus muffins. And it's a CSV file, or .csv, meaning that it's comma-separated variable. And it's going to open it up in a nice spreadsheet for me. And you can see up here we have the type. We have muffin, 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 cupcake, cupcake, cupcake. And then it's broken up into flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we can do is we can go ahead and look at this data also in our Python. Let us create a variable recipes equals, we're going to use our pandas module, .read CSV. Remember, it's a comma-separated variable. And the file name happened to be cupcakes versus muffins. Oops, I got double brackets there. Do it this way. There we go. Cupcakes versus muffins. Because the program I loaded, or the place I saved this particular Python program is in the same folder, we can get by with just the file name. But remember, if you're storing it in a different location, you have to also put down the full path on there. And then because we're in pandas, we're going to go ahead and you can actually, inline you can do this, but let me do the full print. You can just type in recipes.head in the Jupyter Notebook. But if you're running in code in a different script, you need to go ahead and type out the whole print recipes.head. And pandas knows that that's going to do the first 5 lines of data. And if we flip back on over to the spreadsheet where we opened up our CSV file, you can see where it starts on line 2. This one calls it 0, and then 2, 3, 4, 5, 6 is going to match. Go and close that out because we don't need that anymore. And it always starts at 0. And it automatically indexes it since we didn't tell it to use an index in here. So that's the index number for the left-hand side. And it automatically took the top row as labels. So pandas using it to read a CSV is just really slick and fast. One of the reasons we love our pandas. Not just because they're cute and cuddly teddy bears. And let's go ahead and plot our data. And I'm not going to plot all of it. I'm just going to plot the sugar and flour. Now obviously you can see where they get really complicated if we have tons of different features. And so you'll break them up and maybe look at just 2 of them at a time to see how they connect. And to plot them, we're going to go ahead and use Seaborn. So that's our SNS. And the command for that is sns.lmplot. And then the 2 different variables I'm going to plot is flour and sugar. Data equals recipes. The hue equals type. And this is a lot of fun because it knows that this is pandas coming in. So this is one of the powerful things about pandas mixed with Seaborn and doing graphing. And then we're going to use a palette set 1. There's a lot of different sets in there. You can go look them up for Seaborn. We'll do a fit regular equals false, so we're not really trying to fit anything. And it's a scatter, KWS. A lot of these settings you can look up in Seaborn. Half of these you could probably leave off when you run them. Somebody played with this and found out that these were the best settings for doing a Seaborn plot. And let's go ahead and run that. And because it does it inline, it just puts it right on the page. And you can see right here that just based on sugar and flour alone, there's a definite split. And we use these models because you can actually look at it and say, hey, if I drew a line right between the middle of the blue dots and the red dots, we'd be able to do an SVM and a hyperplane right there in the middle. Then the next step is to format or pre-process our data. And we're going to break that up into 2 parts. We need a type label, and remember, we're going to decide whether it's a muffin or a cupcake. Well, a computer doesn't know muffin or cupcake, it knows 0 and 1. So, what we're going to do is we're going to create a type label, and from this we'll create a numpy array, np, where, and this is where we can do some logic. We take our recipes from our panda, and wherever type equals muffin, it's going to be 0. And then if it doesn't equal muffin, which is cupcakes, it's going to be 1. So we create our type label. This is the answer. So when we're doing our training model, remember we have to have a training data. This is what we're going to train it with, is that it's 0 or 1. It's a muffin or it's not. And then we're going to create our recipe features. And if you remember correctly from right up here, the first column is type. So we really don't need the type column because that's our muffin or cupcake. And in pandas, we can easily sort that out. We take our value recipes dot columns. That's a pandas function built into pandas. Dot values, converting them to values. So it's just the column titles going across the top. And we don't want the first one. So what we do is, since it always starts at 0, we want 1 colon till the end. And then we want to go ahead and make this a list. And this converts it to a list of strings. And then we can go ahead and just take a look and see what we're looking at for the features. Make sure it looks right. Let me go ahead and run that. And I forgot the S on recipes, so we'll go ahead and add the S in there and then run that. And we can see we have flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And that matches what we have up here, right where we printed out everything but the type. So we have our features and we have our label. Now, the recipe features is just the titles of the columns, and we actually need the ingredients. And at this point, we have a couple options. One, we could run it over all the ingredients. And when you're doing this, usually you do. But for our example, we want to limit it so you can easily see what's going on. Because if we did all the ingredients, we have, that's what, 7, 8 different hyperplanes that would be built into it. We only want to look at one so you can see what the SVM is doing. And so we'll take our recipes and we'll do just flour and sugar. Again, you can replace that with your recipe features and do all of them, but we're going to do just flour and sugar, and we're going to convert that to values. We don't need to make a list out of it because it's not string values. These are actual values on there. And we can go ahead and just print ingredients, and you can see what that looks like. And so we have just the amount of flour and sugar, just the 2 sets of plots. And just for fun, let's go ahead and take this over here and take our recipe features. And so if we decided to use all the recipe features, you'll see that it makes a nice column of different data. So it just strips out all the labels and everything, and we just have just the values. But because we want to be able to view this easily in a plot later on, we'll go ahead and take that and just do flour and sugar. And we'll run that and you'll see it's just the 2 columns. So the next step is to go ahead and fit our model. We'll go ahead and just call it model. And it's a SVM. We're using a package called SVC. And in this case, we're going to go ahead and set the kernel equals linear. So it's using a specific setup on there. And if we go to the reference on their website for the SVM, you'll see that there's 8 of them here. 3 of them are for regression. 3 are for classification. The SVC, support vector classification, is probably one of the most commonly used. And then there's also one for detecting outliers, and another one that has to do with something a little bit more specific on the model. But SVC and SVR are the 2 most commonly used, standing for support vector classifier and support vector regression. Remember, regression is an actual value, a float value or whatever you're trying to work on. And SVC is a classifier, so it's a yes, no, true, false. But for this, we want to know 0, 1, muffin, cupcake. We go ahead and create our model. And once we have our model created, we're going to do model.fit. And this is very common, especially in the sklearn. All their models are followed with the fit command. And what we put into the fit, what we're training with it, is we're putting in the ingredients, which in this case we limited to just flour and sugar. And the type label, is it a muffin or a cupcake? Now, in more complicated data science series, you'd want to split into, we won't get into that today, we split it into training data and test data, and they even do something where they split it into thirds, where a third is used for where you switch between which one's training and test. There's all kinds of things that go into that, and it gets very complicated when you get to the higher end. Not overly complicated, just an extra step which we're not going to do today because this is a very simple set of data. And let's go ahead and run this, and now we have our model fit. And I got an error here, so let me fix that real quick. It's capital SVC, it turns out. I did it lowercase. Support vector classifier. There we go. Let's go ahead and run that. And you'll see it comes up with all this information that it prints out automatically. These are the defaults of the model. You notice that we changed the kernel to linear. And there's our kernel linear on the printout. And there's other different settings you can mess with. We're going to just leave that alone for right now. For this, we don't really need to mess with any of those. So next, we're going to dig a little bit into our newly trained model. And we're going to do this so we can show you on a graph. And let's go ahead and get the separating. And we're going to say we're going to use a W for our variable on here. And we're going to do model.coefficient_0. So what the heck is that? Again, we're digging into the model. So we've already got a prediction and a train. This is the math behind it that we're looking at right now. And so the W is going to represent two different coefficients. And if you remember, we had y equals mx plus c. So these coefficients are connected to that, but in two-dimensional. It's a plane. We don't want to spend too much time on this because you can get lost in the confusion of the math. So if you're a math whiz, this is great. You can go through here and you'll see that we have a equals minus w of 0 over w of 1. Remember, there's two different values there. And that's basically the slope that we're generating. And then we're going to build an XX. What is XX? We're going to set it up to a numpy array. There's our np dot line space. So we're creating a line of values between 30 and 60. So it just creates a set of numbers for x. And then if you remember correctly, we have our formula y equals the slope times x plus the intercept. Well, to make this work, we can do this as yy equals the slope times each value in that array. That's the neat thing about numpy. So when I do a times xx, which is a whole numpy array of values, it multiplies a across all of them. And then it takes those same values and we subtract the model intercept. That's your, remember we had mx plus c, so that'd be the c from the formula, y equals mx plus c. And that's where all these numbers come from. A little bit confusing because it's digging out of these different arrays. And then what we want to do is we're going to take this and we're going to go ahead and plot it. So plot the parallels to separating hyperplane that pass through the support vectors. And so we're going to create B equals a model support vectors. Pulling our support vectors out there. Here's our YY, which we now know is a set of data. And we have we're going to create YY down equals A times XX plus B1 minus A times B0. And then model support vector B is going to be set that to a new value, the -1 setup. And YY up equals A times XX plus B1 minus A times B0. And we can go ahead and just run this to load these variables up. If you wanted to understand a little bit more of what's going on, you can see if we print YY, we just run that, you can see it's an array. This is a line. It's going to have, in this case, between 30 and 60, so there's going to be 30 variables in here. And the same thing with YY up, YY down. And we'll plot those in just a minute on a graph so you can see what those look like. You just go ahead and delete that out of here and run that so it loads up the variables. Nice clean slate. I'm just going to copy this from before. Remember this, our SNS, our seaborn plot, LM plot, flour, sugar. And I'll just go ahead and run that real quick so you can see remember what that looks like. It's just a straight graph on there. And then one of the neat things is because seaborn sits on top of pyplot, we can do the pyplot for the line going through. And that is simply plt.plot. And that's our XX. and YY are two corresponding values, XY. And then somebody played with this to figure out that the line width equals 2 and the color black would look nice. So let's go ahead and run this whole thing with the pie plot on there. And you can see when we do this, it's just doing flour and sugar on here. Corresponding line between the sugar and the flour and the muffin versus cupcake. And then we generated the support vectors, the YY down and YY up. So let's take a look and see what that looks like. So we'll do our PL plot. And again, this is all against XX, our X value. But this time we have YY down. And let's do something a little fun with this. We can put in a K dash dash. That just tells it to make it a dotted line. And if we're going to do the down one, we also want to do the up one. So here's our YY up. And when we run that, it adds both sets of line. And so here's our support, and this is what you expect. You expect these two lines to go through the nearest data point. So the dashed lines go through the nearest muffin and the nearest cupcake when it's plotting it. And then your SVM goes right down the middle. So it gives it a nice split in our data, and you can see how easy it is to see, based just on sugar and flour, which one's a muffin or a cupcake. Let's go ahead and create a function to predict muffin or cupcake. I've got my recipes I pulled off the internet, and I want to see the difference between a muffin or a cupcake. And so we need a function to push that through. And we'll create a function with def. And let's call it muffin or cupcake. And remember, we're just doing flour and sugar today. We're not doing all the ingredients. And that actually is a pretty good split. You really don't need all the ingredients to know it's flour and sugar. And let's go ahead and do an if-else statement. So if model predict is of flour and sugar equals 0. So we take our model and we run a predict. It's very common in sklearn where you have a dot predict. You put the data in, and it's going to return a value. In this case, if it equals 0, then print you're looking at a muffin recipe. Else, if it's not 0, that means it's 1, then you're looking at a cupcake recipe. That's pretty straightforward for a function, or def for definition. DEF is how you do that in Python. And of course, if you're going to create a function, you should run something in it. And so let's run a cupcake, and we're going to send it values 50 and 20, a muffin or a cupcake. I don't know what it is. And let's run this and just see what it gives us. And it says, oh, it's a muffin. You're looking at a muffin recipe. So it very easily predicts whether we're looking at a muffin or a cupcake recipe. Let's plot this. There we go. Plot this on the graph so we can see what that actually looks like. And I'm just going to copy it and paste it from below, where we're plotting all the points in there. So this is nothing different than what we did before. If I run it, you'll see it has all the points and the lines on there. And what we want to do is we want to add another point. And we'll do PLT plot. And if you remember correctly, we did, for our test, we did 50 and 20. And then somebody went in here and decided we'll do YO for yellow, or it's kind of an orangish yellow color is going to come out. Marker size 9. Those are settings you can play with. Somebody else played with them to come up with the right setup so it looks good. And you can see there it is graphed, clearly a muffin. In this case, in cupcakes versus muffins, the muffin has won. And if you'd like to do your own muffin cupcake contender series, you certainly can send a note down below, and the team at Simplilearn will send you over the data they use for the muffin and cupcake. And that's true of any of the data. We didn't actually run a plot on it earlier. We had men versus women. You can also request that information to run it on your data setup so you can test that out. So to go back over our setup, we went ahead for our support vector machine code. We did a predict 40 parts flour, 20 parts sugar. I think it was different than the one we did, whether it's a muffin or a cupcake. Hence, we have built a classifier using SVM, which is able to classify if a recipe is of a cupcake or a muffin, which wraps up our cupcake versus muffin. So the key takeaways, what is machine learning? We discussed that with some of the different aspects of machine learning on there. We went into types of machine learning. If you memorize, we have supervised, unsupervised, and reinforcement learning. We discussed regression line or best fit, and we did the building a decision tree and what the logic is behind that. And finally, we did classification using SVM, support vector machine, and we did the code in there.
Today, we are diving into machine learning, the technology behind things like Netflix recommendations, Siri, and even the face unlock of your phone. Machine learning helps devices get smarter by learning from data and predicting what we might like or need. And here's why machine learning is huge for your career. Right now, machine learning jobs are among the fastest growing roles worldwide. Companies in every industry, tech, healthcare, finance, and more, are looking for people with machine learning skills to improve their products, automate tasks, and make smarter decisions. Machine learning engineers in the US earn around $112,000 on average, with plenty of room for growth as you gain experience. So if you want to jump into this exciting field, learning machine learning can open doors to high-paying, in-demand jobs. So in this video, I'll guide you through the ultimate roadmap to master machine learning in 2025, one step at a time. So let's get started. So in the first month, start with the foundations of programming. So programming is a language you'll use to communicate with your computer and bring machine learning algorithms to life. So this month is all about Python, the language of choice for most machine learning practitioners. So here's what to focus on. First, learn Python basics. Begin with Python's fundamentals like variables, data types, loops, and functions. So spend time writing small programs daily to get comfortable. After that, explore the key libraries like NumPy, Pandas, and Scikit-learn. So NumPy is for numerical operations. It makes handling large datasets faster and easier. And Pandas is to manipulate and analyze data. So Pandas allow you to filter, sort, and reshape data in a breeze. And then Scikit-learn is for implementing algorithms in just a few lines of code. So now you might have heard about R, another language used in machine learning. But don't stress about it now. Python will serve you well, especially as a beginner, because it's simpler and more flexible. So aim to spend an hour or two each day coding. By the end of this month, you'll have a solid base to build on. Now in the second month, get organized with version control and data structures. So this month is about learning how to organize and manage your code effectively and sharpening your problem-solving skills with data structures and algorithms. So first is version control with Git. So think of Git as your project history tracker. So imagine working on a big project and making changes, then realizing something went wrong. You want to go back to an earlier version, right? So that's where Git comes in. And here's what you should practice. Number one is committing changes. So save different versions of your work as you progress. And then branching, which means work on separate features without affecting your main code. And then comes merging, which means combining changes from different versions once they are ready. So you have to set up an account on GitHub or GitLab to store your projects online. So not only will this be super useful, but it'll also start building your portfolio. Now next is data structures and algorithm. So think of data structures like tools in a toolkit. So each one like arrays, stacks, queues, etc. serves a specific purpose. So here's how to approach them. Number one, arrays and lists. Now arrays and lists are for storing data in sequence. After that, you can get familiar with stacks and queues. So stacks and queues are for tasks that need ordered data access. And then you have sorting and searching algorithms. So these make your programs more efficient. And that's super important in machine learning where data can get massive. So the goal here is to build up your problem-solving skills, which are key to machine learning success. So take it slow, practice daily, and you'll see progress. Now in the third month, learn to access data with SQL. So in machine learning, a lot of work involves accessing and organizing data from databases. So SQL, a structured query language, is your ticket to getting the data you need for training ML models. So here's what you should focus on. Select and where. So these commands help you pull specific pieces of data. And then you can move on to joins. Joins usually combine data from different tables. So this is so powerful that you'll use it all the time. And then comes group by and aggregate functions. They are great for summarizing data to find patterns. So spend time working with sample databases you can find online and practice writing queries. Being comfortable with SQL will save you time when preparing data for your models. Now, after completing the third month, you can move on to mathematics, which is building your analytical mind. So this month, we are tackling the math behind machine learning. So don't worry, you don't need to be a math genius, but understanding certain concepts will make everything feel less mysterious. So in this month, you have to focus on linear algebra. So this is the math behind how models see data. So you can study vectors, matrices, and operations like multiplication. Next comes calculus. So you'll use calculus to help your models learn. So you have to focus on derivatives and gradients, which help minimize errors in your model. And then you can move on to probability and statistics. So understanding probability helps you make sense of data. So learn about distributions like normal distribution, binomial distribution, and then variance and standard deviation. So once you have learnt maths, next you'll be moving on to data handling and visualization, which is the heart of machine learning, as you all know. So with math under your belt, it's time to dig into data handling and visualization. So data preparation is vital because your model is only as good as the data you feed it. So number one comes data manipulation. So using pandas and NumPy, you'll clean and organize your data. You might be removing missing values, like clean up messy data so it doesn't confuse your model. And then you will learn transforming variables, like converting data into formats that work for models. And then you will move on to encoding categorical data, like changing text data, like female or male, into numbers. Now, once you're done with data manipulation, next comes data visualization. So visualization is how you get to see your data before training a model. So here you have to learn Matplotlib and Seaborn. So you can create line charts, histograms, scatter plots, and heat maps. So this lets you explore patterns and spot outliers. So understanding these patterns in your data is crucial for building effective models. Now, in the 6th month, you will be moving on to the machine learning fundamentals. So now it's time to start building your own models. So you will focus on two main types of machine learning this month. Number one comes the supervised learning. So this is when you train a model on labeled data, where the outcome is already known. So you'll work with algorithms like linear regression, which predicts a continuous outcome. Then you will work with decision trees, which breaks down decisions into a tree structure. And then you have support vector machines under supervised learning, which separates data into classes. Now, after supervised learning comes unsupervised learning. So here your model identifies patterns in data without labeled outcomes. So two popular techniques in unsupervised learning is number one, clustering, like k-means clustering, which means groups similar data points. And then you have dimensionality reduction. This reduces data complexity by focusing on key features. So you can use scikit-learn to try out these algorithms on sample data sets. So this will give you hands-on experience with model training, and you will learn to fine-tune them to get better results. Now, before moving on, if you are interested in advancing your career in the field of AI and machine learning, Simplilearn's postgraduate program, delivered in collaboration with Purdue University and IBM, is a perfect opportunity. This highly ranked program offers a comprehensive curriculum covering essential topics like machine learning, deep learning, NLP, computer vision, reinforcement learning, generative AI, prompt engineering, and many more. With hands-on experience to 25 plus projects and access to 20 plus cutting-edge tools, you will gain the skills needed to excel in today's competitive job market. So join now and elevate your expertise with the backing of Purdue's academic excellence and IBM's industry-leading insights. You can find the course link in the description box and pinned comments. Now moving on to the 7th month, you'll be building and training models with advanced libraries. So by now you have experimented with some basic models. So let's step it up with advanced tools like TensorFlow and PyTorch. So these libraries offer more flexibility and power. So TensorFlow and PyTorch, so here you can start with simple models and work your way up. So these libraries allow for building neural networks, which you'll be studying more on the next month. Now, once you have become familiar with TensorFlow and PyTorch, you can move on to model training and evaluation. So you have to learn to split data into training and testing sets and evaluate models using metrics like accuracy and precision. So your goal this month should be to get comfortable with these libraries and understand how they handle data and model training behind the scenes. So once you are done with this, you will be moving on to the 8th month, where you'll be dealing with advanced machine learning. So this month's concept will be number one on ensemble learning, which means combining multiple models to get better predictions. So here you'll be learning about bagging. For example, random forests. Here multiple decision trees make predictions. And then you have boosting, like AdaBoost, XGBoost. So models learn from each other's mistakes over here. And after ensemble learning comes deep learning. So here you explore neural networks which mimic the human brain. So you'll learn about neural network basics. So you can start with simple, fully connected networks, and then you can move on to backpropagation and gradient descent. So these helps your model learn and improve. So you can use TensorFlow or PyTorch to practice building neural networks. So you can work on projects to reinforce these concepts. Now moving on, you have to specialize on topics like NLP and computer vision. So machine learning applications are so powerful, and here you'll get a taste of two major fields, which is NLP or natural language processing. So here they work with text data for tasks like sentiment analysis and text classification. So you can start with basic pre-processing like tokenization, stop word removal, and move to building simple NLP models. After that, you can try out computer vision. So for image data, you have to learn CNNs, convolutional neural networks. So these networks analyze visual patterns, making them ideal for image classification. So you practice with open data sets like text, documents, and images, and apply the concepts you will learn to see results in real-world applications. Now in the 10th month, you'll be dealing with model deployment, which is bringing your models to life. So here you'll be using Flask or Django. So you can use these frameworks to create a web API so users can interact with your model. For example, build a web app that lets people upload images for classification. And then you can also try out Docker. So package your model and its dependencies so it can run on any machine. So this is super helpful for deploying models without compatibility issues. So by the end of this month, you'll be able to share your models with the world. So moving on to the 11th month, you'll be starting with cloud and production. So this month, you'll learn how to deploy models on the cloud and ensure they perform well in real-world environments. So you'll be dealing with cloud platforms like AWS, Google Cloud, or Azure. So you have to learn to deploy models on the cloud for wider accessibility and scalability. And then comes monitoring and maintenance. So understand how to track your model's performance over time and update it as needed. So these skills are essential for maintaining models in production and ensuring they stay reliable. And finally, you will be creating real-world projects and portfolio building. So here you have to choose topics that interest you and showcase your skills. So first you can start with full projects. So complete projects that go from data cleaning and model building to deployment. So ideas could be a sentiment analysis tool or an image recognition app. And then you have to build your portfolio. So organize and document your projects, host them on GitHub, and create an online portfolio to share with potential employers or collaborators. So by following this roadmap, you'll be well prepared to handle real-world machine learning challenges and have an impressive portfolio to show for it.
Welcome to Machine Learning Tutorial Part 2. My name is Richard Kirshner with the Simplilearn team. That is www.simplilearn.com. Get certified, get ahead. Today in our second tutorial, we're going to cover k-means and linear regression, along with going over the quiz questions we had during our first tutorial. What's in it for you? We're going to cover clustering. What is clustering? K-means clustering, which is one of the most common used clustering tools out there, including a flowchart to understand k-means clustering and how it functions. And then we'll do an actual Python live demo on clustering of cars based on brands. Then we're going to cover logistic regression. What is logistic regression? Logistic regression curve and sigmoid function. And then we'll do another Python code demo to classify a tumor as malignant or benign based on features. And let's start with clustering. Suppose we have a pile of books of different genres. Now we divide them into different groups like fiction, horror, education, and as we can see from this young lady, she definitely is into heavy horror. You can just tell by those eyes and the maple Canadian leaf on her shirt. But we have fiction, horror, and education, and we want to go ahead and divide our books up. Well, organizing objects into groups based on similarity is clustering. And in this case, as we're looking at the books, we're talking about clustering things with known categories. But you can also use it to explore data. So you might not know the categories, you just know that you need to divide it up in some way to conquer the data and to organize it better. But in this case, we're going to be looking at clustering in specific categories. And let's just take a deeper look at that. We're going to use k-means clustering. K-means clustering is probably the most commonly used clustering tool in the machine learning library. K-means clustering is an example of unsupervised learning. If you remember from our previous thing, it is used when you have unlabeled data. So we don't know the answer yet. We have a bunch of data that we want to cluster into different groups. Define clusters in the data based on feature similarity. So we've introduced a couple terms here. We've already talked about unsupervised learning and unlabeled data. So we don't know the answer yet. We're just going to group stuff together and see if we can find an answer of how things connect. We've also introduced feature similarity, features being different features of the data. Now with books, we can easily see fiction and horror and history books, but a lot of times with data, some of that information isn't so easy to see right when we first look at it. And so k-means is one of those tools where we can start finding things that connect, that match with each other. Suppose we have these data points and want to assign them into a cluster. Now when I look at these data points, I would probably group them into two clusters just by looking at them. I'd say two of these group of data kind of come together. But in k-means, we pick k-clusters and assign random centroids to clusters, where the k-clusters represents two different clusters. We pick k-clusters and assign random centroids to the clusters, then we compute distance from objects to the centroids. Now we form new clusters based on minimum distances and calculate the centroids. So we figure out what the best distance is for the centroid, then we move the centroid and recalculate those distances. Repeat previous two steps iteratively till the cluster centroids stop changing their positions and become static. Repeat previous two steps iteratively till the cluster centroids stop changing and the positions become static. Once the clusters become static, then k-means clustering algorithm is said to be converged. And there's another term we see throughout machine learning is converged. That means whatever math we're using to figure out the answer has come to a solution, or it's converged on an answer. Shall we see the flow chart to understand? Make a little bit more sense by putting it into a nice easy step-by-step. So we start, we choose k, we'll look at the elbow method in just a moment. We assign random centroids to clusters, and sometimes you pick the centroids, because you might look at the data in a graph and say, oh, these are probably the central points. Then we compute the distance from the objects to the centroids. We take that and we form new clusters based on minimum distance and calculate their centroids. Then we compute the distance from objects to the new centroids. And then we go back and repeat those last two steps. We calculate the distances. So as we're doing it, it brings into the new centroid, and then we move the centroid around and we figure out which objects are closest to each centroid. So the objects can switch from one centroid to the other as the centroids are moved around. And we continue that until it is converged. Let's see an example of this. Suppose we have this data set of 7 individuals and their score on two topics, A and B. So here's our subject. In this case, referring to the person taking the test. And then we have subject A, where we see what they've scored on their first subject, and we have subject B, and we can see what they score on the second subject. Now let's take two farthest apart points as initial cluster centroids. Now remember, we talked about selecting them randomly, or we can also just put them in different points and pick the furthest one apart so they move together. Either one works okay, depending on what kind of data you're working on and what you know about it. So we took the two furthest points, 1 and 1, and 5 and 7. And now let's take the two farthest apart points as initial cluster centroids. Each point is then assigned to the closest cluster with respect to the distance from the centroids. So we take each one of these points in there, we measure that distance, and you can see that if we measured each of those distances, and you use the Pythagorean theorem for a triangle in this case, because you know the x and the y, and you can figure out the diagonal line from that. Or you can just take a ruler and put it on your monitor. That'd be kind of silly, but it would work if you're just eyeballing it. You can see how they naturally come together in certain areas. Now we again calculate the centroids of each cluster. So cluster 1 and then cluster 2, and we look at each individual dot. There's 1, 2, 3, we're in one cluster. The centroid then moves over. It becomes 1.8, 2.3. So remember, it was at 1 and 1? Well, the very center of the data we're looking at would put it at the roughly 2, 2, but 1.8 and 2.3. And the second one, if we wanted to make the overall mean vector, the average vector of all the different distances to that centroid, we come up with 4, 1 and 5, 4. So we've now moved the centroids. We compare each individual's distance to its own cluster, mean, and to that of the opposite cluster, and we find, we can build a nice chart on here, that as we move that centroid around, we now have a new different kind of clustering of groups, and using Euclidean distance between the points and the mean, we get the same formula. You see new formulas coming up. So we have our individual dots, distance to the mean, centroid of the cluster, and distance to the mean, centroid of the cluster. Only individual 3 is nearer to the mean of the opposite cluster, cluster 2, than its own cluster 1. And you can see here in the diagram where we've kind of circled that one in the middle. So when we've moved the centroids of the clusters over, one of the points shifted to the other cluster because it's closer to that group of individuals. Thus, individual 3 is relocated to cluster 2, resulting in a new partition. And we regenerate all those numbers of how close they are to the different clusters. For the new clusters, we will find the actual cluster centroids. So now we move the centroids over, and you can see that we've now formed two very distinct clusters on here. On comparing the distance of each individual's distance to its own cluster mean and to that of the opposite cluster, we find that the data points are stable, hence we have our final clusters. Now, if you remember, I brought up a concept earlier, k-mean on the k-means algorithm. Choosing the right value of k will help in less number of iterations. And to find the appropriate number of clusters in a data set, we use the elbow method. And within sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And so you see what we've done here is we have the number of clusters. And as you do the same k-means algorithm over the different clusters, and you calculate what that centroid looks like, and you find the optimal, you can actually find the optimal number of clusters using the elbow of the graph, is called as the elbow method. And on this, we guessed at 2 just by looking at the data. But as you can see, the slope, you actually just look for right there where the elbow is in the slope, and you have a clear answer that we want 2 different, to start with k-means equals 2. A lot of times people end up computing k-means equals 2, 3, 4, 5 until they find the value which fits on the elbow joint. Sometimes you can just look at the data, and if you're really good with that specific domain, remember domain, I mentioned that last time, you'll know that where to pick those numbers or where to start guessing at what that k value is. So let's take this, and we're going to use a use case using k-means clustering to cluster cars into brands using parameters such as horsepower, cubic inches, make, year, etc. So we're going to use the dataset cars data, having information about 3 brands of cars, Toyota, Honda, and Nissan. We'll go back to my favorite tool, the Anaconda Navigator with the Jupyter Notebook. And let's go ahead and flip over to our Jupyter Notebook. And in our Jupyter Notebook, I'm going to go ahead and just paste the basic code that we usually start a lot of these off with. We're not going to go too much into this code because we've already discussed NumPy, we've already discussed Matplotlib, and pandas. NumPy being the number array, pandas being the pandas data frame, and Matplot for the graphing. And don't forget, since if you're using the Jupyter Notebook, you do need the Matplotlib inline so that it plots everything on the screen. If you're using a different Python editor, then you probably don't need that because it'll have a pop-up window on your computer. And we'll go ahead and run this just to load our libraries and our setup into here. The next step is, of course, to look at our data, which I've already opened up in a spreadsheet. And you can see here we have the miles per gallon, cylinders, cubic inches, horsepower, weight pounds, how heavy it is, time it takes to get to 60. My card is probably on this one at about 80 or 90. What year it is. So this is, you can actually see this is kind of older cars, and then the brand, Toyota, Honda, Nissan. So the different cars are coming from all the way from 1971, if we scroll down, to the 80s. We have between the 70s and 80s a number of cars that they've put out. And let's, when we come back here, we're going to do importing the data. So we'll go ahead and do dataset equals. And we'll use pandas to read this in, and it's from a CSV file. Remember, you can always post this in the comments and request the data files for these, either in the comments here on the YouTube video or go to Simplilearn.com and request that. The cars CSV, I put it in the same folder as the code that I've stored. So my Python code is stored in the same folder, so I don't have to put the full path. If you store them in different folders, you do have to change this and double check your name variables. And we'll go ahead and run this, and we've chosen dataset arbitrarily because it's a dataset we're importing, and we've now imported our cars CSV into the dataset. As you know, you have to prep the data, so we're going to create the X data. This is the one that we're going to try to figure out what's going on with. And then there's a number of ways to do this, but we'll do it in a simple loop so you can actually see what's going on. So we'll do for I in X dot columns. So we're going to go through each of the columns, and a lot of times it's important. I'll make lists of the columns and do this because I might remove certain columns, or there might be columns that I want to be processed differently. But for this, we can go ahead and take X of I, and we want to go fill NA, and that's a pandas command. But the question is, what are we going to fill the missing data with? We definitely don't want to just put in a number that doesn't actually mean something. And so one of the tricks you can do with this is we can take X of I, and then in addition to that, we want to go ahead and turn this into an integer, because a lot of these are integers. So we'll go ahead and keep it integers. And We add the bracket here, and a lot of editors will do this. They'll think that you're closing one bracket. Make sure you get that second bracket in there if it's a double bracket. That's always something that happens regularly. So once we have our integer of x of y, this is going to fill in any missing data with the average. And I was so busy closing one set of brackets, I forgot that the mean also has brackets in there for the pandas. So we can see here we're going to fill in all the data with the average value for that column. So if there's missing data, it's in the average of the data it does have. And then once we've done that, we'll go ahead and loop through it again and just check and see to make sure everything is filled in correctly. And we'll print, and then we take x is null, and this returns a set of the null value, or the how many lines are null, and we'll just sum that up to see what that looks like. And so when I run this, and so with the x, what we want to do is we want to remove the last column because that had the models. That's what we're trying to see, if we can cluster these things and figure out the models. There is so many different ways to sort the x out. For one, we could take the x, and we could go data set, our variable we're using, and use the iLocation, one of the features that's in pandas. And we could take that and then take all the rows and all but the last column of the data set. And at this time we could do values. We just convert it to values. So that's one way to do this. And if let me just put this down here and print x, it's a capital X we chose, and I run this, you can see it's just the values. We could also take out the values and it's not going to return anything because there's no values connected to it. What I like to do with this is, instead of doing the iLocation, which does integers, more common is to come in here and we have our data set, and we're going to do dataset dot columns. And remember, that lists all the columns. So if I come in here, let me just mark that as red, and I print dataset.columns, you can see that I have my index here. I have my MPG, cylinders, everything, including the brand, which we don't want. So the way to get rid of the brand would be to do data columns of everything but the last one, -1. So now if I print this, you'll see the brand disappears. And so I can actually just take dataset columns -1, and I'll put it right in here for the columns we're going to look at. And let's unmark this and unmark this. And now if I do an x.head, I now have a new data frame, and you can see right here we have all the different columns except for the brand at the end of the year. And it turns out when you start playing with the data set, you're going to get an error later on, and it'll say cannot convert string to float value. And that's because for some reason these things, the way they recorded them, must have been recorded as strings. So we have a neat feature in here on pandas to convert, and it is simply convert objects. And for this we're going to do convert underscore numeric equals true. And yes, I did have to go look that up. I don't have it memorized, the convert numeric in there. If I'm working with a lot of these things, I remember them, but depending on where I'm at, what I'm doing, I usually have to look it up. And we run that. Oops, I must have missed something in here. Let me double check my spelling. And when I double check my spelling, you'll see I missed the first underscore in the convert objects. And when I run this, it now has everything converted into a numeric value, because that's what we're going to be working with, is numeric values down here. And the next part is that we need to go through the data and eliminate null values. Most people, when they're doing small amounts, working with small data pools, discover afterwards that they have a null value and they have to go back and do this. So, be aware, whenever we're formatting this data, things are going to pop up, and sometimes you go backwards to fix it. And that's fine. That's just part of exploring the data and understanding what you have. And I should have done this earlier, but let me go ahead and increase the size of my window one notch. There we go. Easier to see. So we'll do for I in working with x dot columns. We'll page through all the columns. And we want to take x of I, and we're going to change that, and we're going to alter it. And so with this, we want to go ahead and fill in x of I. Pandas has the fill in a, and that just fills in any non-existent missing data. And we'll put my brackets up, and there's a lot of different ways to fill this data. If you have a really large data set, some people just void out that data and then look at it later in a separate exploration of data. One of the tricks we can do is we can take our column and we can find the means. And the means is in our quotation marks. So when we take the columns, we're going to fill in the non-existing one with the means. The problem is that returns a decimal float. So some of these aren't decimals. Certainly, we need to be a little careful of doing this, but for this example, we're just going to fill it in with the integer version of this. It keeps it on par with the other data that isn't a decimal point. And then what we also want to do is we want to double check. A lot of times you do this first part first to double check, then you do the fill, and then you do it again just to make sure you did it right. So we're going to go through and test for missing data. And one of the ways you can do that is simply go in here and take our x of I column. So it's going to go through the x of I column. It says is null. So it's going to return any place there's a null value. It actually goes through all the rows of each column is null. And then we want to go ahead and sum that. So we take that and we add the sum value. And these are all pandas. So is null is a panda command, and so is sum. And if we go through that and we go ahead and run it, and we go ahead and take and run that, you'll see that all the columns have 0 null values. So we've now tested and double checked, and our data is nice and clean. We have no null values. Everything is now a number value. We turned it into numeric. And we've removed the last column in our data. And at this point, we're actually going to start using the elbow method to find the optimal number of clusters. So we're now actually getting into the sklearn part, the k-means clustering on here. I guess we'll go ahead and zoom it up one more notch so you can see what I'm typing in here. And then from sklearn, we're going to our sklearn cluster, we're going to import k-means. I always forget to capitalize the k and the m when I do this. So it's capital K, capital M, k-means. And we'll go ahead and create a array, WCSS equals, we'll make it an empty array. If you remember from the elbow method from our slide, within the sum of squares, WSS is defined as the sum of square distance between each member of the cluster and its centroid. So we're looking at that change in differences as far as a square distance. And we're going to run this over a number of k-mean values. In fact, let's go for I in range, we'll do 11 of them. Range 0 of 11. And the first thing we're going to do is we're going to create the actual, we'll do it all lowercase. And so we're going to create this object from the k-means that we just imported. And the variable that we want to put into this is in clusters. And we're going to set that equals to I. That's the most important one because we're looking at how increasing the number of clusters changes our answer. There are a lot of settings to the k-means. Our guys in the back did a great job just kind of playing with some of them. The most common ones that you see in a lot of stuff is how you init your k-means. So we have k-means plus plus. This is just a tool to let the model itself be smart how it picks its centroids to start with, its initial centroids. We only want to iterate no more than 300 times. We have a max iteration we put in there. We have the nth init, the random state equals 0. You really don't need to worry too much about these when you're first learning this. As you start digging in deeper, you start finding that these are shortcuts that will speed up the process as far as the setup. But the big one that we're working with is the in clusters equals I. So we're going to literally train our k-means 11 times. We're going to do this process 11 times. And if you're working with big data, you know the first thing you do is you run a small sample of the data so you can test all your stuff on it. And you can already see the problem that if I'm going to iterate through a terabyte of data 11 times, and then the k-means itself is iterating through the data multiple times, that's a heck of a process. So you got to be a little careful with this. A lot of times, though, you can find your elbow, using the elbow method, find your optimal number on a sample of data, especially if you're working with larger data sources. So we want to go ahead and take our k-means and we're just going to fit it. If you're looking at any of the sklearn, very common, you fit your model. And if you remember correctly, our variable we're using is the capital X. And once we fit this value, we go back to the array we made, and we want to go ahead and just append that value on the end. And it's not the actual fit we're pinning in there, it's when it generates the value you're looking for is inertia. So k-means.inertia will pull that specific value out that we need. And let's get a visual on this. We'll do our PLT plot, and what we're plotting here is first the x-axis, which is range 0, 11, so that will generate a nice little plot there, and the WCSS for our y-axis. It's always nice to give our plot a title, and let's see, we'll just give it the elbow method for the title, and let's get some labels. So let's go ahead and do PLT X label, and what we'll do number of clusters for that, and PLT Y label, and for that we can do, there we go, WCSS, since that's what we're doing on the plot on there. And finally we want to go ahead and display our graph, which is simply PLT dot show. There we go. And because we have it set to inline, it'll appear inline. Hopefully I didn't make a type error on there. And you can see we get a very nice graph. You can see a very nice elbow joint there at 2, and again right around 3 and 4, and then after that there's not very much. Now, as a data scientist, if I was looking at this, I would do either 3 or 4, and I'd actually try both of them to see what the output looked like. And they've already tried this in the back, so we're just going to use 3 as a setup on here. And let's go ahead and see what that looks like when we actually use this to show the different kinds of cars. And so let's go ahead and apply the k-means to the cars data set. And basically we're going to copy the code that we looped through up above, where k-means equals k-means number of clusters, and we're just going to set the number of clusters to 3, since that's what we're going to look for. And you could do 3 and 4 on this and graph them just to see how they come up differently. It'd be kind of curious to look at that. But for this we're just going to set it to 3. Go ahead and create our own variable y k-means for our answers. And we're going to set that equal to, whoops, a double equal there, to k-means, but we're not going to do a fit. We're going to do a fit predict is the setup you want to use. And when you're using untrained models, you'll see a slightly different, because usually you see fit and then you see just the predict. But we want to both fit and predict the k-means on this. And that's fit underscore predict, and then our capital X is the data we're working with. And before we plot this data, we're going to do a little pandas trick. We're going to take our x value and we're going to set x as matrix. So we're converting this into a nice rows and columns kind of setup, but we're going to have columns equals none, so it's just going to be a matrix of data in here. And let's go ahead and run that. A little warning. You'll see these warnings pop up because things are always being updated. So there's like minor changes in the versions and future versions. Instead of matrix, now it's more common to set it dot values instead of doing as matrix. But as matrix works just fine for right now, and you'll want to update that later on. But let's go ahead and dive in and plot this and see what that looks like. And before we dive into plotting this data, I always like to take a look and see what I am plotting. So let's take a look at y k-means, and I'm just going to print that out down here. And we see we have an array of answers. We have 2, 1, 0, 2, 1, 2. So it's clustering these different rows of data based on the 3 different spaces it thinks it's going to be. And then let's go ahead and print x and see what we have for x. And we'll see that x is an array, it's a matrix, so we have our different values in the array. And what we're going to do, it's very hard to plot all the different values in the array. So we're only going to be looking at the first 2, or positions 0 and 1. And if you were doing a full presentation in front of the board meeting, you might actually do a little different and dig a little deeper into the different aspects, because this is all the different columns we looked at. But we'll only look at columns 1 and 2 for this to make it easy. So let's go ahead and clear this data out of here. and let's bring up our plot. And we're going to do a scatter plot here. So PLT scatter, and this looks a little complicated, so let's explain what's going on with this. We're going to take the x values, and we're only interested in y of k means equals 0, the first cluster. Okay? And then we're going to take value 0 for the x-axis, and then we're going to do the same thing here. We're only interested in k means equals 0, but we're going to take the second column. So we're only looking at the first two columns in our answer, or in the data. And then the guys in the back played with this a little bit to make it pretty. And they discovered that it looks good if it has a size equals 100. That's the size of the dots. We're going to use red for this one. And when they were looking at the data and what came out, it was definitely the Toyota on this. We're just going to go ahead and label it Toyota. Again, that's something you'd really have to explore in here as far as playing with those numbers and see what looks good. We'll go ahead and hit enter in there. And I'm just going to paste in the next two lines, which is the next two cars. And this is our Nissan and Honda. And you'll see with our scatter plot, we're now looking at where y underscore k means equals 1. And we want the 0 column, and yk means equals 2. Again, we're looking at just the first two columns, 0 and 1. And each of these rows then corresponds to Nissan and Honda. And I'll go ahead and hit enter on there. And finally, let's take a look and put the centroids on there. Again, we're going to do a scatter plot. And on the centroids, you can just pull that from our k-means, the model we created, dot cluster centers, and we're going to just do all of them in the first number and all of them in the second number, which is 0, 1, because you always start with 0 and 1. And then they were playing with the size and everything to make it look good. We'll do a size of 300. We're going to make the color yellow, and we'll label them, it's always good to have some good labels, centroids. And then we do want to do a title, PLT title, and pop up there. PLT title, because you always want to make your graphs look pretty, and we'll call it clusters of car make. And one of the features of the plot library is you can add a legend. It'll automatically bring in it since we've already labeled the different aspects of the legend with Toyota, Nissan, and Honda. And finally, we want to go ahead and show, so we can actually see it. And remember, it's inline, so if you're using a different editor that's not the Jupyter Notebook, you'll get a pop-up of this. And you should have a nice set of clusters here. So we can look at this, and we have clusters of Honda in green, Toyota in red, Nissan in purple. And you can see where they put the centroids to separate them. Now, when we're looking at this, we can also plot a lot of other different data on here because we only looked at the first two columns. This is just column 1 and 2. Or 0, 1 as you label them in computer scripting. But you can see here we have nice clusters of car make, and we were able to pull out the data, and you can see how just these two columns form very distinct clusters of data. So if you were exploring new data, you might take a look and say, well, what makes these different? Almost going in reverse, you start looking at the data and pulling apart the columns to find out why is the first group set up the way it is. Maybe you're doing loans and you want to go, well, why is this group not defaulting on their loans? And why is the last group defaulting on their loans? And why is the middle group 50% defaulting on their bank loans? And you start finding ways to manipulate the data and pull out the answers you want. So now that you've seen how to use k-mean for clustering, let's move on to the next topic. Now let's look into logistic regression. The logistic regression algorithm is the simplest classification algorithm used for binary or multi-classification problems. And we can see we have our little girl from Canada who's into horror books is back. That's actually really scary when you think about that with those big eyes. In the previous tutorial, we learned about linear regression, dependent and independent variables. So, to brush up, y equals mx plus c. A very basic algebraic function of y and x. The dependent variable is the target class variable we are going to predict. The independent variables, x1 all the way up to xn, are the features or attributes we're going to use to predict the target class. We know what a linear regression looks like, but using the graph we cannot divide the outcome into categories. It's really hard to categorize 1.5, 3.6, 9.8. For example, a linear regression graph can tell us that with increase in number of hours studied, the marks of a student will increase, but it will not tell us whether the student will pass or not. In such cases where we need the output as categorical value, we will use logistic regression. And for that, we're going to use the sigmoid function. So you can see here we have our marks, 0 to 100, number of hours studied. That's going to be what they're comparing it to in this example. And we usually form a line that says y equals mx plus c. And when we use the sigmoid function, we have p equals 1 over 1 plus e to the minus y. It generates a sigmoid curve. And so you can see right here, when you take the ln, which is the natural logarithm, I always thought it should be nl, not ln. That's just the inverse of e, or e to the minus y. And so when we do this, we get ln of p over 1 minus p equals m times x plus c. That's the sigmoid curve function we're looking for. And we can zoom in on the function, and you'll see that the function, as it derives, goes to 1 or to 0, depending on what your x value is. And the probability, if it's greater than 0.5, the value is automatically rounded off to 1, indicating that the student will pass. So if they're doing a certain amount of studying, they will probably pass. Then you have a threshold value at the 0.5. It automatically puts that right in the middle usually. And your probability, if it's less than 0.5, the value rounded off to 0, indicating the student will fail. So if they're not studying very hard, they're probably going to fail. This, of course, is ignoring the outliers of that one student who's just a natural genius and doesn't need any studying to memorize everything. That's not me, unfortunately. I have to study hard to learn new stuff. Problem statement. To classify whether a tumor is malignant or benign. And this is actually one of my favorite data sets to play with because it has so many features, and when you look at them, you really are hard to understand. You can't just look at them and know the answer. So it gives you a chance to kind of dive into what data looks like when you aren't able to understand the specific domain of the data. But I also want you to remind you that in the domain of medicine, if I told you that my probability was really good at classified things at, say, 90% or 95%, and I'm classifying whether you're going to have a malignant or a benign tumor, I'm guessing that you're going to go get it tested anyways. So you got to remember the domain we're working with. So why would you want to do that if you know you're just going to go get a biopsy because, you know, it's that serious? This is like an all or nothing. Just referencing the domain, it's important. It might help the doctor know where to look just by understanding what kind of tumor it is. So it might help them or aid them in something they missed from before. So let's go ahead and dive into the code, and I'll come back to the domain part of it in just a minute. So use case, and we're going to do our normal imports here, where we're importing NumPy, Pandas, Seaborn, the Matplot library, and we're going to do Matplot library inline since I'm going to switch over to Anaconda. So let's go ahead and flip over there and get this started. So I've opened up a new window in my Anaconda Jupyter Notebook. And by the way, Jupyter Notebook, you don't have to use Anaconda for the Jupyter Notebook. I just love the interface and all the tools that Anaconda brings. So we got our import NumPy as in P for our NumPy number array. We have our Pandas PD. We're going to bring in Seaborn to help us with our graphs as SNS. So many really nice tools in both Seaborn and Matplot library. Then we'll do our Matplot library.pyplot as PLT, and then of course we want to let it know to do it in line. And let's go ahead and just run that so it's all set up. And we're just going to call our data, not creative today, equals PD, and this happens to be in a CSV file. So we'll use the pd.read_CSV, and I happen to name the file, or renamed it, data for p2.csv. You can, of course, write in the comments below the YouTube and request for the data set itself, or go to the Simplilearn website, and we'll be happy to supply that for you. And let's just open up the data before we go any further, and let's just see what it looks like in a spreadsheet. So when I pop it open in a local spreadsheet, and this is just a CSV file, comma separated variables, we have an ID, so I guess they categorize this for reference or what ID, which test was done. The diagnosis, M for malignant, B for benign, so there's two different options on there. And that's what we're going to try to predict is the M and B and test it. And then we have like the radius mean or average, the texture average, perimeter mean, area mean, smoothness. I don't know about you, but unless you're a doctor in the field, most of the stuff, I mean, you can guess what concave means just by the term concave, but I really wouldn't know what that means in the measurements they're taking. So they have all kinds of stuff like how smooth it is, the symmetry, and these are all float values. We can just page through them real quick. And you'll see there's, I believe, 36 if I remember correctly in this one. So there's a lot of different values they take and all these measurements they take when they go in there and they take a look at the different growth, the tumorous growth. So back in our data, and I put this in the same folder as the code. So I saved this code in that folder. Obviously, if you have it in a different location, you want to put the full path in there. And we'll just do pandas first 5 lines of data with the data.head. When we run that, we can see that we have pretty much what we just looked at. We have an ID, we have a diagnosis. If we go all the way across, you'll see all the different columns coming across displayed nicely for our data. And while we're exploring the data, our Seaborn, which we referenced as SNS, makes it very easy to go in here and do a joint plot. You'll notice very similar to, because it is sitting on top of the plot library, so the joint plot does a lot of work for us. And we're just going to look at the first 2 columns that we're interested in, the radius mean and the texture mean. We'll just look at those 2 columns. And data equals data. So that tells it which 2 columns we're plotting and that we're going to use the data that we pulled in. And let's just run that. And it generates a really nice graph on here. And there's all kinds of cool things on this graph to look at. I mean, we have the texture mean and the radius mean, obviously the axes. You can also see, and one of the cool things on here is you can also see the histogram. They show that for the radius mean. Where is the most common radius mean come up and where the most common texture is. So we're looking at on each growth its average texture and on each radius its average radius on there. It gets a little confusing because we're talking about the individual object's average, and then we can also look over here and see the histogram showing us the median or how common each measurement is. And that's only 2 columns, so let's dig a little deeper into Seaborn. They also have a heat map. And if you're not familiar with heat maps, a heat map just means it's in color. That's all that means. Heat map. I guess the original ones were plotting heat density on something, and so ever since then it's just called a heat map. And we're going to take our data and get our corresponding numbers to put that into the heat map. And that's simply data.corr for that. That's a pandas expression. So remember, we're working in a pandas data frame, so that's one of the cool tools in pandas for our data. And let's just pull that information into a heat map and see what that looks like. And you'll see that we're now looking at all the different features. We have our ID, we have our texture, we have our area, our compactness, concave points. And if you look down the middle of this chart, diagonal, going from the upper left to bottom right, it's all white. That's because when you compare texture to texture, they're identical. So they're 100%, or in this case, a perfect 1 in their correspondence. And you'll see that when you look at, say, area, or right below it, it has almost a black on there when you compare it to texture. So these have almost no corresponding data. They don't really form a linear graph or something that you can look at and say how connected they are. They're very scattered data. This is really just a really nice graph to get a quick look at your data. It doesn't so much change what you do, but it changes verifying. So when you get an answer or something like that, or you start looking at some of these individual pieces, you might go, hey, that doesn't match. According to showing our heat map, this should not correlate with each other. And if it is, you're going to have to start asking, well, why? What's going on? What else is coming in there? But it does show some really cool information on here. I mean, we can see from the ID, there's no real one feature that just says, if you go across the top line, that lights up. There's no one feature that says, hey, if the area is a certain size, then it's going to be benign or malignant. It says there's some that sort of add up. And that's a big hint in the data that we're trying to ID this, whether it's malignant or benign. That's a big hint to us as data scientists to go, okay, we can't solve this with any one feature. It's going to be something that includes all the features or many of the different features to come up with a solution for it. And while we're exploring the data, let's explore one more area and let's look at data.isNull. We want to check for null values in our data. If you remember from earlier in this tutorial, we did it a little differently where we added stuff up and summed them up. You can actually, with pandas, do it really quickly, data.isNull and sum it, and it's going to go across all the columns. So when I run this, you're going to see all the columns come up with no null data. So we've just to rehash these last few steps, we've done a lot of exploration. We have looked at the first two columns and seen how they plot with the seaborn, with a joint plot which shows both the histogram and the data plotted on the XY coordinates. And obviously you can do that more in detail with different columns and see how they plot together. And then we took and did the seaborn heat map, the SNS heat map of the data. And you can see right here where it did a nice job showing us some bright spots where stuff correlates with each other and forms a very nice combination or points of scattering points. And you can also see areas that don't. And then finally we went ahead and checked the data. Is the data null value? Do we have any missing data in there? Very important step because it'll crash later on. If you forget to do this step, it will remind you when you get that nice error code that says null values. Okay, so not a big deal if you miss it, but it's no fun having to go back when you're in a huge process and you've missed this step, and now you're 10 steps later and you got to go remember where you were pulling the data in. So we need to go ahead and pull out our x and our y. So we just put that down here, and we'll set the x equal to, and there's a lot of different options here. Certainly we could do x equals all the columns except for the first two, because if you remember the first two is the ID and the diagnosis. So that certainly would be an option. But what we're going to do is we're actually going to focus on the worst radius, the worst texture, parameter, area, smoothness, compactness, and so on. One of the reasons to start dividing your data up when you're looking at this information is sometimes the data will be the same data coming in. So if I have two measurements coming into my model, it might overweigh them. It might overpower the other measurements because it's basically taking that information in twice. That's a little bit past the scope of this tutorial. What I want you to take away from this, though, is that we are dividing the data up into pieces, and our team in the back went ahead and said, hey, let's just look at the worst. So I'm going to create an array, and you'll see this array, radius worst, texture worst, perimeter worst. We've just taken the worst of the worst, and I'm just going to put that in my x. So this x is still a pandas data frame, but it's just those columns. And our y, if you remember correctly, is going to be, oops, hold on one second. It's not x, it's data. There we go. So x equals data, and then it's a list of the different columns, the worst of the worst. And if we're going to take that, then we have to have our answer for our y, for the stuff we know. And if you remember correctly, we're just going to be looking at the diagnosis. That's all we care about is what is it diagnosed? Is it benign or malignant? And since it's a single column, we can just do diagnosis. Oh, I forgot to put the brackets. There we go. Okay. So it's just diagnosis on there. And we can also real quickly do like x dot head if you want to see what that looks like. And y dot head. And run this. And you'll see it only does the last one. I forgot about that if you don't do print. You can see that the y dot head is just MMM because the first ones are all malignant. And if I run this, the x dot head is just the first 5 values of radius worst, texture worst, parameter worst, area worst, and so on. I'll go ahead and take that out. So moving down to the next step, we've built our two data sets, our answer and then the features we want to look at. In data science, it's very important to test your model. So we do that by splitting the data. And from sklearn model selection, we're going to import train test split. So we're going to split it into two groups. There are so many ways to do this. I noticed in one of the more modern ways, they actually split it into 3 groups, and then you model each group and test it against the other groups. So you have all kinds of, and there's reasons for that, which is past the scope of this, and for this particular example isn't necessary. For this, we're just going to split it into 2 groups, one to train our data and one to test our data. And the sklearn model selection, we have train test split. You could write your own quick code to do this where you just randomly divide the data up into 2 groups, but they do it for us nicely. And we can actually do it in one statement with this, where we're going to generate 4 variables, capital X train, capital X test. So we have our training data we're going to use to fit the model, and then we need something to test it. And then we have our Y train, so we're going to train the answer, and then we have our test. So this is the stuff we want to see how good it did on our model. And we'll go ahead and take our train test split that we just imported, and we're going to do X and our Y, our two different data that's going in for our split. And then the guys in the back came up and wanted us to go ahead and use a test size equals 0.3. That's test underscore size. Random state, it's always nice to kind of switch your random state around, but not that important. What this means is that the test size is we're going to take 30% of the data and we're going to put that into our test variables, our Y test and our X test. And we're going to do 70% into the X train and the Y train. So we're going to use 70% of the data to train our model and 30% to test it. Let's go ahead and run that and load those up. So now we have all our stuff split up and all our data ready to go. And now we get to the actual logistics part. We're actually going to create our model. So let's go ahead and bring that in from sklearn. We're going to bring in our linear model and we're going to import logistic regression. That's the actual model we're using. And this, we'll call it log model. Oops, there we go, model. And let's just set this equal to our logistic regression that we just imported. So now we have a variable log model set to that class for us to use. And with most of the models in the sklearn, we just need to go ahead and do a fit on there. And we use our X train that we separated out with our Y train. Now let's go ahead and run this. So once we've run this, we'll have a model that fits this data, that 70% of our training data. And of course it prints this out that tells us all the different variables that you can set on there. There's a lot of different choices you can make. But for what we're doing, we're just going to let all the defaults sit. We don't really need to mess with those on this particular example. And there's nothing in here that really stands out as super important until you start fine-tuning it. But for what we're doing, the basics will work just fine. And then we need to go ahead and test out our model. Is it working? So let's create a variable yPredict, and this is going to be equal to our log model. And we want to do a predict. Again, very standard format for the sklearn library is taking your model and doing a predict on it. And we're going to test yPredict against the Y test. So we want to know what the model thinks it's going to be. That's what our yPredict is. And with that, we want the capital X test. So we have our train set and our test set, and now we're going to do our yPredict. And let's go ahead and run that. And if we print yPredict, let me go ahead and run that, you'll see it comes up and it prints a nice array of B and M for benign and malignant for all the different test data we put in there. So it does pretty good. We're not sure exactly how good it does, but we can see that it actually works and is functional. It was very easy to create. You'll always discover with our data science that as you explore this, you spend a significant amount of time prepping your data and making sure your data coming in is good. There's a saying, good data in, good answers out. Bad data in, bad answers out. That's only half the thing. That's only half of it. Selecting your models becomes the next part as far as how good your models are. And then, of course, fine-tuning it depending on what model you're using. So we come in here, we want to know how good this came out. So we have our yPredict here, logModel.predict X test. So for deciding how good our model is, we're going to go from the sklearn.metrics, we're going to import classification report. And that just reports how good our model is doing, and then we're going to feed it the model data. And let's just print this out. And we'll take our classification report, and we're going to put into there our test, our actual data. So this is what we actually know is true. And our prediction, what our model predicted for that data on the test side. And let's run that and see what that does. So we pull that up, you'll see that we have a precision for benign and malignant, B and M. And we have a precision of 93 and 91, a total of 92. So it's kind of the average between these two of 92. There's all kinds of different information on here. Your F1 score, your recall, your support coming through on this. And for this, I'll go ahead and just flip back to our slides that they put together for describing it. And so here we're going to look at the precision using the classification report. And you see this is the same printout I had up above. Some of the numbers might be different because it does randomly pick out which data we're using. So this model is able to predict the type of tumor with 91% accuracy. So when we look back here, you will see where we have benign and malignant. It actually is 92 coming up here. But we're looking at about a 92, 91% precision. And remember, I reminded you about domain. So when we're talking about the domain of a medical domain with a very catastrophic outcome, at 91 or 92% precision, you're still going to go in there and have somebody do a biopsy on it. Very different than if you're investing money and there's a 92% chance you're going to earn 10% and 8% chance you're going to lose 8%. You're probably going to bet the money, because at that odds it's pretty good that you'll make some money, and in the long run, you do that enough, you definitely will make money. And also with this domain, I've actually seen them use this to identify different forms of cancer. That's one of the things that they're starting to use these models for, because then it helps the doctor know what to investigate. So that wraps up this section. We're going to go in there and let's discuss the answer to the quiz asked in Machine Learning Tutorial Part 1. Can you tell what's happening in the following cases? Grouping documents into different categories based on the topic and content of each document. This is an example of clustering where k-means clustering can be used to group the documents by topics using bag of words approach. So if you've gotten in there that you're looking for clustering, and hopefully you had at least one or two examples like k-means that are used for clustering different things, then give yourself a 2 thumbs up. B. Identifying handwritten digits in images correctly. This is an example of classification. The traditional approach to solving this would be to extract digit-dependent features like curvature of different digits, etc., and then use a classifier like SVM to distinguish between images. Again, if you got the fact that it's a classification example, give yourself a thumb up, and if you're able to go, hey, let's use SVM or another model for this, give yourself those 2 thumbs up on it. C. Behavior of a website indicating that the site is not working as designed. This is an example of anomaly detection. In this case, the algorithm learns what is normal and what is not normal, usually by observing the logs of the website. Give yourself a thumbs up if you got that one. And just for a bonus, can you think of another example of anomaly detection? One of the ones I use it for in my own business is detecting anomalies in stock markets. Stock markets are very fickle and they behave very erratic. So finding those erratic areas and then finding ways to track down why they're erratic. Was something released in social media? Was something released? You can see where knowing where that anomaly is can help you to figure out what the answer is to it in another area. D. Predicting salary of an individual based on his or her years of experience. This is an example of regression. This problem can be mathematically defined as a function between independent, years of experience, and dependent variables, salary of an individual. And if you guessed that this was a regression model, give yourself a thumbs up. And if you're able to remember that it is between independent and dependent variables and that terms, give yourself 2 thumbs up. Summary. So to wrap it up, we went over what is k-means. And we went through also the chart of choosing your elbow method and assigning a random centroid to the clusters, computing the distance, and then going in there and figuring out what the minimum centroids is and computing the distance and going through that loop until it gets the perfect centroid. And we looked into the elbow method to choose k based on running our clusters across a number of variables and finding the best location for that. We did a nice example of clustering cars with k-means, even though we only looked at the first 2 columns to make it simple and easy to graph. You can easily extrapolate that and look at all the different columns and see how they all fit together. And we looked at what is logistic regression. We discussed the sigmoid function, what is logistic regression, and then we went into an example of classifying tumors with logistics. I hope you enjoyed part 2 of machine learning.
So in today's session, we will discuss what RNN model is. Moving ahead, we will see why should we use RNN. After that, we will see how does RNN work, recurrent neural network. After covering these topics, we will move forward and see types of RNN, recurrent neural network, and applications of RNN. At the end, we will do a hands-off live demo of sentiment analysis using RNN. So before starting, let us have a simple question to brush up our knowledge. So question is, what are the application of RNN? Okay, NLP, time series, image captioning, and all of the above. Please answer in the comment section below and we will update the correct answer in the pinned comments, or you can pause this video, give it a thought and answer in the comment section. Before we move on to the programming part, let's discuss what RNN is and proceed further for the same. So what is RNN? Recurrent neural network. So RNN work on the principle of saving output on a particular layer and feeding this back to the input in order to predict the output of the layer. This is how can convert a feed neural network into a recurrent neural network RNN. The node in different layers of neural network are compressed to form a single layer of recurrent neural network. A, B and C are the parameters of neural network. Now that you understand what RNN is, let's look at the way why RNN. Okay, so why RNN? RNN were created because there are few issues in the feed forward neural network. Cannot handle the sequential data, considers only the current input, cannot memorize previous input. Okay, so the solution of these issues is RNN. And RNN can handle sequential data, accepting the current input data and previously received input data. So RNN can memorize previous input due to their internal memory. So moving forward, let's see how does RNN networks work. Okay, so the input layer X takes an input to the neural network and processes it and the passes it into the middle layer. The middle layer H can consist of multiple hidden layers, each with its own activation function and weight and biases. If you have a neural network where the various parameters of different hidden layers are not affected by the previous layer, that is, the neural network does not have the memory, then you can use RNN. So the RNN will standardize the different activation function and weights and biases so that each hidden layer has the same parameter. Then instead of creating multiple hidden layers, it will create one and loop over it as many times it has required. So moving forward, let's see types of RNN. So there are four types of RNN: one to one to many, and many to one. So let's see one-to-one RNN. So this type of neural network is known as the vanilla neural network. It is used for general machine learning problem which has a single input and a single output. Now see one-to-many RNN. This type of neural network has a single input and multiple outputs. An example of this is the image captioning. Now let's see many-to-one RNN. This RNN take a sequence of input and generates a single output. Sentiment analysis is a good example of this kind of neural network, where a given sentence can be classified as expressing positive or negative sentiment. And the last one is many-to-many RNN. This RNN takes a sequence of inputs and generates a sequence of output. Machine translation is the one of the example. So moving forward, let's see application of recurrent neural network. First one is image captioning. RNNs are used to caption an image by analyzing the activities present. The second one is time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And the third one is natural language processing. Text mining and sentiment analysis can be carried out using RNN for NLP, natural language processing. The fourth one is machine translation. Given an input in one language, RNNs can be used to translate the input into different language as output. So now let's move to the programming part. First, we will import some libraries, major libraries for the first we will import for the data frame. So I will write import and SPD. The second one is import numpy as np. So Pandas is a software library written for the Python programming language for data manipulation and analysis. In particular, it offers a data structure and operations for manipulating numerical tables and the time series. And this NumPy. NumPy is a library for the Python programming language, adding support to four large multi-dimensional array and matrices, along with a large collection of high-level mathematical function to operate on these arrays. Okay, so for plotting, we will import some libraries like Seaborn as SNS. This is nothing, just a short form of, we don't have to write again and again Seaborn. We can write SNS. So then another one is from word cloud port word cloud. Port matplotlib dot pyplot as plt. Okay, so Seaborn is a library that uses matplotlib underneath to plot graphs. It will be used to visualize random distribution. And the word cloud is a visual representation of words. Cloud creators are used to highlight popular words and phrases based on frequency and relevance. They provide you with quick and simple visual insights that can lead to more in-depth analysis. And this matplotlib. Matplotlib is a plotting library for the Python programming language and its numerical mathematical extension NumPy. It provides an object-oriented API for embedding plots into application using general purpose UI. Okay, like Tinker, WXPython, Qt, or GTK. So let's import some NLTK, Natural Language Toolkit. So I will write import NLTK. Okay, from NLTK dot stem import word net lematizer. Then from NLTK dot corpus import top words. Then from NLTK dot tokenize port word tokenize. So NLTK, the Natural Language Toolkit, or more commonly NLTK, is a suite of libraries and programs for symbolic and statistical natural language processing for English written and Python programming language. And this is stop words. Stop words are words that are so common they are basically ignored by typical tokenizers. And this word tokenize is a function in Python that splits a given sentence into words using the NLTK library. Okay, so let's import some scikit-learn library. So for that, I will write from sklearn dot model collection import train test splits. Okay, then from sklearn dot feature extraction dot text import FID vectorizer. Then from sklearn dot matrices matrix import confusion metric classification. Okay, so scikit-learn is a free source software machine learning library for Python programming language. It features various classification, regression, and clustering algorithms, including support vector machine learning, logistic regression, and many others like random forest classifier. And this train test split method is used to split our data into train and test set. First, we need to divide our data into features like x and y labels. And this TF-ID vectorizer converts a collection of raw documents into a matrix of TF or IDF features. The fast text or word to vectorizer word embedding Python implementation. And this confusion matrix. A confusion matrix is a table that is used to define the performance of a classification algorithm. Okay, then we'll import some libraries like from sklearn dot linear model port logistic regression. Then from learn pm port, then from learn symbol port random forest classifier. Okay, then from sklearn dot navbase port Bernoulli base. Okay, so everything is correct. We will see while running. So logistic regression estimate the probability of an event occurring, such as voted or didn't vote, based on a given dataset of the independent variable. Here SVC, logistic regression estimate, sorry, linear support vector machine, SVC is an algorithm that attempts to find a hyperplane to maximize the distance between classified samples. And this random forest classifier creates a set of decision trees from a randomly selected subset of the training set. And this Bernoulli NB, Bernoulli naive Bayes is a part of the naive Bayes family. It is based on Bernoulli distribution and accept only binary values, that is 0 or 1. So let's import some TensorFlow. So import TensorFlow dot compat dot v2 and then import TensorFlow datasets as TFDS. So TensorFlow is a free and open source library for machine learning and artificial intelligence across a range of tasks, but has a particular focus on training and inference of deep neural networks. Okay, let's import warnings. Nothing warning. The warnings. Import RE and import string, import pickle. So everything is basic. Just let's see the pickle. Pickle is a Python, is primarily used in serializing and deserializing a Python object structure. Okay, let's run it. Let's see how many errors can come. After that, we will load the data set and we will go through data visualization. Okay, word cloud cannot import name word cloud. Okay, C will be capital here. Random forest. Class. Okay, it's still loading here. Let's see. Okay, so loading is done. So now let's load the data set. So we'll write data equals to pd dot read underscore csv dataset name test one. So you can find this dataset on the description box below. Coding equals to Latin equals to polarity okay, id comma date comma query Perhaps you forgot comma where. Just to polarity. Okay. Yeah. Seems fine. Let me change this first. Is using RNN. Okay. So here I will write data equals to data dot sample equals to one data. Okay. So let me like brief tell you that what we are going to, okay. Let me brief you like what we will do in this sentiment analysis using RNN. So in this demo, like you will see text processing on Twitter dataset, and after that we will perform different machine learning algorithms on the data such as logistic regression, random forest classifier, SVC, naive Bayes to classify positive and negative tweets. After that, I will also build a RNN recurrent neural network, which is the best fit for such textual sentiment analysis. Okay, since it's a sequential data set, which is requirement for the RNN network. So let's dive into. So now we will see the data visualization, data set details target like the polarity of the tweets, zero, negative. Okay, then the date, like date of the tweet and the polarity and the user that what tweeted, then the text. Okay, so I will write print data set shape data comma shape. Okay, wait, let me first do like this. Yeah. So there are 20, or you can say 2 lakh rows and 6 number of columns. Okay, so it is a huge data. I will, you can find this data set from the description box below. So here, let's see the data. And why I use head is used for like for showing top 10 rows of the dataset. If you will use tail instead of head, it will show the last 10 rows of the dataset. Okay, here polarity 0. 0 means negative and 4 means positive. Okay, like you can consider as 0 1. This is ID, date, then query, then user, then the text. Okay, so here I will do data, polarity, dot. Okay, these are the 0 4. Okay, uniqueness. 0 means negative and the 4 means positive. Yeah, replacing the value 4 as 1 for the ease of understanding what I said to you, you can consider as 0 1. So data, polarity equals to data, polarity 4 to 1. And then data. So now you can see 0 1 0 1 0 1 1 0. Okay. So if you will write only head, it will show the top 5 rows only. Okay. So now let's use one Python function describe data dot type. So as you can see here, count is 2 lakh and the mean of the particular row is this, and the ID is this, standard deviation, minimum value, the 25%, the 50%, and the 75%, and the maximum. Okay. So let's see the number of positive versus negative tagged sentence. Okay. So here I will write positives equals to data, polarity, data dot polarity was equals to 1, then negatives, data, polarity, data dot polarity is equals to 0. Print total length of the data is dot format data dot shape now I will print the total length, the negative and the positives. Okay, so number of positive. Okay, dot format of positives. So I will copy this and paste it here, and here I will do the changes for the negatives. Okay, now let's see. So here polarity is not defined. Comma. So you, as you can see, the total length of the data is 2 lakh and the number of positive sentences is like 1 lakh 46. And number of negatives, okay, spelling is, the number of negative text sentences 99,954. Okay, so now we have a brief data. So now let's get a word count per of text. So for this, I will write count and words done length of words dot split. Okay. Then now let's plot a word count distribution for both positive and negative. So I will create a bar plot. So for that, I will write it word count to data and text dot apply word count. Okay, then I will write p positive equals to data, then count data dot polarity is equals to 1. Then so let me copy this only. Here I will write 0 and okay, then plt dot figure and figure size equals to 12 comma 6. Okay. Then plt dot 45, then plt dot x label word count, plt dot y label and frequency. Then we'll write g equals to plt dot comma n color equals to alpha equals to 0.5, positive. Okay, then let's make a legend also. Location should be right. False. Where data word count priority equals to okay, my bad. So as you can see the positive and the negatives. Okay. So these are the like word count distribution for both positive and negative. Okay. So now let's what we can do the get the common words in training data set for the training data set. So for that I will do from collections import counter all words equals to and for and test data text equals to line dot split for word and words if length of word greater than 2, all words dot append word dot lower, here I can write counter all words dot most common, then I need 20. So as you can see, these are the most common word used like in every sentence. The, and, you, for, have, that, I am, but, just, like this, out, over, all. So these are the most common words. Like it used, the is used like 64,000 times, and like this. Your is used for 8,000 times, something like that. So now we will do some data processing. Okay. Now let's do the data processing. So live and SNS dot count plot data polarity. Okay, these are the negatives and these positives. There is a slight change, I guess. That is why it's not looking so much of different. Like there's a slight 46 different, so that is why it's looking almost same. Okay. So now removing the unnecessary columns like query, user, word count, data dot drop date query and word count. X is equals to 1, comma, place equals to true. Okay. Okay, it will be true. So here I will write data word count is no, okay, my bad. So here I will write data dot drop id comma x equals to 1, true. Then data dot head the data. See, we have only the two, the polarity and the text. Okay. So now let's see the null values. So data dot data print. Okay. So there is no null values. So now converting pandas object to a string type. For that, we have to write text equals to data text type. Yeah, that as types. Yeah. So now download the stop words NLTK dot download words words equals to set stop words. It's in English. Print stop words. This these are some stop words. So moving forward, let's download NLTK dot download the NLTK dot download dot net. So the pre-processing steps taken are like lower casting, each text is converted to lowercase. Then remover of URLs will do this. matlab, we will do. Okay. Links starting with HTTP or HTTPS or www are replaced by like commas. Removing usernames, removing short words, removing stop words. Like lemmatization is the process will do of for the converting a word to its base. Okay. So for that, what I will do, will just copy the whole code for you. Will explain you one by one what I've done. Okay. So this is a course for the URL pattern for removing all the www, HTTPS and HTTP type of thing and removing them. And I have used pattern for the lower casting, removing all the URLs. Okay. Then removing all the usernames like at the red and removing punctuations and stop words. Okay, like this. So now what we have to do, data we have processed tweets, then data text dot apply lambda x process, then tweets, okay, then print text preprocessing, So it is taking time. And it will be completed. It will return here. The text pre-processing is done. Okay. As you can see, the text pre-processing is done. So now let's check data dot add done. As you can see the at the rate and this slices are gone. Okay. So now the text is pre-processed. So now what we will do, we will analyze the data. So now we are going to analyze the pre-processed data to get an understanding of it. We will plot word clouds for positive and negative tweets from our data set and see which what occurs the most. Okay. First we will create for the negative words or negative tweets, you can say. So I will add plt dot figure, then figure size 15 comma 15. Okay. Then word cloud equals to word cloud max words equals to 2000 comma width equals to 1600 comma height equals to 800 and rate dot join the data dot polarity, and I will write here polarity, okay, equals to 0. Again, then processed tweets. Okay. Then here I have to write plt dot show may show wc interpolation equals to bilinear. Okay, perhaps you forget the comma here. So 2000, then comma width dot generate. Okay, what I can do? Let me run now. Let's see. Hope this time it will work. Okay, it's still loading. As you can see, this is words. Okay, like today I am and work, don't wish, they need much. These are the most negative tweets. Okay, words from negative tweets, you can say. Right? So let's see the positive tweets. Okay. So the thing will be same. me copy, paste it here. So for this, I will do one. It will take little bit of time to come. Still loading. Like as you can see, hate, can't. Okay. Sorry. These are the negative words. Okay, still loading. So let's wait for like few seconds. Now you can see the positive words like love, okay, good, lol, and awesome, something like that. Okay, so these are some positive words. So now let's do the vectorization and splitting the data, like storing into input variable process to its to x and output variable polarity to y. Okay, we'll do that. So x equals to data processed to its values and y equals to data clarity dot values. Okay, now I will write here print x dot shape print y dot shape. Okay, cool. So now what we will do, we will convert text to word frequency vectors. Okay, TF to IDF. So this is an acronym that stands for term frequency to inverse document frequency, which are the components of the resulting scores assigned to each word. Okay, so term frequency, this summarizes how often a given word appears within a document. And inverse document frequency, this downscales word that appear a lot across documents. Okay, so now here we will convert a collection of raw documents to a matrix of TF to IDF features. Okay, then I will write vector equals to TF vectorizer and sublinear x equals to vector dot fit transform and print fitted. Okay, print number of feature comma length vector dot get their names. So number of feature words are like 170321. Okay, now we will do like now let's print the shape. Yeah. So now we will do the split to train and test. So the preprocessed data is divided into two sets of data, training data and the testing data. So dataset upon which the model would be trained on contains 80% data. And the test data is the data set upon which model would be tested again contains 20% of data. So for that I will write x train test, comma y train, comma train test by test size equals to 0.20, random state equals to 101. Okay, random state. So what I will do the, print the shape of X train, Y train, X test, Y test. Like how many columns are there, rows. Not column exactly, the rows are there. Okay. So I will paste there. So see, X train, like this is a total was like 2 lakh. Okay. So 1,60,000 in training, as we discussed earlier, like 80% in training and 20% in testing. Okay. So now let's do the model building. Okay, model evaluating functions. So now let's make a model. Okay, and first I will write and then I will explain you the whole. Okay, so here what I did it, this will tell you the accuracy of the model of training data and the testing data. Okay, then we will predict the values for test data set and the evaluation for the data set. Then we will compute and plot the confusion matrix. Okay, the both the categories negative positives. Okay, group name will be true negative and the false positive. Okay, so this is the thing. That's Let's run it. So now what we will do first for the logistic regression. So here I will write lg equals to logistic regression. Okay, then history equals to lg dot fit x train comma y train. Okay, then model evaluate lg. Now let's see. This is for the logistic regression. Okay, as you can see, the accuracy of the training data is 83%, the testing data is 77%. Okay, so this is the confidence matrix, the predictive value, like these are the categories. Now let's see for the linear SVM. For that I will write SVM equals to SVC and SVM dot fit train comma y train, then model evaluate of SVM. Okay, and after that we will do for random forest and the naive Bayes. Okay, then we will start with the RNN. So as you can see, the accuracy of training data is very pretty good, 93%, and registration is 83%, and the testing is less than regression model. Let's see for the random forest. So I will write here RF equals to random forest classifier emitters equals to 20, criterion equals to entropy, more than max depth equals to 50. Then RF dot fit X train comma y train, and model evaluate. Okay. Loading. Let's see the accuracy, how it will come. After this, we will do for the naive base, and after that, we will move on to our main model RNN, recurrent neural networks. Still loading. Yes, it will take little bit of time. So as you can see, the confusion matrix. Okay. So training data accuracy is 75%, is very less. So now let's see the last model naive base. Okay. So NB equals to Bernoulli NB NB dot fit Spain, comma y train. Okay, then model evaluate. So naive base training 86 76. So as far linear SCC has the best test training accuracy, you can say, and the best testing accuracy is 76 70 76.45 77. See logistic regression. So now let's move to the our main model RNN. So what is RNN? Recurrent neural network at are the state of the art algorithm for sequential data and are used by Apple Siri and Google Search Voice. It is the first algorithm that remembers its input due to an internal memory, which makes it perfectly suited for machine learning problems that involve sequential data. And there is one more thing, embedding layer. Embedding layer is one of the available layers in Keras. This is mainly used in natural language processing related applications such as language modeling, but it can also be used with other tasks that involve neural networks. While dealing with NLP problems, we can use pre-trained word embeddings such as GLOW. Alternatively, we can also train our own embeddings using Keras embedding layer. LSTM layer, long short term memory networks, usually called LSTMs. I have made already many videos, you can check it out, were introduced by Skymeter. These have widely been used for speech recognition, language processing, sentiment analysis, and text prediction. If you are going deep into LSTM, we should first understand the need of LSTM, which can be explained by the drawback of practical use of RNN. So let's start with RNN. Okay, so here I will importing some libraries. Okay, so after that I will write import Keras version 2.110. Okay, fine. So now let's print x test, comma y train, y test equals to train test with tweets, comma data dot polarity dot values, then test size equals to 0.2. Test size 0.2 means like 80 and 20% thing, 80 to training and the 20% to testing. Okay. Then let's the model evaluation. Okay. So I will. These are ReLU, sigmoid, all the the layers. So now this epoch, it will run till 5,000. Like count will go till 5,000. Okay. See the 5,000 and it will go to 1 to 10. So it will take time. So I will get back to you after this, completing this. Okay. Now as you can see, the epochs ran successfully. Okay. So what should I do? For I will give some space here. So now we will see the positive and negative outcome. Okay. This is something like testing. Okay. We will test. We will predict. We will give one a sentence and then we will predict it is coming right or wrong. The accuracy is giving a right or wrong. Okay. So here I will write sequence equals to tokenizer dot text to sequences. Okay. Then I will write this data science article is worst. Okay. So here I will write test equals to pad sequences, and here I will write sequence comma max length equals to max length. Then I will write here prediction equals to model we will write model, then we'll write model 12 2 dot predict, then test. Okay. If prediction is greater than 0.5 means 50%, then it should print positive. Okay. Else negative. Okay, let me run this. Okay, sequential object has no. Okay, spell mistake. See, the negative because here is the word worst. It is showing correct. Now check from the RNN model. So model equals to keras dot models dot load models. Here we will load RNN model. RNN underscore model dot sgf5. It is pre-trained model. Okay, pre-trained RNN model. So sequence equals to tokenizer dot text to sequences. Then I will write here this ML course is best. Okay, best equals to pad underscore sequences sequence underscore learn. Okay. Then prediction equals to model dot predict. Then test if prediction is greater than 0.5 and positive. 0.5 means 50%, more than 50%. Else print negative. Attribute load models. Be positive because this ML course is best. So there is no negative word. Okay. So what we will do now, we will do model saving, loading, and prediction. Okay. So for that, I will write import pickle file equals to open vectorizer pickle, then wb. Okay. And here I will write pickle dot dump vector file vector goes. Okay. So like this, I have to write for base, logistic regression, SVM, and random forest. So what I will do, right here. Okay, let's run this. Okay. So now what we have to do, we have to predict using saved model. Okay. What we will do here, we will load model first and we will predict. Okay. So first I will write the function name load models and we will load the vectorizer. So file equals to open vectorizer dot pickle rb and vectorizer equals pickle dot load file, then file dot close. Now I am loading the logistic regression model. So for that we have to write open b lg equals to pickle load file, then file dot close, then run riser lg. Okay, run it. Yeah. So now we will predict the sentiment. So for that I will write df predict riser comma text. Okay. So here we will predict the sentiment. So for that, this underscore text equals to process underscore sentiments for sentiment in text. Then text data vectorizer dot transform this underscore then sentiment to model dot predict text data. So here I will make a list of text with sentiments. So for that I will add data equals to empty array. Then for text prediction and zip text comma sentiment data dot append text comma prediction. Okay. And we will convert the list into pandas data frames. So for that I will add df equals to pd dot data frame comma columns equals to text comma sentiment. Okay. Then df equals to df dot replace comma 1 negative comma positive. And df. Okay. So at last I will write here if equals to then here we will loading the model vectorizer comma lg equals to load. Here we text to classify like what should be in the list. So like text equals to here I will like I love machine learning work is so beyond I feel so. Okay. So here df equals to predict vectorizer g comma text then print df dot head. See, I love machine learning positive, Perk is so active positive, John I feel so good negative. Okay, there is and yeah, see that's coming. Okay, so this is how you can do the sentiment analysis using RNN model. Here we have loaded RNN model, so it is showing right. So let's do them as poses. right here at boy. Negative. Okay. RNN model is working, so right.
Today we are going to explore k-nearest neighbors or KNN, which is one of the most popular algorithms in data science. Python is a powerful tool for data science, and KNN is great for classifying data by predicting the category of sample based on its closest neighbor. This algorithm is used in many fields like healthcare, finance, and agriculture, helping us make decisions based on data. The best part, it is really easy to use. You just need to pick a number for k and choose a distance function to compare data points. However, KNN has its downsides. It doesn't work well with the large data set, and it requires proper scaling of the data to get accurate result. In this video, we will show you how KNN work with real dataset. The IRIS dataset will walk you through simple Python code and demonstrate how to find the best k value to maximize your model's accuracy. So stay tuned to see KNN in action. So welcome to the demo part. So I am here using Google Colab. So you can use any of your favorite IDE like Jupyter Notebook, IntelliJ, Visual Code Studio, anything. Okay. So let me rename this file as KNN classification. Okay, cool. So let me tell you that KNN can be used for the classification, regression, predictive problems. So KNN falls in the supervised learning family of algorithms. Okay. So we will measure the distance between the k neighbors, and the first step will be we'll choose the number of k of neighbors. Then we'll take the k nearest neighbors of the new data point according to your distance metric, and the step 3 will be our among these k neighbors count the number of data points of each category. Okay, step 4 we will assign the new data points to the category where you counted the most neighbors. Okay, so let's start. First, let's import some library. Import numpy as np, and let's import pandas as pd. So everyone knows what is numpy and the pandas. Okay, so NumPy is a library for the Python programming language, adding support for large multi-dimensional arrays. Okay, along with the large collection of high-level mathematical functions. And whereas Pandas is a software library written for the Python programming language for the data manipulation and analysis, all the data frames and data structure it offers for the manipulating numerical tables. Okay, and the time series, you can say. So moving forward, we'll import our data set. So you can download the data set from the description box below. Okay, data set equals to pd.read underscore csv. The data name is iris.csv. Okay, this is how you read your data in Python. Okay, yeah, data set is loaded. So data set dot shape. Okay, yeah, so data set dot shape is used for how many numbers of rows and columns present in your data set. Okay, 150 rows and 6 columns. So let me tell you brief about data set, this iris data set. So iris data set include 3 iris species with 50 samples each, as well as some properties about each flower. So one flower species is linearly separable from the other 2, you can say, but the other 2 are not linearly separable from each other. Okay, and this shape I told you, we can get a quick idea of how many instances of rows and columns are present in our data set. So let's see our data set dot head. So head is used for you can see top 5 rows of your data set using head, and if you will use tail instead of head, you can see the last 5 rows of your data set. Cool. Okay, so columns are id, sepal length, sepal width, petal length, petal width, and the species. Cool. Then moving forward, let's describe our data sets. So these are the basic function, okay, of Python, you can say. So data set dot describe, what describes do is it will give you count of all the rows, mean value, standard deviation value, minimum value, what is it, 25%, okay, of all the values in the particular row, what is the 50%, what is the 75%, what is the maximum is 150, you can say, okay, and 25% of 150 is 38.25, this, okay, of all the columns. If it is normal character, so it won't give you any data, okay, cool, yeah. So moving forward, let's now take a look at the number of instances row belong to each classes, okay. So we will write data set dot group by species dot size, okay. Species S is capital, that's why it's showing the error, yeah. So you can see Iris setosa are 50, Iris versicolor are 50, and Virginica is 50, okay, and the data type is integer. Cool. So as we can see, dataset contains 6 columns like ID, sepal length, sepal width, and petal length, petal width, and species. The actual features are described by columns 1 to 4. The last columns labels of samples. Okay, so firstly we need to split data into two arrays like X features and Y labels. So how we will do this? By writing code like feature underscore columns equals to sepal length, sepal width, petal length, petal width. Just remember you are writing correct name. Okay. Then X equals to dataset feature underscore columns. Okay. Dot values. Then Y equals to dataset species dot values. Cool. Then let me run it. So this is how we can split the data set, okay, into two arrays, X and the Y. Okay, in X there are feature columns, these 4 columns are there, and in Y species column is there. Okay, and what is the species column? This setosa, virginica, and all this. Cool. Then now we will do label encoding. So as you can see, labels are categorical. K-inverse classifier does not accept string labels. So we need to use label encoder to transform them into numbers. Okay. Then iris setosa correspond to 0, iris versicolor correspond to 1, and iris virginica correspond to 2. Okay. 0, 1, 2. Cool. So how can we write? From sklearn dot pre-processing import label encoder. Okay, so what we'll do, label encoder transform them into numbers. Okay, so I will write L equals to label encoder, okay, my bad, label encoder, okay, then Y equals to elifate dot transform Y. Okay, so now I will run it. Yeah, correct. So splitting dataset into training set and the test set now. Okay, so now we'll split dataset into training set and test set to check later on whether or not a classifier work correctly or not. Okay, so here I will write from sklearn dot not cross. I will write here sklearn dot model selection import train test split. So what is train test split? Train test split is a model validation procedure that reveals how your model performs on your new data. Okay, and what is xtrain, xtest, ytrain, ytest in Python? Okay, let me first write it and then I will let you know. Okay, then I will write here xtrain comma xtest comma ytrain comma ytest, okay, equals to train test split, then x comma y comma test size 0.2 and the random
is this. Okay, some error came. Okay, underscore model selection. Yeah, cool. So what is X train, X test, Y train, Y test? Okay, so X train and Y train sets are used for training and fitting the model. Okay, so the X test and the Y test are the set used for testing the model, and it's predicting the right outputs label. Okay, so here you can see test size is 0.2, means 80% is for testing, 80% is for training and 20% is for testing for the new data. Cool. Yeah, so now we will see some let's do some data visualization. Okay, so here I will write import matplotlib dot pyplot as plt, then import cborn as sns, then here I will write matplotlib inline. So what is matplotlib? Matplotlib is a plotting library for the Python programming language, and it's numerical mathematics extension. Okay, so NumPy, it provides an object API for embedding plots into application using generating purpose GUI toolkits like Kinter and Python, Qt or GTK. Okay, whereas Cborn is a library for making statistical graph in Python. It builds on the top of Matplotlib and integrates closely with Pandas data structure. Okay, Cborn helps us to explore and understand the data. Okay, so I will run it. Here I will write from pandas dot plotting import parallel coordinates, then plt dot figure size should be 15 comma 10. Okay, then parallel coordinates. Okay, then dataset dot drop, I don't need id, comma axis is 1. Okay, then comma species, then plt dot title and let parallel coordinates plot. Okay, and you can give some font size equals to 20, then font weight equals to, okay, let's say bold only, bold, then plt dot x label, then features comma font size equals to 15, then plt dot y label, then I'll write here features values comma font size equals to 15. Okay, then plt dot legend, then loc equals to 1 comma I will write here frame on equals to true comma shadow equals to true comma face color equals to white, T should be capital, and comma edge color equals to okay plt dot show. Okay, some error is there, plt dot figure size, okay, spelling mistake. Okay, one more error, plt dot legend, okay, face color, okay, some spelling mistake. So yeah, let me make it view output in full screen. Yeah, so parallel coordinates is a plotting technique for plotting multivariate data. So it allows one to see clusters in the data and to estimate other stat visually. So using parallel coordinate points, are represented as the connected line segments, as you can see. Okay, and each vertical line represent one attribute, and one set of connected line segments represent one data point. Okay, and points that tend to cluster will appear closer together. Okay, so this color is iris setosa, and this is iris versicolor, and this purple one is iris virginica, as you can see in the legend. Okay, cool. So moving forward, let's create another graph, Andrew curves. Okay, so here I will write from pandas dot plotting import scatter. No, it's plotting import Andrew curves. Okay, then plt dot figure. It's AI based, so it's giving me suggestions. Okay, so sometimes suggestions are good, but not always. Yeah, let's carry on. Figure size is 15, 10. Then Andrew curves. Then I will add dataset dot drop idx is species and plt Andrew curves plot. Okay, fine. Okay, let me add, we don't need x label and all, let me add legend, plt dot legend, then same loc equals to 1, then proposition size, then I will write here size is 15, frame on equals to 2, comma shadow equals to true. So this is truly based upon you, if you want to add legend or not, or you can skip. If you want to skip, you can skip. Okay, face color equals to white, then edge color equals to black. Okay, then plt dot show. Yeah, so no error is there. So let me first view output in full screen. Okay, so Andrew curves, these are the Andrew curves. Okay, you can see the graph in the curve. So Andrew curve allow one to plot multivariate data as a large number of curves, so that are created using the attributes of samples, okay, as coefficient for Fourier series. Okay, so by coloring these curves differently for each class, it is possible to visualize data clustering. So curves belonging to samples of the same class will usually be closer together and they form large structure. Okay, as you can see here. And this is the legend why we are setting the forecolor is should be white, and yeah, and the edge color should be black. Okay, and frame on shadow should be there. You can see the shadow. Okay, like this. If you want to skip, you can skip this part, legend part. Okay, but like it's good to have, it's good practice to have this. Cool. So let's create one small pair plot. Okay, so I will write here plt dot figure, then I will write sns dot pair plot, then I will write dataset dot drop, we'll drop again id, we don't need, axis is 1, then I will write hue equals to species, size equals to 3, then markers equals to OSD. Yeah, cool. Then plt dot show. It's running. Yeah. So first let me make it to full screen. Yeah. So here pairwise is useful when you want to visualize the distribution of the variable or the relationship between the multiple variable separately within subsets of your data set. Okay. So here this blue one is setosa, versicolor, and the virginica. Okay, so these are some graph you can say, or here you can see sepal length. Okay, so green one is virginica and versicolor are almost having same sepal length. Okay, and here are the different types of graphs. Okay, if you don't want to let's say if you don't know how to read this graph, you can use this graph, or you can use this graph. Either you can use this graph. Okay, that's the power of pairwise plots, you can say. And the sepal width centimeter. Okay, setosa, no, okay, virginica and versicolor again having almost same sepal width. Okay, and here as well. Okay, this setosa is in different form. Okay, yeah, so we'll create one small pair of one small graph, then we'll move forward. Okay, I will write here plt dot. So now we are creating box plot figure. Okay, then dataset dot drop, then again id comma axis should be 1 dot box plot. Okay, then figure size I chose this. Yeah, let's run it. Yeah, again see, this is the box plot. Petal length same, petal width, sepal length, sepal width. Okay, according to width it is showing, like from this to this width we have the versicolor, and from this to this width, this length, sorry, sepal length, we have that virginica lies here, iris virginica, and from here to here iris setosa lies. Okay, the sepal length. Cool. And like you can use 3D models, you can use different types of charts. Okay, I did 4, and 4 are enough to read the data set. Okay, so now we will do some KNN classification. Okay, we will make prediction and we will see the accuracy of our data set. Okay, so now what I will do, I will write here from sklearn dot neighbors import k neighbors. Okay, right from sklearn dot neighbors import k neighbor classifier. Okay, then I will write here from sklearn dot matrix import confusion matrix comma accuracy score. Okay, then I will write from sklearn dot model selection import cross value score. Okay, so here what I did, we are fitting the classifier to the training set and the loading the libraries basically. Okay, then we'll initiate a learning model k equals to 3. Okay, so here I will write classifier, let me give one space, classifier equals to neighbors classifier and neighbors equals to 3. Okay, then fitting the model, I will write here classifier dot fit x train comma y train. Okay, then now we will predicting the test set results. Okay, so y prediction equals to classifier dot predict x test. Cool. Okay, from okay, spelling mistake. Okay, okay, yeah, I guess it's fine now. So now let's evaluate the prediction. So here I will build the confusion matrix. Okay, so here I will write cm confusion matrix equals to confusion underscore matrix y test comma y prediction. Okay, then here I will write cm. Okay, so what is confusion matrix basically? So confusion matrix is a table that shows how well a model performs by comparing its prediction to the actual values. Okay, so what it shows, a confusion matrix displays the number of correct and incorrect prediction of each class in models. Cool. Either it can give you true positive, true negative, false positive, false negative. Either it can give you 0 or 1. Okay, so yeah, moving forward, let's calculate the model accuracy. This is the main part. If the model accuracy is low, it means your analysis of classification is not good. Okay, so accuracy, it should be more than 80 at least. Accuracy equals to accuracy underscore score y test comma y prediction into 100, otherwise it will give me in points. So I will write print model Canon model accuracy is, I will write plus str, I will round it. Okay, accuracy I will add the percent. So why I wrote this accuracy to round? So I don't want after points, I need only two numbers. Okay, I don't want like 6, 7, 8, 9, 10, 11, 12 like this. Okay, I need only like 80.20 like this. Cool. Let's run it. See, our KNN model accuracy is 96.67. That's why I wrote 2 here, and the percent should be there. So 96, which is very, very, very good. Okay, so this is how you can find the accuracy. So now let's find the optimal number of neighbors in K. Okay, basically finding the best K. So we will use using cross validation parameter. Okay, tuning. So first I will create the list of K for Canon. Okay, so here I will write K underscore list equals to list range 1 comma 50 comma 2. Here I will create the list of CV score. Okay, so here I will write CV scores. Okay, I have to give the brackets. Yeah. So we'll here perform the tenfold cross validation. Okay, I will explain you what is cross validation. Don't worry. First, let me write for K and K list KNN equals to K neighbor classifier, and here I will write N neighbors equals to K. Then scores equals to cross value score KNN, and X train comma Y train. Okay, comma I will write here cross validation equals to 10 comma scoring equals to, I will write here accuracy. Okay, and then here CV underscore scores dot append to scores dot mean. Okay, so now yeah, let me run it. Okay, comma some error came. Okay, the error is the scoring parameter. Yeah, why? Because here accuracy you can see, and I did the spelling mistake. Okay, so now what is cross validation? Of course, cross validation determine the accuracy of your machine learning model by partitioning the data into two different groups. Okay, called training set and testing set. You can see test and the testing set. Okay, X and Y. So the data is randomly separated into a certain number of groups or subsets called folds. Okay, you can see the 10 folds we have wrote. Each fold contains about the same amount of. Okay, and there is one more thing, validation. So validation is a technique for assessing the accuracy of the model on data set. Okay, and this cross validation we did on new data set. Cool. So now let's find the best K. Okay, so here I will write best K equals to K list Okay, before that I will write one thing. I will write here MSC was changing to misclassification error. Okay, so equals to 1 as x for x in CV scores. Okay, at least I will write MSE dot index minimum MSE. I will use this bracket, square bracket. Okay, so then I will write print the best optimal number of neighbors is %d person best underscore k. Okay, let's run it. See, the best optimal number of neighbors. Okay, neighbors is 9. Okay, so in the k nearest neighbor KNN algorithms, okay, so k represent the number of neighbors that are considered when classifying a query point. Okay, see, if we'll classify this particular point, you will get the 6. Okay, 1 2 3 4 5 6. Okay, and let me show you. If you will classify this portion only, so you will get 1 2 3 4 5 6 points like this. Okay, so the best optimal number of neighbor is 9.
What is Python? Python is a high-level object-oriented programming language developed by Guido van Rossum in 1989 and was first released in 1991. Python is often called a batteries-included language due to its comprehensive standard library. A fun fact about Python is that the name Python was actually taken from the popular BBC comedy show of that time, Monty Python's Flying Circus. Now, let's look at the top features of Python. First, so Python has a simple structure and a clearly defined syntax. This allows the learners to pick up the language quickly, so it is easy to learn and use. Python can run on different operating systems such as Windows, Linux and Mac, making it a portable language. It enables programmers to develop the software for several competing platforms by writing a program only once. Third, Python is freely available at the official website. Since it is open source, this means that source code is also available to the public. Now, Python uses an object-oriented approach that encapsulates code within objects. Python provides a collection of libraries for various tasks such as machine learning, web development, and data analysis. And finally, in Python, you don't need to assign the data type of the variable. When you assign some value to the variable, it automatically allocates the memory to the variable at runtime. Now with that, let's move on to the uses of Python programming. So Python programming language is used to develop desktop applications and build web applications too. It is popularly used in the field of data science, machine learning, and artificial intelligence to analyze data, build predictive models, and make business decisions. Python is also widely used in game development. Now, let's see some of the popular Python frameworks and libraries. Python can be used for web development using frameworks like Django, Flask, Pyramid, and CherryPy. Now you can build graphical user interfaces using libraries and frameworks such as tkinter or just Kinter. You can also use PyGTK, PyQt, or PyJS or Python JavaScript. Now Python is also used to perform machine learning tasks using libraries such as TensorFlow, PyTorch, Scikit-learn, Matplotlib, and SciPy. You can also perform mathematical computations using NumPy and Pandas. Now let's look at the best IDEs that you can use to write programs in Python and perform specific tasks. So we have Jupyter Notebook, which is part of the Anaconda distribution that is widely used these days. Even for our demo in this video, we'll be using Jupyter Notebook. I'll show you in a while. Then we have the Visual Code Editor from Microsoft. This is also one of the preferred IDEs by learners and companies. Then we also have the popular text editor called Sublime Text Editor. Then we also have PyCharm, followed by Python IDLE and Spider as our top IDEs. Now let's look at the top companies that are using Python in our day-to-day work. So we have Google, Quora, Facebook, even Netflix, Spotify and Instagram. Now there are other top product-based, service-based and startups that also use Python programming. So what really is Python programming language? Python is an object-oriented, high-level programming language that supports built-in data structures and dynamic semantics. It supports multiple programming paradigms such as structured, object-oriented and functional programming. Python is often described as batteries included language because it has a comprehensive collection of standard libraries. Python supports different modules and packages, which allows program modularity and code reuse. Python was developed by Guido van Rossum and its implementation started in December 1989. Python 1.0 version was released in the year 1994. Python 2.0 came out in October 2000, while Python 3.0 was released in December 2008. Now that you have got an understanding of the Python programming language, let's now look at the top 10 reasons why you should learn Python. So at number 10, we have ease of use. One of the most common reasons to like Python is that it is quite easy to learn and code. It provides a simple syntax that improves readability and makes it easier to understand. So developers can create any desktop or machine-based application using this language. Python is very versatile and is instrumental in artificial intelligence and machine learning. We will talk about this later in the session. Compared to Java or C++, it has fewer lines of codes. In the example here, we are printing a hello world program in Java. As you can see, if you have to write a program in Java, you first have to declare the class name along with its scope. Next, using curly braces, you need to pass the main method along with its arguments. And then, using system.out.println method, you can print hello world. That's quite a tedious task, isn't it? The same task of printing hello world can be done using just one line of code in Python, as shown here. You can write the print function and pass whatever you want to display inside the brackets, and that will print the output. It is so simple. That is why Python is considered as a high-level language and it's open source. You can just download it from the website and start using it. At 9, we have active community. You need a community to learn new technology, and friends are your best asset when it comes to learning a programming language. Python has large community support. It has an extensive and active community to assist engineers, developers, analysts, and data scientists with expert support in case of programming errors or issues with the software. You can just go ahead and put your queries in the community forum. The community members will address your queries in real quick time. Communities like Stack Overflow also brings many Python experts together to help learners. Python Enhancement Proposals or PEP is where the proposals and the improvements are announced. Also, there are a set of recommendations or core values called the Zen of Python written by Tim Peters that represents the guiding principles for Python development. Up next at 8, we have portable and extensible. Multiple cross-language operations can be performed effectively because Python is portable and extensible in nature. For example, if the users have a Python code written on Windows and they want to execute on a Mac operating system or Linux operating system or Solaris, they can easily do it without any amendment. They can also run this code on any platform flawlessly and without any interrupt. Due to its extensibility feature, you can integrate other programming languages such as Java, .NET, C and C++ codes with Python. The components of other programming languages can be used with Python, and thus it can be used to make a cross-platform suitable application too. So it is a really good feature that Python provides. The next reason to learn Python is testing frameworks. Python supports several built-in flawless testing tools and frameworks that help in debugging and speeding up workflows. Some of the tools and frameworks supported by Python are PyTest, Selenium, and Splinter. This is the reason for which every tester tries to use Python-based tools and frameworks to test any application or code or to validate it in an easier manner. PyTest is the most recommended testing framework for functional, integrational, and unit testing. You can run Selenium test scripts using Python programming language to automate various tasks. And Splinter is an open source tool for testing web applications using Python. It lets you automate browser actions such as visiting URLs and interacting with their items. At number 6, we have libraries and packages. Another reason why Python has become so popular in the industry these days is that it has a massive collection of libraries and packages that make your task simple and easy. It has a range of libraries, packages, frameworks, and modules for data manipulation, statistical calculation, web development, machine learning, and data science. Python programmers have developed tons of free and open source libraries that you can use. You can find many of them via Python Package Index, the repository of Python software. Python provides the default package called pip. Anaconda is a third-party Python ecosystem. Other examples include NumPy, SciPy, and Django. Then we have scripting and automation. Python is not just a programming language. It can also be used for writing scripts for automating tasks and workflows without human intervention. The code can be written in the form of scripts and executed later. Further, it is interpreted by the machine and checked for errors at runtime. The machine is used to read and interpret the code. Once the developer checks the code, it can further run or be used several times without any interruption. This allows you to automate a set of certain tasks within a program, or the same code can be used with other applications as well. At number 4, we have web development. Another reason to learn Python is that it makes the web development process so much easier. It provides a wide collection of frameworks that make it easier for developers to develop web applications. Some of the examples are Django, Flask, Pyramid, TurboGears, CherryPy, etc. These frameworks are written in Python, which makes the code a lot faster and stable. The task which used to take hours in PHP can be finished in minutes using Python. Python is also used for web scraping. Django offers many elements of intricate programs such as template design, management panel, signing in, signing up, signing out, URL routing, etc. Once the user establishes the framework, all these features become ready to use. Flask is a microwave framework written in Python. Of all the components that are part of this module, they are all ready to execute in the server context. Pinterest and LinkedIn use Flask. Pyramid offers more attributes than Flask. It will assist users with URL routing and authentication support. TurboGears is a highly recommended and scalable framework that supports features such as authentication, caching, identification, management of sessions, and pluggable applications. Up next at number 3, we have machine learning. The growth of machine learning has been phenomenal in the last 5 years, and it's rapidly changing the world around us. Python is one of the most preferred programming languages for machine learning because of its simple syntax and support for several machine learning libraries. Using different libraries and functions in Python, the system can learn and train itself from past data. Once the system is trained, it can then learn to adjust itself to new inputs. Finally, it can make predictions and perform human-like tasks automatically. At number 2, we have data science. Machine learning and data science go hand in hand. Python is robust, scalable, and provides extensible visualization and graphics options. Hence, it is widely used in data science. Python has libraries such as NumPy for numerical computation of data, Pandas for operations to manipulate data on numerical tables and time series. It also provides SymPy for symbolic computation and SciPy for technical and scientific computations. It has another library called PyBrain, which is sought for Python-based reinforcement learning, artificial intelligence, and neural network library. Scikit-learn is the machine learning library for creating classification, regression, and clustering algorithms. And finally, it provides PyTorch and TensorFlow for deep learning. Finally, coming to the most important and the top reason to learn Python, which is career opportunities and salary. Python language provides a variety of job opportunities and promises a high growth graph with huge salary prospects. It is being used by most of the tech giants. Industry leaders using Python are Amazon, Google, Facebook, IBM, NASA, Netflix, and YouTube. Next, you can see the Google Trends, but I have considered 3 programming languages: Python, Java, and C++. I have compared them for the past 12 months. You can see it clearly on your screens that Python has become a front runner in terms of popularity and web search volume. It means people are interested in Python, they want to learn it and use it in their work. You can also check for the YouTube search. There also you will find that Python programming language is the most searched language on YouTube. Now on your screens, you can see the report of PYPL, which is Popularity of Programming Language Index. It is created by analyzing how often language tutorials are searched on Google. It is a leading indicator. The raw data comes from Google Trends. The bar graph depicts that Python is the most popular and widely used programming language across the globe, followed by Java, then JavaScript, and C#. The Popularity of Programming Language Index can help you decide which language to study or which one to use in a new software project. The next graph shows the popularity of Python and Java over the years, starting from 2004 till the current period, which is 2020. Worldwide, Python is the most popular language. Python grew the most in the last 5 years by 19.4%, and Java lost the most by minus 7.2%. Now let's talk about the different career opportunities and the job roles that you can get into if you learn Python language. First, you can become a Python developer, where you will be asked to write and test codes, debug programs, and integrate applications with third-party web services. Second, you can become a web developer. Here, you will be responsible for writing server-side web application logic. Python web developers usually develop back-end components, connect the application with third-party services, and support the front-end developers by integrating their work with the Python application. You can also become a data analyst if you know Python. As a data analyst, you have to gather data from multiple sources using scripts, analyze that data, develop and implement databases, and data collection systems. You can become a data scientist. As a data scientist, you need to understand the challenges in business and come up with the best solutions using modern tools and techniques to analyze, visualize, and build prediction models to make business decisions. Lastly, you can be a machine learning engineer, where you can develop intelligent machines that can learn from vast volumes of data and apply knowledge without human intervention. So there's a lot of scopes if you learn Python.
But before we move on, let's understand first what is Jupyter Notebook. So guys, as you can see all over here, that Jupyter Notebook is a popular open source tool that basically allows you to create and share documents which contains codes, equations, you can have visualizations also. Basically, it is used for data analysis, machine learning, and scientific research, which makes it a very essential tool for developers like data scientists and researchers alike. Now, before installing Jupyter Notebook, I request you that you have Python installed in your system. So the requirement should be Python 3.6 or greater. So now let us officially navigate to the Python's website. So guys, as you can see all over here, so on python.org, if I click on download Python, so we're going to see that all over here, download Python 3.125. So as I already told you that the requirement of Python should be greater than 3.6. So just you can click all over here and you can see the download had started. So guys, as you can see all over here that we have installed the Python. Now let us open the file. So you can see the given software is going to install on this directory. Okay. So just click all over here. So guys, as you can see all over here, the Python installation of 3.125 is in progress. Let's wait for some time till it gets installed. So as you can see guys all over here that we have successfully installed our Python. Now let us open our terminal and let us check whether Python is correctly installed. So we are going to type python/version. So as you can see all over here, we have successfully installed our Python. So guys, that was our prerequisite. Now there are two ways to install Jupyter Notebook. The first one can be pip. Okay, pip is a package manager, or using Anaconda distribution. So let us see with pip first. So guys, pip is a package manager which is used to install and manage software packages, libraries written in Python. So you can see all over here that the Python with version greater than 3.6 have default pip installed in them. Okay, so we can use pip command to install our Jupyter Notebook. So guys, as you can see all over here, we have come to the official documentation of jupyter.org, and it is saying that installing Jupyter Lab with pip command. So what you can do guys, you can just copy all over here. You can go right all over here and click on this. Now as you can see all over here, it has started downloading the Jupyter Lab. So guys, we are going to install our Jupyter Lab with the pip command. So this is the official documentation of Jupyter Notebook. Okay, and just all you have to do is copy this and type on your terminal. So as you can see all over here, it has started downloading the packages which is required to download the Jupyter Notebook. Let us wait for some time. Okay guys, so we have successfully completed this step. Now let us move on to our next step. So as you can see all over here, so we have installed. Okay, then what we have to do, then you can type this, you can launch the Jupyter Lab with this command on the terminal. Now let us wait. So as you can see all over here guys, we have successfully installed our Jupyter Notebook. So you can go all over here and just create a new notebook, and you can also choose your kernel and you can start working on your Jupyter Notebook. Suppose I'll show you one snippet. So 3 plus 5, let us try to run this notebook. So as you can see, it is giving us the 8 as answer. So it is following the Python syntax, and in this way we have successfully installed our Jupyter Notebook using the pip command. So now, as you can also see all over here, you can also install Jupyter Notebook with this command, pip install notebook, and then you can just open it. This is also another alternative. Similarly, you can install with Viola also. Same command and just open the Viola. Now, if you are using any other operating system like macOS or Linux, then you can install by brew install Jupyter Lab. So Homebrew will be the package manager for macOS and Linux. So I hope so you are pretty clear with how to install Jupyter Notebook with the pip command. Now, I have downloaded Anacondas from this official website. So as you can see all over here, this is the official website of Anaconda. Okay. Now just type your email and you can just download it. So similarly, as you can see, after installing, I'm going to launch my installer and let us click next. Okay. Let us click agree. Okay. And let us install this on the given directory. Let us wait for some time till the installation gets complete. So guys, as you can see all over here, we have completed our installation of Anaconda. So just click on finish and you can say we have successfully installed our Anaconda. Now let us open our Anaconda navigator. So just click on So as you can see all over here, just right click on this and our Anaconda navigator will be opened. So as you can see all over here, this is our Anaconda navigator and it is loading the packages. And for us to install the Jupyter notebook, so as you can see all over here, just click on launch. So guys, if you click on launch, it is going to open our Jupyter notebook. So as you can see all over here, it is saying launching the Jupyter notebook and it is hosted on localhost 8889. So this is our hosted Jupyter notebook. And similarly, you can create a new notebook all over here. And in this way, you can start working.
LLMs. If you ever wondered how machine learning can now understand and generate human-like text, you are in the right place. From chatbots like ChatGPT to AI assistant that power search engines, LLMs are transforming how we interact with technology. One of the most exciting advancements in this space is Google's Gemini or OpenAI ChatGPT, a cutting-edge large language model designed to push the boundaries of what AI can achieve. In this video, we will explore what LLMs are, how they work, and why models like Gemini are critical for the future of AI. Google Gemini is part of a new wave of AI models that are smarter, faster, and more efficient. It is designed to understand context better, offer more accurate responses, and integrate deeply into services like Google Search and Google Assistant, providing more human-like interactions. So we will break down the science behind LLMs, including their massive training datasets, transformer architecture, and how models like Gemini use deep learning innovation to change industries. Plus, we will compare Google Gemini to other popular LLMs such as OpenAI ChatGPT models, showing how each of these technologies is used to power chatbots, virtual assistants, and other AI-driven applications. By the end of this video, you will have a clear understanding of how large language models like Gemini work, their key features, and what they mean for their future AI. Don't forget to like, subscribe, and hit the bell icon to never miss any update from Simplilearn. So what are the large language models? Large language models like ChatGPT 4, Generative Pre-trained Transformer 4, O, and Google Gemini are sophisticated AI systems designed to comprehend and generate human-like text. These models are built using deep learning techniques and are trained on vast datasets collected from the internet. They leverage self-attention mechanism to analyze relationship between words or tokens, allowing them to capture context and produce coherent, relevant responses. LLMs have significant applications, including powering virtual assistant, chatbots, content creation, language translation, and supporting research and decision making. Their ability to generate fluent and contextually appropriate text has advanced natural language processing and improved human-computer interaction. So now let's see what are large language models used for. Large language models are utilized in scenarios with limited or no domain-specific data available for training. These scenarios include both few-shot and zero-shot training approaches, which rely on the model's strong inductive bias and its capability to derive meaningful representation from a small amount of data or even no data at all. So now let's see how are large language models trained. Large language models typically undergo pre-training on a board, all-encompassing dataset that shares statistical similarities with the dataset specific to the target task. The objective of pre-training is to enable the model to acquire high-level features that can later be applied during the fine-tuning phase for specific tasks. So there are some training processes of LLM which involve several steps. The first one is text pre-processing. The textual data is transformed into a numerical representation that the LLM model can effectively process. This conversion may be involved techniques like tokenization, encoding, and creating input sequences. The second one is random parameter initialization. The model's parameters are initialized randomly before the training process begins. The third one is input numerical data. The numerical representation of the text data is fed into the model of processing. The model's architecture, typically based on transformers, allows it to capture the contextual relationship between the words or tokens in the next. The fourth one is loss function calculation. A loss function calculation measures the discrepancy between the model's prediction and the actual next word or token in a syntax. The LLM model aims to minimize this loss during training. The fifth one is parameter optimization. The model's parameters are adjusted through optimization technique. This involves calculating gradient and updating the parameters accordingly, gradually improving the model's performance. The last one is iterative training. The training process is repeated over multiple iterations or epochs until the model's output achieve a satisfactory level of accuracy on that given task or dataset. By following this training process, large language models learn to capture linguistic patterns, understand context, and generate coherent responses, enabling them to excel at various language-related tasks. The next topic is how do large language models work?
So large language models leverage deep neural network to generate output based on patterns learned from the training data. Typically, a large language model adopts a transformer architecture which enables the model to identify relationship between words in a sentence irrespective of their position in the sequence. In contrast to RNNs that rely on recurrence to capture token relationship, transformer neural network employs self-attention as their primary mechanism. Self-attention calculates attention scores that determine the importance of each token with respect to the other token in the text sequence, facilitating the modeling of intricate relationships within the data. Next, let's see application of large language models. Large language models have a wide range of application across various domains. So here are some notable applications. The first one is natural language processing, NLP. Large language models are used to improve natural language understanding tasks such as sentiment analysis, named entity recognition, text classification, and language modeling. The second one is chatbot and virtual assistant. Large language models power conversational agents, chatbots, and virtual assistant, providing more interactive and human-like user interaction. The third one is machine translation. Large language models have been used for automatic language translation, enabling text translation between different languages with improved accuracy. The fourth one is sentiment analysis. LLMs can analyze and classify the sentiment or emotion expressed in a piece of text, which is valuable for market research, brand monitoring, and social media analysis. The fifth one is content recommendation. These models can be employed to provide personalized content recommendations, enhancing user experience and engagement on platforms such as news website or streaming services. So these applications highlight the potential impact of large language models in various domains for improving language understanding automation.
So hello guys, welcome to this demo part of this video. So here what I will do, I will go to new, then Python 3 file, then here I will give it the name called exploratory data analysis. Basically we have one dataset file of roller coaster basically. So we will be using that, and you can download that file from the description box below, from the below link, drive link. Okay, so we will be doing some small basic function using Python, and later on we will make some good charts. Okay, we will remove duplicates and all, we will do all that thing. We'll do data preparation, we'll do feature engineering. Okay, and we'll remove the duplicates, we'll check for the duplicates, we'll make charts like histogram, KD blocks, box plot, and like many more similar to that, like heat map. Will make scatter plot, group by comparison. Okay, we all do that, right? So just stick with me and you can write side along with me this code. Okay, so let's start with importing pandas first. I guess everyone know what is pandas and numpy. Fine. As np, then I will import numpy as np. Why this is np and pd? Sorry, my bad, pd is here. Because I don't want to write again and again this pandas, this numpy. So basically I can write this small version. Okay, yeah. So if you guys don't know what is panda, so panda is very popular library for working with data. Okay, its goal is to be the most powerful and flexible open source tool. Okay, so it has these that goal. So data frames are the center of pandas. And what is data frame? A data frame is structured like a table or a spreadsheet. Okay, the rows and the columns. Okay, whereas numpy is an open source Python library again that facilitates efficient numerical operation on large quantities of data. Okay, so there are many functions in numpy as well. Those we can use in the pandas data frame. Got it? So we'll import one more .pyplot .pylab, okay, as plt. Okay, there is one more library, matplotlib, for plotting the graph, and there is one more, import seaborn
as SNS. So what is Seaborn? Seaborn is again the Python data visualization library based on Matplotlib. Okay, it provides a high-level interface for drawing attractive and informative statistical graphs. Okay, then I will write here plt dot style dot use. We'll write ggplot. Got it? ggplot. Fine. So yeah, let me run it. So what is ggplot? So ggplot is this is an open source data visualization package for statistical programming. Okay, so yeah, you can say or a general scheme for data visualization which breaks up graph into semantic components such as scales and layers. Okay, matplotlib dot py. Okay, it's pylab p. Okay, yeah. So now we will import our data set df. Df means data frame. You can write any word of your choice. Then pd, again pandas dot read underscore csv, used for reading csv file. Okay, excel files. Got it? Then here I will write my this coaster dot csv. Okay, I'm not writing any path because my this data set is here itself. Coaster c coast. This is coaster.csv. Okay, if you have your data set in another location, as in like in C drive, D drive, or whatever, okay, you can give that path. Okay, let me run it. Yeah. So now we will do some data understanding. Okay, we'll see data frame shape, head and tail, data types, and describe like small function we will use. df dot shape. Right. So we have 1087 rows and 56 columns in our data set. Okay, then we will see df dot head 5. So df dot head means it will give me top 5 rows of my data set. Okay, you can see 1 2 3 4 5. Okay, 5 rows and 56 columns. Here 56 columns, but we have 1087 rows. Okay, so we have coaster name, length, speed, location, status, opening date, type, this. Okay, we will do we'll make some graphs using these columns. Okay, and there is one more df dot tail, again last 5 rows. So df dot tail gives you the last 5 rows. See 1086 1085. Okay, and if you want to see full data, it is here. Okay, 0 to 1086. Fine. Yeah. So we have one more df dot columns to check all the columns. See, coaster name, length, speed, location, status, opening date, type, and these all are my columns names. Fine. So we have one more data types. Actually, we have like many data types, but let me show you some important ones, or you can say some of the basics ones. Okay, so df dot d types. D types means data types. Coaster name is object type, length object, and inversion is float. Okay, we'll check inversion. Where's inversion? Yeah, float type. Okay, then everything is object, and year introduces int, numeric one, and latitude float. Okay, so basically we have 3 types: float, int, and object. Okay, then what we will do? Let's just quickly check this. Describe. Okay, so what is the count of this inversion? 932. Okay, it won't include any what is it, empty cells. Okay, it won't count empty cells, right? Mean of this particular table, then standard deviation, then mean, minimum value 25%, 70%, 75%, and max. It will describe you all this. Okay, and there is one more df dot info to get the info. See,
Coaster name 1087 value non-null object. Then length 953 non-null. Okay, like this. Yeah. So now moving forward, what we will do? We will do data preparation. Okay. What comes in data preparation? Like dropping irrelevant columns and rows, which we don't want. Okay. Then second thing is identifying duplicates columns. Then third is renaming columns. Then we will do some feature creations. Right. So if you want to drop a column, okay, how you can drop? So you have to write just df dot drop. First I will give here hashtag data preparation. Okay, yeah. So how you can drop a column? Okay, df dot drop. Then here I will write opening date comma axis equals to 1. Okay. Opening, okay, axis spelling is wrong. Instead of this, okay, maybe what is the opening date? Okay, O is capital here. Instead of this, you can use double equals to. Okay, axis is not defined. My bad. So what you have to do, you have to keep this here and you have to keep it here. Yeah. Again, axis is not defined. Yeah, fine. Okay. So as you can see here, first I will show you this. Question name, length, speed, location, status, and opening date is here. Fine. So if you will go here, question name, length, speed, location, status, nothing, opening date is there. Right? So this is how you can drop a table. Fine. For a while I'm making it as a comment. Maybe in future upcoming, making graph, I'll need this. Okay. So yeah. So I will write here df equals to df question name comma location then comma status. Then here I will write manufacturer. Fine. Then again comma. Then I will give here year introduced, then comma latitude. Wait, I will tell you why I'm doing this. Then longitude, latitude, longitude. Then I will give you type main. Okay. Then opening date clean. Fine. Then speed into in meter per hour. It is right. Speed into hour. Okay. Then comma. What else? Then height into foot. Inversion clean comma g-force clean dot copy. Yeah. Fine. So here I will write okay. Type in. Okay, one more mistake is here. Fine. So now what I will do, I will write here opening date clean equals to pd2 dot date time df opening date clean. Fine.
happen. So what does this pd dot to datetime do? Okay, so it converts argument to date time. Okay, so this function, you can say, converts a scalar, array like, or series or data frame, dictionary like, to a pandas date time object. Okay, so now let's rename the columns. Okay, then to for better things, df equals to df dot rename columns equals to coaster name, then poster name, comma, year introduced, then year introduced. Okay, opening date clean to opening date. Okay, then I will write as speed immutable r, then I will write caps speed underscore immutable r. Got it? Then height into foot, I will write it as capital. So why I'm writing this? Because this is a very good practice as a professional way, as a data analyst or as a business analyst, whatever you are working on machine learning projects or whatever the thing. So this is a good practice. Okay, so inversions clean, then it should be like inversions, then g-force clean to g-force. Fine, let me run it. Okay, now let's check the column. Yeah, so now you can say our column name is changed. Fine, so I will write this na dot sum. So what does this is na dot sum do? So is na function returns a boolean value of true if the value is nan and the false otherwise, and the sum function returns the sum of the true values, which equals to the number of nan values in the column. So here we have 0 nan, here same, this status 213, here 217, 5, height foot is 916. Okay, so now what we will do, we will write here df dot location df dot duplicate. I told you in starting, will duplicate it. Okay, so question name, location, status, okay, let's duplicate it now. Okay, so now what we will do, I will check duplicates for the question name. So you can write df dot go loc, then df dot duplicated and subset equals to poster name, then dot head. Okay, head of 5. Now everyone know, right, what this head does. Okay, yeah, so here you can see, so these are duplicate, okay, of the question name, right? Why? Because you can just check the type and wood and all. Fine, so now checking with an example duplicate, let's check df dot query Coaster name is equals to crystal. Now you will get beach cyclone. Okay, I took this crystal beach cyclone. Fine. Then run it. So now you can see 39 and 43 are the same. Okay, everything is same. So this one is duplicate. So now what I will do, I will write here. Just let me give some space. Yeah. df dot columns. Then I will write here df equals to df dot location. Then df dot duplicated subset equals to coaster name, then location, then opening date. Okay, dot reset index, then drop that. Okay, so now what we will do some feature understanding. Okay, so now we will do some feature understanding. Okay, so in this we will plot some feature distribution like histogram, KD, box plot. Okay, for that I will write here df year introduced. Okay, then I will write value counts. So now what I will do, let's create bar chart. Okay, ax equals to df year introduced dot value counts. Okay, then dot head 10 max I need, then dot plot kind equals to I need bar, then title is top. I like what should we give? Top 10 years coasters introduced. Okay, then I will write here ax dot set x label, then I will write here year introduced. Okay, then I will write here ax dot set y label, then count. Okay, let me run it. Okay, unexpected character after line continuation. Okay, we can remove this as well. Unexpected intended. So now let me run it. Yeah, so this is our bar plot. Okay, so this is how you can create bar plot using your data. Okay, so a bar plot is one of the most common types of graphics in this data visualization or EDA. It shows the relationship between a numerical and the categorical variable. Okay, so each entity of this categoric variable is represented as a bar. Got it? So now let's do some more. So what let's make histogram class. Okay, histogram. So for that I will write ax equals to df speed equal r, then plot kind equals to histogram, then comma I will write bins here, Okay, bins equals to 20, then title equals to coaster, speed, okay, in meter per hour, then ax dot set x level is speed meter per hour. Okay, forgot to give this. Okay, yeah. So a histogram displays numerical data by grouping data into bins of equal width. So here each bin is plotted as a bar whose height correspond to how many data points are in that bin. So bins, you can say, are also sometimes called the intervals or classes or buckets. Basically, it's the same. So here for this much is the bin. For this much is the bin. So this is like that. Okay. So now let's create KD plot. So for that, it's very simple. AX equals to DF. Then I can write as speed in meter per hour. Then plot kind equals to KD, comma, then title. I can write anything, coaster, speed, then AX dot set X level, speed, okay, meter per hour. Yeah. So KD, what does KD means? A kernel density estimate. This plot is a method of visualizing the distribution of observation in a data set, analogs to a histogram. So KD represent the data using a continuous probability density curve in one or more dimension. Okay, in one or more dimension, that curve. Fine. So now let's do some feature relationship. So in this we will make scatter plot, heat map correlation and pair plot. Okay, or we can also do some group by comparison. Fine. So now let's first make scatter plot. Okay. So df dot plot kind equals to scatter comma x equals to speed meter per hour comma y equals to height in foot. Fine. Then comma, let's give the title equals to coaster speed versus height. Fine. Then plt dot show. Okay, some error is there. Speed meter per hour. Okay. Okay, S should be capital and H should be capital. Yeah. So this is scatter plot. Speed versus height. This is speed versus height. Okay. If the I can see here height is directly proportional to speed somewhat, because if you can see the 350's speed is then 120 kilometer per hour. No, it's not like that. Okay, fine. So scatter plot identifies the possible relationship between change observed in two different sets of variables. Here the variables are height and the speed. Okay, it provides a visual and the statistical means to test the strength of relationship between two variables. Fine. Now let's make one more to give you better idea. Okay, with legend. Now I will show you with sns dot scatter plot, then x equals to speed meter per hour comma y equals to height into foot feet, whatever you can say. Then hue will be there, then year introduced. Okay, then data equals to df then AX equals to set title, then equals to speed versus height, then PLT dot show. Yeah. So now you can see. So this color, the light color. Let me zoom it. Okay. So this color we have some here which are introduced in 90s. Okay. And this color which are introduced in 1925, and these color which are introduced in 2000. Okay. So you can see like this as well. So now let's make pair plot. Okay. It's look amazing. So let me write SNS dot pair plot, then df comma variable equals to, I need year introduced, then speed meter per hour, comma, that should be capital, height, foot. Just remember the spelling. Okay, it's case sensitive. Inversions, comma g-force, okay, comma hue. I will put what okay, I will put type main, fine, then plt dot show. Okay, let me run it. Okay, some error is there. Here introduced, y will be capital, then same here. So that's why I'm saying just remember the proper spelling. Again some error, sorry, my bad. Inversions is inversions. Now let me run it. Okay, again some error is there. Okay, what inversions? Okay, let me check here while renaming. Inversions only. Okay, fine. Inversions. Let me paste it, but nothing changes. Let me check again. Okay, some error is there. Wait. So yeah, you can see it's running fine. So after this, what I will do. So what is the pair plot? So pair plot function allows the user to get, then an axis grid via which each numerical variable stored in the data is shared across the x and the y, okay, in the structured column. So this is how, see, type in wood, other and steel. This red one is wood, other are the blue one, and the purple are the steel one. Okay, the different format. Okay, now let's create the last graph, which is heat map. Okay, so let me write df correlation equals to df here introduced, comma speed meter per hour, comma height into foot, again it will be the same, comma inversions, comma g-force, then drop na, then correlation, okay, df underscores here introduced, I is capital, yeah. So this is correlation values of all the things, right? So now let's write SNS dot heat map, then tf underscore corr comma and not will be true. Okay, now let me run it. Yeah, so to create heat map in Python, so you can use this, okay, Bond library for this heat map. So this function takes a data frame, as an input and generates a heat map type of things as the output. Okay, so this is how you can perform EDA using any data set, or you can show your data or insights with a beautiful representation using graphs and all like this. Fine.
Web scraping is a powerful technique that allows you to automatically extract data from website, turning the vast amount of information available online into something you can easily analyze and use. Whether you are gathering data for research, building a dataset for machine learning project, or just curious about how websites work behind the scenes, web scraping is an essential skill to have in your toolkit. On the other hand, Python is one of the most popular programming languages for web scraping, thanks to its simplicity and the wealth of libraries available. In this video, we will explore how to use Python to scrape data from websites, and we will dive into practical examples using Python libraries like Request and Beautiful Soup to fetch and parse web content. But it's not just about the code. Web scraping comes with its own set of challenges and ethical considerations. We will talk about how to scrape responsibly, respecting the rules set by websites, and ensuring that your scraping activity don't negatively impact the sites you are collecting data from. So by the end of this video, you will have a solid understanding of how to start scraping data from the web using Python. Whether you are new to programming or looking to add web scraping to your skill set, this video will give you the knowledge and tools you need to get started. So let's jump in and see how Python can help you unlock the full potential of the web. So without any further ado, let's get started.
So here I am using this Google Colab for the web scraping. Okay, you can use your own like Jupyter Notebook, Visual Code Studio, anything. Okay, so here I will write web scraping using Python. Okay, then here first you have to install some libraries like Request, and you have to install Beautiful Soup, and you have to install that pandas, because we will create one data frame and we will save it, then we will check our data. Okay, and you can install some basic Python libraries like NumPy and all that. Okay, so here first I will import Request. Okay, then I will write from bs4 import Beautiful Soup. Okay, soup. Then I will write import pandas as bill. Fine. Then now what I will do, okay, let's see what is this request and all the thing. So Request is an HTTP client library for the Python programming language. So Request is one of the most downloaded Python libraries. Okay, it's like more like over 2000, not exactly 2000, sorry, 200 or 300 million monthly download. Okay, so what it does, it maps the HTTP protocol onto Python's object-oriented semantics. And here Beautiful Soup. So Beautiful Soup is a Python package for parsing the HTML and XML documents, including those with malformed markup. It creates a parse tree for documents that can be used to extract data from HTML, which is useful for web scraping. Let me run it. Here our second step will be define the URL and the headers. Okay, URL and the headers. So URL, okay, from where you want to extract your data. So I will write here Simplilearn, then this. Okay, let's open this PMP certification. Okay, let's cut it. Yeah, so here I will write this, and headers equals to. So these are the headers. Okay. So like in which device or you are working on, which browser you are working on. So these are for the headers. So now what I will do, I will send a GET request to the Simplilearn page. Okay, to this URL. For that, right, let me write is sending GET request. Okay, here write response equals to requests dot get, then URL comma headers equals to headers. Okay, let me run it. Okay, working fine. So now let's check if the request is successful or not. For that, if response dot status code equals to 200, then soup equals to beautiful soup. Okay, then response dot content comma HTML dot parser. Okay, here I will write codes titles. Why? Because here I'm initializing the list to store our titles or whatever the things are. Okay, basically the data. Okay, why I'm writing course here? Because this is again course page, that's why, nothing else. Okay, here I will give the empty list. So now we will find all course titles based on the actual HTML structure. What is HTML structure? You have to go to the page, right click, then inspect. Okay, according to this HTML structure means what is the class name, what is the this PMP certification is which heading, H1 heading, H2 heading, which heading it is. Okay, so let's see which heading it is. Okay, this PMP certification training H1 heading. Okay, just remember H1 heading. So here I will write for course in soup dot find for H1. Okay, then title equals to course text dot strip. Okay, then here I will write course titles dot append title. Okay, now what I will do, I will check if any data was extracted before it not. Okay, I will write if course titles. Here I will create a data frame, df equals to pd dot data frame. In this I will write course title. It will be our that column name. So I will write it course data. Okay, then course titles. Okay, then here I will write df dot to csv, then just create Simplilearn.csv. Okay, so our data will be saved in this Simplilearn.csv. Okay, CSV. Fine. Here what I will do, I will write index equals to false. Print data data is saved in CSV, Simplilearn.csv. Fine. So here I will write else print web page. Okay, write field to retrieve the web page. Okay, that's it. Let me run it. Okay, if response or status group, response object has no attribute, status code. Okay. Okay, title. It is text. Some minor spelling mistakes are there. Okay, dear dot field. Sorry, my bad. Again. Okay, sorry. D will be capital, F will be capital. Yeah, so now you can see data is saved in Simplilearn.csv. So what I will do, I will write data equals to, everyone know how to read CSV in Python. read underscore CSV. What was our file name? Simplilearn.csv. Okay, let me copy paste, run it, and then find data. Okay, PMP certification training data is fetched. Okay, here you can see H1 we gave, and that's why PMP certification training came. Let's take what's in H2. Okay, in H2 there is leading premier PMI partner, something is there. Okay, I will change here H1 to H2, then I will run it. Okay, fine. See, leading premier PMI. Okay, let me make it big. Yeah, so now you can see course data we mentioned. So if you will see, this H1 didn't come. Why? Because we have mentioned H2. That's why. So these all are the H2. Okay, so what is this? I don't know. Okay, this is a time series graph. This is Google collecting. Okay, so this is how you can literally retrieve your data from any website. Okay, just remember that some websites don't give you access to their, for their scraping, just like Amazon don't give. So you have to use at that time API, and this is not ethical also to use someone's data, okay, without asking or whatever you guys.
Welcome to the Neural Network tutorial. My name is Richard Kirschner. I'm with the Simplilearn team. What's in it for you? Well, today we're going to cover what is a neural network, what can neural networks do, how does a neural network work, types of neural networks, and then we're going to jump into a use case to classify between the photos of dogs and cats. And we'll do that on the Keras with the TensorFlow in the back, but it's a Python script, so that's always my favorite part is when we dive into the actual script. So what is a neural network? So hi guys, I heard you want to know what a neural network is. Here we have, looks like you just went shopping at a red tag sale. My robot's back. So as a matter of fact, you have been using neural network on a daily basis. In today's world, it's just amazing how much we use our new technology. We're not even aware of it. When you ask your mobile assistant to perform a search for you, like saying your Google or Siri or whoever you use, Amazon Web. Self-driving cars, so that's the newest thing coming out. They're just now trying to make those legal in different states in the US and around the world. Even in the UK, they now have self-driving cars going up and down the street. It's pretty amazing. These are all neural network driven. Computer games use it. So a lot of computer games are driven by neural networks in the back end as part of the game system and how it adjusts to the players. And it's also used in processing the map images on your phone. So every time you do a navigation someplace and it opens it up, they now use neural networks to help you find the quickest way to get there. Neural network. A neural network is a system or hardware that is designed to operate like a human brain. In today's development, this is so important to understand because we don't have anything else to compare it to. I'm sure someday in the future, the computer will redefine, or the neural network, or the AI, artificial intelligence, will redefine what these mean. But as far as we can today's world, in today's commercial development, we have to compare it to what humans do. So we want to compare how it operates to a human brain and how it solves problems like a human does. What can a neural network do? And really, we're just going to dive in deeper to what we just covered and look at other examples. So what can a neural network do? Well, let's list out the things neural networks can do for you. Translate text. Boy, we got Google Translate, and Microsoft has their own Translate. They have some really cool, they actually have an earpiece that's supposed to start translating as you talk. What a cool technology. What a cool time to live. Identify faces. Can you imagine all the uses for facial identification? In the case of our sample, or our code that we're going to look at later, we'll be identifying dogs and cats, so not quite as detailed as understanding whose face belongs to who. I'm waiting for the Google glasses to come out so I can see who's who and identify faces as I'm walking around, have a little name tag over them. Not out there yet, but boy, we are close. We can identify the faces, and they have all kinds of technologies to bring that information back to us. Recognize speech goes along with the translate text. So now as you're talking into your assistant, it can use that to do commands, turn lights on, all kinds of things you can do with recognizing speech. Read handwritten text. They're starting to translate all these old text documents that they've had in storage. Instead of doing it individually where somebody's going through each text by themselves in a room, you can picture like an old Raiders of the Lost Ark theme where he's in the back, archaeologist studying the text. Now it's fed into a computer. They take a picture. They even use neural networks to take a scroll that is so messed up that they can't undo the scroll, and they x-ray it, and then they use that x-ray to translate the text off of it without ever opening the scroll. I mean, just way cool stuff they're starting to do with all this. And of course, control robots. What would be a neural network without bringing in the robots? And we have our own favorite robot in the middle who goes to our red tag cell and goes shopping for us. So, these are just a few of the wonderful things that neural networks are being applied to. It's such an infant stage technology. What a wonderful time to jump in. And there are a lot of other things it goes into. I mean, we could spend just forever talking about all the different applications from business to whatever you could even imagine. They're now applying neural networks to help us understand. So now that we talked a little bit about all the cool things you can do with a neural network, let's dive in and say, how does a neural network work? So now we've come far enough to understand how neural network works. Let's go ahead and walk through this in a nice graphical representation. They usually describe a neural network as having different layers. And you'll see that we've identified a green layer, an orange layer, and a red layer. The green layer is the input. So you have your data coming in. It picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in a more detail in a little bit. And then finally we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law? They got me going through a red light the other day. Well, last month. That's like the horrible thing. They send you this picture of you and all your information because they pulled it up off of your license plate and your picture. I shouldn't have gone through the red light. So here we are, and we have an image of a car, and you can see the license plate on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels, and the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1. 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again the pixel shows this one up there. It's like part of the car, and so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixel of a car image fed as an input. And you're going to see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now, when we look at our setup that we're programming in Python, it has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows so it's all one array. So you'd have like row 1 and then just tack row 2 onto the end. You can almost feed the image directly into some of these neural networks. The key is, though, is that if you're using a 28 by 28 and you get a picture of this 30 by 30, shrink the 30 by 30 down to fit the 28 by 28. So you can't increase the number of input, in this case green dots. It's very important to remember when you work on neural networks. And let's name the inputs x1, x2, x3 respectively. So each one of those represents one of the pixels coming in. And the input layer passes it to the hidden layer. And you can see here we now have 2 hidden layers in this image, in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So they get these random weights that come through. If x1 lights up, then it's going to be x1 times this weight going into the hidden layer. And we sum those weights. The weights are multiplied with the input signal, and a bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layers nodes, or in this case, whatever you want to call them, network setup, the orange dots. And so you take the value of x1, you multiply it by the weight for the next hidden layer. So x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes to hidden layer 1 node 2, hidden layer 1 node 3, and so on. And the bias, a lot of times they just put the bias in as like another green dot or another orange dot, and they give the bias a value 1, and then all the weights go in from the bias into the next node. So the bias can change. We always just remember that you need to have that bias in there. There's things that can be done with it. Generally, most of the packages out there control that for you, so you don't have to worry about figuring out what the bias is. But if you ever dive deep into neural networks, you got to remember there's a bias, or the answer won't come out correctly. The weighted sum of the input is fed as an input to the activation function to decide which nodes to fire and for feature extraction. As the signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. And this becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks and you're programming. So let's look at the different activation functions before we move ahead. Here's our friendly red tag shopping robot. And so one is a sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value, and you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, but for the most part, it's going to be really close to 1 and really close to, in this case, 0 to 1. The threshold function. So if you don't want to worry about the uncertainty in the middle, you just say, oh, if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1. Really straightforward. There's no in between in the middle. And then you have the what they call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1, it's going to be 1. And if it's less than 0, it's 0. So it kind of just dead ends it on those two ends, but allows all the values in the middle. And again, this, like the sigmoid function, allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1. The next hidden layer might pick that up and say, oh, this piece of information is uncertain, or this value has a very low certainty to it. And then the hyperbolic tangent function. And you can see here it's 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme. A little bit different in here in that it goes between minus 1 and 1. So you'll see some of these that go 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's, it doesn't fire. And if it's over 0, it fires. And it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function. Very similar in use. And I believe originally used to be everything was done in the sigmoid function. That was the most commonly used. And now they just kind of use more the ReLU function. The reason is, one, it processes faster because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good as far as putting it into the next level if you want to know just how close it is to 0. How close is it not to functioning? Is it minus 0.1, minus 0.2? Usually they're float values. You get like minus 0.00138 or something. So, important information, but the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally, the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, and we have the optical character recognition, OCR, is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just a letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here, but you might have it even in the order. It might be what order the license plate's in. So you might have A, B, C, D, E, F, G, the alphabet plus the numbers, and then you might have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So it's a very large array that comes out. It's not a small amount of, we show 3 dots coming in, 8 hidden layer nodes, 2 sets of 4. We just show 1 red coming out. A lot of times this is, 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that just on the input. And so you can imagine the hidden layer is just as big. Each hidden layer is just as big, if not bigger. And then the output is going to be, there's so many digits. It's a lot. It's a huge amount of input and output. But we're only showing you just, it'd be hard to show in one picture. And so it comes up, and this is what it finally gets out on the output, is it identifies a number on the plate. And in this case, we have 08-D-03858. Error in the output is back propagated through the network, and weights are adjusted to minimize the error rate. This is calculated by a cost function. When we're training our data, this is what's used. And we'll look at that in the code when we do the data training. So we have stuff we know the answer to, and then we put the information through, and it says, yes, that was correct, or no. Because remember, we randomly set all the weights to begin with. And if it's wrong, we take that error. How far off are you? Are you off by, if it was like -1, you're just a little bit off. If it's like -300 was your output, remember when we're looking at those different options? Hyperbolic or whatever, and we're looking at the REL. The REL doesn't have a limit on top or bottom. It actually just generates a number. So if it's way off, you're going to have to adjust those weights a lot. But if it's pretty close, you might adjust the weights just a little bit. And you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the back propagation. It sends the error backward. The output is compared with the original result, and multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through the data and making small changes in the network until it gets the right answers. With every iteration, the weights at every interconnection are adjusted based on the error. We're not going to dive into that math because it is a differential equation and it gets a little complicated. But I will talk a little bit about some of the different options they have when we look at the code. So we've explored a neural network. Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radial basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data So you want to group things together, and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together. And this is a great way, if you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohonen self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Alexa or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora, and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches, like a filter. This allows a network to remember an image in parts. Convolution neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so then it can do a face recognition on each person. Applications used in signal and image processing. In this case, I use facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohonen self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here, we have quite a variety of dogs in the pictures and cats. And, just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of it identifying, instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the RELU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an RELU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. You'll see here that we did pip install TensorFlow since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the h5py in Ubuntu, but you do need the rest in there because there are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models, because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense. And you can actually just kind of guess at what these do. We're working in a 2D photograph. And if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image. So it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed, because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this has just imported these packages for us to use. And Jupyter's nice about this, that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control Plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between two things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. It's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important, because after that, Keras knows what your shape is coming in here, and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember, we talked about the different activations on here. We're using the ReLU model. Like I said, that is the most commonly used now because, one, it's fast. It doesn't have the added calculations in it. It just says, here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in-depth than we're ready to cover in this tutorial. But this is used to convert from the photo, because we have 64 by 64 by 3, and we're just converting it to 2-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our 2 hidden layers, and they are 2-dimensional because we're dealing with a 2-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, 2. And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional, instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing, because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice, is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier add a flatten setup, and then we're going to also add a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you, so we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a 2-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2, but now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array, so it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128. They got that. You can say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network. And we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have 2 more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them. And now we've set up our classifier. So we have an object classifier, and if you go back up here, you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are two layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2x2. So into a two-dimensional array from a three-dimensional array with the colors. Then we flatten it. So there's our add or flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the two-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, backpropagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have two data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter Notebooks. You can really see. We're going to come in here, we do the Keras pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out, and since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here, we do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells it it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. Their value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range, horizontal flip equals true, and this of course has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now though, we're going to just stick with some basic stuff here, and let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Now let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing, we've done a train data generator, we've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1 over 255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we are actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember we created the training set up here. And then we're going steps per epoch. So it's 8,000 steps. Epoch means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epoch 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epoch 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epoch 8,000, 25 epochs, and validation steps 2,000. And I changed these to 4,000 epochs, or 4,000 steps per epoch, 10 epochs, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epoch, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epoch, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epoch. And the epoch is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epoch, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epoch 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epoch. And that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epoch times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epoch. What's our accuracy at the end of the epoch? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Keras neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as the return for the data array. Although, you can use a standard data array from Python. And we have Keras pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the Keras processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, Keras is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as NP. Expand the dimensions, test image, axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here, we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab, friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos, and those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here, and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with. So, key takeaways. Well, we covered what is a neural network. We use all kinds of processing, the map images on your phone. We talked about things that a neural network can do, translate text, identify faces, all the way to control robots. Lots of exciting things. How does a neural network work? So we discussed that with the different layers, going from the picture to the input layer, to the hidden layers and their weights, to the final output layer. We also talked about how it does the math and computing the output as yes or no, categorically true, false. We discussed types of artificial neural networks. A lot of vocabulary there, from the feed-forward neural network, which is the most commonly used. That's the neural network we used is a feed-forward neural network that does backward propagation to train. And there's a lot of other ones out there. There's the radial biases, the Kohanen self-organizing recurrent neural network, convolution neural network, modular neural network. The big one was modular because it incorporates pieces of all the other ones so that whatever you're working on now is a huge conglomerate of multiple networks. Just all cutting edge. All of it's new. People even working on it don't even know where it's going. Again, very exciting times. And finally, we dug through my favorite part. You can see with my latte on one side, my old school pens and pencil, and all my sticky notes working away. That's not actually me, by the way. You probably guessed that. And we walked through and actually did a cat and dog photo. A simple cat and dog photo. And you could see where some of the problems are in processing large amounts of photographs and data, where that starts to become going from a single machine on my laptop with its lower amount of resources all the way to big data. How if you're processing hundreds and thousands of these photos, this now needs to be set up on an enterprise machine or even on a cluster of computers. Again, significantly past the scope of this. The neat part about it, though, is once you write this code, most of this code, they now have tools that you can almost take the same ideas, if not the actual code, and push it right onto a cluster computation. So really cool times for this. Python. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Although deep learning has been around for a while, it is just in its infant stages of development as far as exploding on the market. I mean, it is. Right now, they're building robots with it. Deep learning is used to train robots to perform human tasks. Music composition. Deep neural nets can be used to produce music by making computers learn the patterns involved in composing music. Image colorization. Neural network recognizes objects and uses information from the images to color them. Machine translation. Given a word, phrase, or a sentence in one language, neural networks automatically translate them into another language. Google Translate is one such popular machine translator you may have come across. And you'll notice in here we didn't show any examples of straight numbers, like projective cells in a business, tracking your favorite stock. You can certainly do those with machine languages, but this is the next level. Save that for your regression models, your linear regression, where you're actually processing and crunching just straight numbers. With machine learning and deep learning, we're going to a whole new level as far as what we can figure out on the computer. What's in it for you? We're going to cover what is deep learning. We're going to take a look at the biological versus artificial intelligence. What is neural network? Activation function in your neural network, and the cost function, and how do neural networks work? how do neural networks learn? So there's you'll see a switch right there. We just went from how are they working in the math in the background to exactly how are they learning. We'll be implementing the neural network. We'll do a gradient descent, deep learning platforms, and we'll give an introduction to TensorFlow and implementation in TensorFlow. That's Google's platform that they open sourced recently, and it's probably one of the most cutting edges in deep learning. And even it is still in the infant stage, which is one of the reasons they released it to open source. What is deep learning? Deep learning is a subfield of machine learning that deals with algorithms inspired by the structure and function of the brain. And you can see we have a nice picture here. We have artificial intelligence, which is kind of the big bubble that encompasses all these different things we're talking about. This is the ability of machine to imitate intelligent human behavior. And in there we have machine learning, application of AI that allows a system to automatically learn and improve from experience. And if you looked at any of our other videos, you'll know that machine learning covers a lot. So deep learning is a subcategory of that, but don't forget machine learning has all kinds of other tools that people use to do very basic descriptive and predictive and postscriptive analytics. And then you have deep learning, application of machine learning that uses complex algorithms and deep neural nets to train a model. Let's take a look at the biological neuron versus the artificial neuron. Now remember, in the human brain, and this is true for most animals, there are a lot of different neurons going on. So this is the very basic one. I mean, there's hundreds of different cells involved. So when we talk about neural networks, and this is why I say it's in a very infant stage, they're really basing it on just the most basic thing that we're able to figure out going on in the neural networks. And you can see right here we have dendrites fetch information from an adjacent neurons and pass them on as inputs. So you have your data coming in and your data going out. Any computer model should be looking at that. What's coming in, what's going out. The data is fed as an input to the neuron. So when we look at the artificial neuron, you can see we have our inputs. They come in, each one is specially weighted into the neuron, and then the neuron has an output. The cell nucleus processes the information received from the dendrites, and the neuron processes the information provided as inputs. Axons are the cables over which the information is transmitted, and the information is transferred over weighted channels. So you can look at that, I mentioned weights briefly, but you alter the data coming in. So those weights are what causes different information coming in to be weighted differently and processed differently. And the synapses receive the information from the axons and transmit it to the adjacent neurons. That's in your biological model. And then when we look at the artificial neuron, the output is a final value predicted by the artificial neuron. So as we dig deeper into looking at the theory behind the neural network, and we kind of flip back and forth between these because there's two huge aspects of it. One is from the outside, what are you seeing, and what's going on from the inside, so you can find to do what you need to do and give the best results you can. And we start off with what do we feed? We feed an unlabeled image to a machine which identifies it without any human intervention. And so you can see here we have a circle that comes in at 784 pixels, and it comes in by 28 by 28. And you can see how it colors in the circle on there. And we put a triangle in. The triangle in also comes in as 28 by 28, and it has 784 pixels. So you'll see between these two, both of them are 784 pixels. This machine is intelligent enough to differentiate between the various shapes. So that's what we want to use our neural network to do, is to say, hey, this is a circle, this is a triangle. And that's more of a categorical. You can also do a regression model where you're actually putting out a float value or a numerical value. We'll be looking at the true-false or the categorical model mostly, because that's where you usually start at. There is no real difference when you, as far as the way the internal functioning goes, when you start flipping between them, other than, well, we'll talk about that in just a minute. So you can actually go between the two quite easily. And the neural network provides this capability. So we're going to use this capability to look between those two. One of the things I want you to note in here is that we're looking at 784 pixels. We're looking at 784 inputs. That's very different than stock with a high-low, or last year's cells based on date, where we're looking at just a couple of numbers, and they're very clear, they're numbers, they're very clear what they are, which is something you'd put into a machine learning linear regression model. This is a step up from that in that we're looking at complex patterns, and how do you figure those complex patterns out? So a neural network is a system modeled on the human brain. And we looked at that, comparing the two. Let's go ahead and look deeper into the neural network itself. We have our inputs coming in. So the inputs are fed to a neuron that processes the data and gives us an output. Input and output. This is the most basic structure of a neural network known as a perceptron. So if you see the term perceptron, that's what we're talking about. We're talking about this single node that has inputs and an output. However, neural networks are usually much more complex. Let's start with visualizing a neural network as a black box. And I always always loved that symbol. It's a black box. It's kind of magical. We have our inputs coming in and we want certain outputs. The box takes inputs, processes them, and gives an output. Let's have a look at what happens within this box. And you can see me there in my secret agent getup. I got my hidden hood and everything. I guess I'm part of the Black Skull or something like that group. So let's take a look at what happens within this magic box. And remember, we're skipping back and forth between the theory of what's going on in the box, which you have to know how to fine-tune and how to build, versus looking at it from the outside. We're programming this box, and we have an input and an output to the box as a whole. Within the box exists a network that is a core of deep learning. And you can see here we're showing one layer, and we have our grid coming in. The network consists of layers of neurons. Each neuron is associated with a number called the bias. And you can think of the bias, if you overly simplify this, and we're doing a linear regression model, this is your y-intercept in your Euclidean geometry. You have to have something that offsets it, and so you always have a bias in these cells. Neurons of each layer transmit information to neurons of the next layer over channels, and so you can see each of our layers going through from left to right. These channels are associated with numbers called weights. These weights, along with the biases, determine the information that is passed over from the neuron to neuron. So just like the bias is your y-intercept in Euclidean geometry, you could look at the one weight. Remember, this is very complicated, so we're not looking at just one weight. You could look at the weight as your slope of the line. Or if you're doing x equals my plus c, it would be the m value. Neurons of each layer transmit information to neurons of the next layer. And you can see here as they light up going across into the final layer, and then to the output. And in this case, the output is going to be either a square in this one, or it might light up the other one, which is a circle. The output layer emits a predicted output. So in this case, we're looking at a classification, true, false. Is it a circle? Is it a triangle? Is it a square? Let's now go deeper what happens within the neuron. So we're going to dig deeper and start getting a little bit closer to some of the math. Don't worry, you don't have to be a calculus expert or know your differential equations. Even though this is one giant differential equation, you don't need to understand those to understand what's going on. Within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. This is simply addition. We're going to sum up the weight times the output from the previous channel, and plus the bias. Sum of the weighted products is computed. This is called the weighted sum. Bias, unique to the neuron, is added to the weighted sum. The final sum is then subjected to the particular function. And we'll discuss that particular function. That part is really important because those functions have a huge impact on how well your model performs under different conditions. The final sum is then subjected to a particular function. This is the activation function. So if you ever hear the term activation function, that's what we're talking about. What activates this cell and what doesn't. As we dig deeper into activation function, an activation function takes the weighted sum of the input as its input, adds a bias, and provides an output. And a lot of times you'll actually see one formula for the sum of the weighted sum and the bias. You'll just see that as a single line of everything added together. And here we've broken it apart because it makes it clear that this bias is not computed the same as the weighted sums. Here are the most popular types of activation function. And I always find these interesting because at one point I was sitting at a table with a gentleman who was finishing his PhD. He was in his last year, and he said he went through all this stuff and he ended up just trying the 4 different activation functions on this particular problem he was working on. So knowing the math behind it doesn't necessarily mean you're going to know it right away. So even somebody who might have a PhD and be doing the calculations on this comes back out of it and ends up just trying the different activation functions to see what's going to make a difference. And a lot of times that's a final step. That's the kind of thing where you built your whole model, you've come back and you're like, wait a minute, can I do a better deal with the sigmoid function or the threshold or the rectifier? Knowing what they're doing is important so you can explain it to somebody else. And again, you probably do this on a small set of data. If you're working with big data, you don't want to take down the full server farm just to test out your 3 different series. You take a small portion of that data, test it, and then you put it through to the big data. So let's take a look at this. We have the sigmoid function, and it's used for models where we have to predict the probability as an output. It exists between 0 and 1. And you'll see that's true of all of our activation functions we're working with. Either the cell's on or off. It's true or false. And there might be a little variation in there, which as an output could be used to compute uncertainty in your solution. So if you're getting a 0.7 with this activation function, it might be, well, I'm not sure if that's really a square, or I'm not sure that's really a triangle. And that might be a flag for it to be looked at by a human observer, at least in today's models where we're at right now. And you can see here where we have the formula is simply equals 1 over 1 plus e to the minus x, where x is your value coming in, and it's going to give you a result that looks very similar to the graph on there, which is somewhere between 0 and 1, and right in the middle you can see that there's a huge you can go through all the different values and uncertainties involved. So the sigmoid function is probably the default on most of them. The next one is the threshold function. It is a threshold-based activation function. If x value is greater than a certain value, the function is activated and fired, else not. Pretty straightforward. Yes, no, true, false. I don't want to test for improbabilities. I just want a straight answer. I don't want to know if there's a partial value on there. It either is true or it's false. And the rectifier function, it is the most widely used activation function. I would debate that. Rectifier is a pretty common one, although I see the sigmoid function used to be the basic one, but it's up there. The rectifier function is very commonly used. It gives the output of x if x is positive and 0 otherwise. And you can see here, again, just like it's either kind of get a value going up there. So max of x of 0. So it's like the threshold function. Yes, no, true, false. It's either 0 or it's some kind of progressive value. And then we have the rectifier function. I would argue with this, because the sigmoid function used to be the most common one, but with the rectifier function, it now says it is the most commonly used or widely used activation function and gives an output of x if x is positive and 0 otherwise. This is kind of nice because it now says absolutely not, or it gives you a value of probability. Now when I say a value of probability, be very careful there. I'm not saying that it's going to tell you this is 75% chance of being a circle. I'm going to tell you that it says, hey, if this says 0.1, it probably needs to be looked at, or 0.2 or 0.3. It's going to depend on your data as to what that value means. In general, that just means it's flagging it that if it's not a 1, then chances are it needs to be looked at by a person and reevaluated. And there's a hyperbolic tangent function. This function is similar to sigmoid function, is bound to a range of -1 to 1. So you can see there's our 1 minus e to the minus 2x and 1 plus over 1 plus e to the minus 2x. Again, it's very similar to the sigmoid function. The bonus of the hyperbolic function is you have that variable coming through the middle. So again, you can look at it and you have a little bit more weight as far as you can process that down the line. That's a little bit more advanced than what we're looking at right now, and a lot of times it's not even necessary in a lot of our different uses for these activation functions. Now, we looked at activation functions, and I kind of said those are a little bit like a black box, because even if you know all the math, a lot of times you end up just playing with them to find out what works, and it also depends on what model you're working with, whether you need a flat yes, no, true, false, or you need to have something in the middle that says, hey, this isn't quite a 1, you might need to process this with the human intervention. And you can look at that. One example would be self-driving cars. You don't want a car to be yes, no, I'm going to go through the light. You want it to be like, okay, if it's almost yes, maybe we stop and have human intervention so we don't get an accident. Cost function is something you can really see and measure and is very important. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. So we have our group of data that's a square, circle, and since we're looking at geometrical shapes, we've had somebody already labeled that data. They've already said this is a triangle, this is a square. And so if this is coming up and it's giving us and it's saying a square is a triangle and it's saying a triangle is a circle, the output is wrong. And so that output can then be measured versus the actual output, and that's the cost. You might also hear this as error, because that's the error value being returned. How far off is it? And what we're looking for is the least cost, or the least error value, and it's obtained by making adjustments to the weights and biases iteratively throughout the training process. And this is called back propagation, and we're going to look in that a little deeper as we look into an example. It's really hard to see when you're just looking at arrows without actual numbers and where that flow is coming from. But you can look at this as here's our inputs. They put out a prediction. The prediction comes out and says, hey, we've already labeled this data because we're in training mode, and the training data is off. This is the cost. Can we send that error or that cost back and adjust those weights? And we do it in very small increments across large amounts of data so that those weights minimize that cost or that error. But what happens within these neurons? So let's look at a little example of this. Kind of helps if you have some kind of visual. Let's build a neural network that predict bike prices based on a few of its features. And we'll see here we have our CC, our mileage, and our ABS, and these are our 3 input layers. And then we have the bike price and the output layer. Now, it doesn't do us very good to just pump it in from the beginning and pump it out. And to be honest, I would use a machine learning linear regression model on this, since these are just straight numbers. But because we want a simple example, we're going to put this through and show you as a neural network what that looks like. And we got to put a hidden layer in there. The hidden layer helps in improving the output accuracy. And you could look at this as a bunch of ORs. So it might say, hey, when we compare these 3 values on the first hidden layer neuron, we're looking at one set of features, and then we might weight them in the second one. So these are a bunch of different ORs, kind of how the math comes out and behind the scenes. And then they go out, of course, to the bike price or the output layer. And each of the connections have a weight assigned with it. And you'll see here we have mileage CC with the weight 1 and weight 2 going into our first neuron. And you'd also have your ABS going in there. And so x1 times weight 1 plus x2 times weight 2 plus the bias of 1. And step 2 is our activation. The activation function coming in there. When does this fire? And the neuron takes a subset of the inputs and processes it. And then we go through and we do that with the second hidden layer neuron and the third one and so on. So you process each layer in order going forward. Now, when I told you this is in its infant stage, they now have neurons that fire into the same layer or back a layer so that you now have a time series. And there's all kinds of wild things that they're experimenting with on these layers. This basic setup has been around since the mid-90s. It's only now because of our technology that it's open to almost everybody to play with it. And that's why I say this is in an infant stage in development. Is this basic math is here, but what we can do with it is amazing, and what they're actually doing with all these different things is amazing. And so we're just at the beginning of how to use all these different tools in our deep learning and our neural networks. And so once we have our hidden layer computed, the information reaching the neurons in the hidden layer is subjected to the respective activation function. And so each one of these fires an activation output, and then those are each weighted to the final output layer. So the processed information is now sent to the output layer, once again, over weighted channels. And you could look at this as each one of these is, I always look at this as like a group of people. They're all looking at the bulletin board, and the first person says, this is what I project sells for the company, and the second person, and the third, and so on. And then their perspectives are weighted based on their expertise. So your accountant might have a very high weight, where the maybe your janitor has a very low weight because their expertise is not in accounting. And then that goes into the output layer. And once in the output layer, it goes, the output, which is the predicted value, is compared against the original value. So now we have our output layer, and since we have like already a list of bikes with the different setups and what their value is, we can now generate an error from this. The cost function determines the error in prediction and reports it back to the neural network. So this is the cost. This is how far off it is. This is your error coming back. And as you can see, this is back propagation going on. So now our error is going in reverse because we know we're not completely correct on this particular channel. The weights are adjusted in order to reduce the error. So each time we go back, we are changing those weights to reduce that error, and we change them in small increments. You don't want to fit one input. Remember, you might have a data pool with a terabyte of data. You don't want to solve for the first set of data that comes in and that be the main solution, because everything else will be off. This is going to confuse you. That's also called a bias. So we have the bias in the cell where we're adding a value, the kind of like the y-intercept, and we have a bias of the whole neural network, which means that it's weighted towards one set of answers. So we want to make small changes in these weights so we don't create a bias. And the weights are adjusted in order to reduce the error, or the cost. The network is now trained using the new weights. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. So let's go ahead and plug in values and see how our neural network works. So here we come in here, and initially our channels are assigned with random weights. This is important because is if you assign them all with the same weight, you might be able to reproduce it, but it turns out that if I put all my weights as 1 or all my weights as 0, it takes longer to train. Where if you have random weights, they already have like a little bit of adjustment and ORs built in, and that will give us a better answer and train faster. Our first neuron takes a value of mileage and CC as inputs. So here comes our computation, whatever those inputs are, and we do that again with the second neuron with those values coming in. You can see here we have weight 3 and so on, and then our third neuron coming down, and of course our fourth neuron. So we're adding all these different values coming in here in our hidden layer. The process value from each neuron is sent to the output layer over weighted channels. So again, here's our weights coming in, and we have N1, N2, N3, and N4. Once again, the values are subjected to the activation function, and a single value is emitted as the output. On comparing the predicted value to the actual value, we clearly see that our network requires training. So here we have it that our bike price we put out, we thought it was worth $2,000 on our random weights, and the bike actually was $4,000 on there. I'm guessing that's not US dollars, because that'd be a very expensive bike, but maybe it is. There's some $2,000, $4,000 bikes out there. The cost function is calculated and backpropagation takes place. And this is pretty simple. You can look at that as our we're subtracting one value from the other, we square it, and then we take half of that. And that is propagated back up, and each layer generates its own errors. Let's go back one, because you have your predicted y and your actual y. That goes back to the first layer. And then based on the value of the cost function, certain weights are changed. So when we look at the next layer, that error is not the original 4,000 minus 2,000 squared divided by 2. This error is based on the error of each cell generated. How far off is that cell as far as its weights? We're not going to show you. It's actually a very complicated differential equation, and you can probably write it out if you wanted to. You just write out each formula. That goes into the next level, and you add them all together, and you can write it out all the way through. Computers make it so you don't have to. And our neural network is considered trained when the value for the cost function is minimum. So when we get our error way down as low as we can, that's when our neural network is trained. And just recently they've come up with all kinds of different means for measuring that particular value. A little bit beyond the scope of today's neural network, but you can actually see it. How far do you do this until the neural network doesn't need to be trained anymore, and you can overtrain a neural network. Now the tools that we're looking at automatically let you know when to stop, which is really nice. And that is just, like I said, we're at the beginning stages in neural networks, and it's just really cool what they can do now, and how much of it's automated, and how much of it is experimental right now. Let's take a look at gradient descent. But what approach do we take to minimize the cost function? So here we have a nice error thing coming in. This is our cost or our error. Let's start with plotting the cost function against the predicted value. And so you can see they fed in multiple y's, and these are the errors coming in and the cost of each of these inputs and changes going on. Note, we start at a random point on the curve. So usually you put in, you pick up your data and you randomly pick where to start in your data. A lot of times you just run it from the beginning because you're going through so much data, it's not that big of a deal, but you start with one point going in. So your forward propagation goes through, you're going to go ahead and find your cost or your error. It points that on the curve, and you can see how we're plotting it right here. Since the gradient at this point is positive, we may move right. So we're going to move a little bit to the right on here. And this time the gradient is negative, we move a little bit to the left. Eventually we try out the point where the gradient is 0. This is the least value of cost function. You have to be a little careful with this because this particular, they make it look nice and simple in this graph. Sometimes these curves look like stair steps, and so there is global minimums and then there is local. There might be a local point where the gradient is 0, but it's not the global one. So it might be way off to the left where it just happens to step down a little bit and you think you're in the right gradient. And with that we have all the right weights, and we can say our network is trained. So here we have just some major, these are some of the big names out there right now in development for deep learning platforms. TensorFlow, which we'll actually do an example in a minute. Deep Learning for J, which is in the Java platform. So if you're a Java programmer. By the way, as TensorFlow is accessed, most people are using Python to access it, but it is a system that's kind of separate from a lot of the programming languages, which makes it a lot more flexible as far as use. Deep Learning for J is Java based. And then Keras is just exploding right now, and this is interesting. and Keras is working with TensorFlow. It actually can sit on top of TensorFlow, and it can also do its own thing. So if you're studying deep learning, you're getting into it, you'll want to know the basics of TensorFlow, but you also are going to want to know the upper level of Keras sitting on top of TensorFlow. We're just looking at TensorFlow today, though, in our example. And there's also Torch on there. There's a bunch more that we didn't list on here. Even sklearn, or the Sci package in Python, has a neural network you can program, a very basic one. And it is the same basic one that you could do in TensorFlow if you stripped everything out of it, and then TensorFlow has a lot of tools they've added in, and so has Keras. But we're going to be looking specifically at TensorFlow in our example. And TensorFlow is an open source tool used to define and run computations on what they call tensors. Very common language now. So more and more we see the term tensor as being a standard in the deep learning language. And this was originally developed by Google. So let's take a little bit big in there. What are tensors? Tensors are just another name for arrays. So a tensor of dimension 5. You can see here we have A, B, K, M, Q, whatever. So it's an array coming in. And the tensor of dimension 5, 4, more like a picture. Very common to see that in a picture. You can also see a tensor even more detailed in a picture as we go to the next one, tensor of dimension 3, 3, 3. This is 3D space. You might have a picture that also has colors. That might be the third dimension. You might have 4 dimensions because you have both your grid and your different color channels and your z-plot. You can see where you can now process a very high level set of data coming in, whether as an image or features. They could be features that have nothing to do with images. So there's a lot of stuff you can do now with the tensors coming in. Thus, this is where the term TensorFlow comes from. So we have right now that TensorFlow is the most popular library in deep learning. And I did mention Keras now works with TensorFlow. So there's a lot of stuff you can do between the two. It's an open source software library developed by Google. So they hit a roadblock and they realized, hey, this is an infant stage technology. You know, we thought it was going to be the next greatest thing and we were going to have a hold on it, but it's really infant as far as how it's applied and what we can do with it. Let's open source it so everybody can work on it. Let's take it to the next level. And that's really what open source does to a lot of these packages when they release them. And you can run on either a CPU or a GPU. So when we look at the details, if you have your graphic processing units, what's nice about those is they run a lot faster. The downside is you have to play with them a little bit to get them up and running, and it's a hardware upgrade. When we run it, I'll be running it in the CPU mode. I have played with it in my GPU on my personal computer. You know, it does increase the processing, but I did run into some version problems with my Python and stuff like that. And when I did finally work it out, I went back to the CPU because it didn't increase my speed enough for what I was working on. But in a larger group, you might be able to put that on. If you're working with a larger stack of computers, you might want to run it in the GPU. You can create a data flow graphs that have nodes and edges. So there's our edges coming in. We didn't talk about edges, but that's a very up and coming way of looking at your analytical data is how do different nodes connect? What do those edges look like in between them? And it's used for machine learning applications such as neural networks. It is mostly a neural network, but they have all kinds of tools which sit on top of our basic neural network. They have new stuff evolving into the TensorFlow library. So it's very much just exploding. Great time to jump into TensorFlow because there's all kinds of cool things they're doing with it and all kinds of cool applications you can now use TensorFlow for. So let's take a look at implementation in TensorFlow. And we're going to build a neural network to identify handwritten digits using the MNIST database, or the MNIST database. And that stands for Modified National Institute of Standards and Technology Database. It is a collection of 70,000 handwritten digits, and the digit labels identify each of the digits from 0 to 9. This is a cool example because it's simple enough that you could actually run this through some basic machine learning categorizing algorithms and train them. And you'll get about the same answer because, again, it's simple grid. The digits on the grid don't have a huge amount of variation like you would, say, an automated driving car looking at the environment. So you can still do this with a lot of your different linear models and stuff like that. You can solve this and you'll get about the same answer. When I ran a comparison between TensorFlow and between some basic regression models or category models in machine learning, they came up pretty even as far as their output. So this is kind of where we start to see the complexity of something coming in this case a tensor, or a grid of information, where the deep learning model does as good as the regular models. And when you get past this kind of complexity and features, suddenly the neural networks come up with better answers, better solutions, and a better build. And that's why there's such a move into neural networks, is we live in a complicated world, and it's just really cool what we can do with this. So the handwritten digits from the NIST database, they come in, the data set is used to train the machine, a new image of a digit is fed, and the digit is identified. And if you've looked at any of our other machine learning tools where we're doing training, where we train our model to fit and then you test it out, this will look pretty familiar. And there is some tools out there for, say, untrained categorizing, where it's just looking for features that fit together. So there are tools that don't need that training. But this is where, when we talk about neural networks, we do need to train them, and this is what we're looking at. So for this, I'm going to use the Anaconda Navigator just because it's a very nice visual tool. You might be in PyCharm or one of your other IDEs for editing Python, because we are looking at Python TensorFlow. And under Anaconda, we have the notebook, which is something we use pretty regularly, and they have the Jupyter Lab. The Jupyter Lab is the Jupyter Notebook, but with tabs and a few new features. So we'll be using the Jupyter Lab today. And under the environment, you'll want to go ahead and if you haven't yet, you'll see that I have a number of different setups in here. Right now I have the Python version 3.6 and the TensorFlow. In this case I have TensorFlow 1.12. If we scroll down you can see that. Here we go, TensorFlow, and it's version 1.12. And in here, if you haven't yet, you'll need to install those. Go in and just open our terminal. And if you've never used the Anaconda, or if you're in your other thing, you might have something simple like pip. Conda is what I use for my install, and you can simply do conda install TensorFlow. And that should bring in the most current version. Now, when I installed this a few months ago, Python version, I'm not going to run this because I already have it installed on here, Python version 3.7, the newest one out, still had a couple glitches with the TensorFlow. I believe they've fixed it as of writing of this, but I'm going to stick with 3.6 just so I don't get any surprises on there. So this is Python version 3.6 with TensorFlow 1.12 on here. And if you haven't installed it yet, you also want to install NumPy for this example. That's numbers Python, or NUMPY. You can just simply run an install on there. Keep in mind, if you're in Anaconda and you've created one of these environments specific to this, keep with Conda. If you're going to use Conda. If you're going to use pip, keep with pip. Don't install one package with pip and one under Conda, because that's how they track those version numbers and how they fit together, and you can end up with a problem. Pip doesn't see Conda and vice versa. So just keep that in mind when you're running your installs. We'll go ahead and open up Jupyter Lab, and we're going to launch that. So here's my Jupyter Lab. One of the really cool features of Jupyter Lab is you have tabs now, so you can open up multiple notebooks. And this is nice because I have my notes I'm working on and then our actual window we're looking in. And we'll go ahead and zoom in a little bit here. There we go. So you have a nice, hopefully easy to see fonts. And then we'll go ahead and do a simple, or get our imports out of the way. And so we're going to import our TensorFlow as TF. That's pretty much a standard for TensorFlow. NumPy, our numbers Python, as PY. And we'll import our matplot library as PLT. Again, these are very common. So if you see TF or PY or PLT, this is a standard that most people use. Do you have to? No. You could just do import NumPy instead of doing as PY. And then from TensorFlow.examples.tutorials, this is always nice because they actually include data set we're going to play with. So we're going to import input data. So those are data coming in. That's all we're doing, is telling it this is where it's coming from. And if we're going to tell where it's coming from, we need to go ahead and create a variable with that information in it. And we'll just call this MNIST or minced. You know, I don't really know how they pronounce that. I should probably look that up. It's a very common data set to use. And there's our input data, and we're going to read data sets. And this is, if you look at this, we imported input data from our TensorFlow. And so this is a TensorFlow read statement for their tutorials. So this isn't like some special Python setup. This is just their setup. It makes it easy to pull it in. So once we get into their data sets, we need to go ahead and tell it what kind of data set. And again, this is what we brought in, but it's going to be the NINST data. And this part is very important. One hot equals true. This means that instead of importing a value from 0 to 9, we evaluate the data set, it's going to bring it in as one hot. Whenever you see one hot encoder, we're flattening that out, and we have true false for 0, true false for 1, true false for 2. So our output, if you remember from our output from the slide we did earlier, in this case I grabbed the one for bike price, doesn't really matter which one we use. This has one output, so we have our bike price. On this, we're going to have, instead of one output, we're going to have 10 outputs representing each of the digits in there. And this code really isn't going to show us anything. It's good to see what we're actually looking at. So let's go ahead and do a figure. AX equals, go into our plot library, subplots, 10, 10. And that is, if you remember, we talked about tensor being data coming in. This is a 10 by 10 grid, or 100 pixels on there. And if we're going to display it, let's go do K0 for I in range 10. Just a simple loop through on the data. Let's do, what is it, for J in range 10. So I actually misquoted that. 10 by 10 is not the actual size of the pixels. The actual pixels are going to be, when we look at the shapes, and we'll get into that in just a second here. We'll take a quick look at shape on there. It turns out they're, they are, I believe, 28 by 28. So let's take a look at that. And we're just going to plot these. What are we looking at? What are we working with? As a data scientist, you should always be looking back at your data and seeing what it looks like and get that human perspective, because you just never know. You know, the computer might put something out that makes no sense, and at that point you want to go back and reevaluate what you did. So we're going to go ahead and plot. We're going to plot 10 of the digits by 10 of the digits, and here's our AX. We'll create the IJ on our subplots, and we're going to do an image show. We're going to look at the training image for images of K. And then we want to reshape this. We're going to reshape this, and we're going to reshape this 28 by 28. That's how I knew I had it wrong, is because I looked down my notes and it's like, oh no, that says 28, it's not 10 by 10. And I should know that already because I've done enough messing with this data set that I should have remembered. But it's 28 by 28, and the aspect we're going to do is auto. And this is all, if you look at this, here's our variable NIST. The NIST is coming from data set. So this is all part of the TF TensorFlow learning or examples tutorial in there. And then we'll go ahead and do K plus equals 1. So we just keep paging through our different images. And let's see what that looks like. Let's go ahead and do a plot show. And we'll go ahead and run this so we can take a look and see what we have here. And so we have a nice plot here, and you can just see that we have some random numbers showing up in each one of these little subplots. If you're wanting a copy of this code, put a note down in the YouTube video and let us know, or come visit us at www.simplilearn.com, and we'll send you out a copy of what we're working on. You can get a copy of that for your own setup. So now we've taken a look, and we can just see we have, here's our pictures that are coming on. We've plotted them, so we have an idea of what we're looking at. Let's go ahead and let's look at the shape of the features. So when we have this, we have our NIST train images, and we'll do the shape on there. Let's take a look and just see what we're looking at. As far as our count and everything. And so you can see here we have 55,000. That's basically how many images we have, and this by 784. And in this data set, there's also our labels. So let's take a look at that. We have our NIST train labels shape. Let's take a look and see what that looks like. And there we have 10, because there's 10 digits. So we brought in, that's our output we're looking at. And so we have, there we go, 55,000. They match. They should match, because you should have equal numbers in both of those. You know, here's our data in, and here's our answer. If you remember, this is a bunch of zeros, and with one, each one will be 0001, would be what, letter 4 or something like that. So let's take a look at what our one hot encoding did for the first observation. And this is, when we're exploring data, you really want to dig in there and just see what the heck am I looking at. So we're going to look at the labels, and this would be the first label that comes up, and we'll go ahead and run this. And when we look at that, you can see this is what I'm talking about. 0, 0, or 1 is 0, 2 is 0, 3 is 0, 4 is 0, 5 is 0, 6 is 0, 7 equals 1. So our very first label is a 7, but our very first label comes up that it's a 7. And so we don't have like 0 through 9. We have a bunch of zeros and just the 1 to mark it as a 7 on here. So now we've kind of looked a quick look at the data. And in here you might ask some questions like, what is 784? 24 times 24. Remember, that's the size of our grid on there, or our tensor coming in. So 784 is the setup on there. And we've gone through all this viewing the data. We'll go ahead and start looking at our TensorFlow. So let's take our X variable. This is going to be our training set. We'll do a placeholder. placeholder, and then we're going to have these come in as float. Now, if I remember correctly, they're actually, 0 or 1 for the values, because they're either, but we have them coming in as a float value, and we have a little bit of a shape coming in here, and there's our 784. So we let it know that this is what our input is for our TensorFlow, and this is our training set. So we'll just put a label on there to help us track that, train set, and then W, and with W we'll go ahead and do TF variables, and we'll do this as zeros. Variables, TF zeros, and we'll set this as 784 by 10, 10 being the output, 784 being our number of variables in, and this is our weights. Remember, we have a bias in there too. And I'll go back over this in just a second as we see how that fits together in our TensorFlow. And we'll do this one with our variables. Again, we have 10, so we're going to do the bias. We do it the same kind of format and setup on here. And so we'll do that as TF zeros of 10. So we'll just create an array of 10 there, and this is our bias. So with these 3 lines, and they're coming out with the eager execution, which would bypass some of what we're doing. But this is important to understand, is the first thing you have to do with TensorFlow is we have to allocate a space for the variables. In our TF placeholder and our TF variable with our weights and our biases, this actually hasn't done anything yet. So all it is placeholders. That's why it's okay to use zeros. You could have just as easily used ones or anything else, and it wouldn't matter. The next stage is to go ahead and set up some of the functions going on. But before we do that, just note that this hasn't done anything. Even if I execute it, all it's done is created placeholders until we do the final initialization. And so we need to go ahead and set up, we'll do y equals tf.nn.softmax. And the code for this is tf.matmul xw plus b. And this is our sum. Let's just put a note here so we can keep track of what's going on. We're finding weighted sum of inputs plus the bias. So there's our plus b, the bias. And then we need to go ahead, let's do y underscore, and again another placeholder. And this one will set, we'll put in as TF placeholder on here. TF placeholder float none 10. There's our one hot encoder going on there. So our 10 values coming out. And we'll do a cross entropy on here. And this is going to be minus TF reduce sum, and we'll do y. Here's our y underscore, which is, remember, we have your y output and your actual output. So this will be our y underscore times the TF log of y. And then finally, before we do the actual initialization of all our variables, we'll set up our train step. This equals our gradient descent optimizer. Very important. Remember, we looked at that chart on our slides, and so we've set up all these formulas, and here's our gradient descent optimizer, and as it keeps looking for that 0 value. That's what we're doing with that particular formula. So let's take a look and see what we're doing here. We just put together all of our pieces for TensorFlow. And, the devil's in the details. We have here our training set coming in. We have to put a placeholder on there. We have our variables with their weights. We have our biases coming out. And then we put in our the weighted sum. So here's summizing our summation here. Then we have our y variable output. So there's our y, how it works, and then of course the actual output on there. And then we have our cross entropy coming in, and that's our minus TF dot reduce sum, the y times the TF log of y. And then the training step, gradient descent optimizer. We're using a 0.01 in this, and we're going to minimize cross entropy. So we're going to let it do all the work. So once we've set up all of these different layers, we've allocated for them, we need to go ahead and initialize them. So we're going to do an init TF initialize, and it's going to be all variables. One of the cool things is they're in the process of doing away with this. So all these steps would be bundled into one instead of having to have placeholders. You initialize them in the same process going on. And then finally, everything in TensorFlow is based on your session. Now this is changing, that there's other options to be able to run this. But we want to go ahead and do session. There's our TF, there's a TF session, and then we want to go ahead and do session run. And what are we going to run? Well, we did initialization of all our variables. So this is what we're running. And this is where actually, once we do this, we actually create our TensorFlow object. So this whole piece of code right here is our TensorFlow object. We have our input coming in with our weighted variables coming in, our softmax for our matmul going out. How does it add it together for our y value? And then then we have the actual float value coming out, checking on our all the way down. So you can see all the different stages going through that we're setting up. And this is one of the reasons that a lot of people like TensorFlow, is because you can designate all these different pieces one step at a time. This is also one of the reasons people don't like TensorFlow, is because you have to designate all the different layers coming down. And there's a lot of steps being made right now to minimize this, to make it either easier to automate it or to allow you to do more complicated things. And all those steps are still at play, so it's worth looking into the more advanced version of what's going on with Keras on top of TensorFlow. It's also important to understand what's going on these individual levels if you're going to play with them. It's important to understand, hey, what's going on with the finding the weighted sum of the inputs plus the bias, because there's other ways to do that. There's all kinds of other tools in there now. But this is the basic setup that you want to do on a TensorFlow coming in. And we want to go ahead and just run and init our TensorFlow. So let's go ahead and do that. Let's run this. We do get a warning here because there's a move to use global variables. This is one of the changes they're making. But as far as this example, it's not going to make a difference because we're doing, once we initialize it, this is initializing our variables. And again, these are only placeholders up here until we initialize them. And I would highly suggest put a note down there or go over to Simplilearn.com and let them know and have them email you a copy of the code so you can actually play with this code right here. Because this is the body of what's going on in TensorFlow. This is the build in neural networks. And then once we've done that, now comes kind of the fun part, is we need to go ahead and train it. So we've created our TensorFlow. We've created our network. And now we need to go ahead and train it. So let's put together that training code. And let's just do for I in range 1000, 0 to 1000. So we're just going to look at the first 1000 in our training. And the way we pull that data from our mince train next batch of 100, so you look at this, we're going to be doing groups of 100, and then there's going to go through 1,000 of them. This is very important that TensorFlow builds this in. This is one of the downsides of doing sklearn or one of the older packages, is they don't let you batch groups in. They wanted to have it all up front, and then you have to build your own batch programs right now. This lets us go ahead and do that. And you can see here we have batch x of s, batch y of s. So there's our x and our y. You can look at this as our training of x and our train of y, or the data in and the answer in. And then we simply do our session run. So here's our session that we've created. We're going to run it, and we want to do the train step. Remember, we initialized our train step up here in our TF, and so there's our train step. Feed is a dictionary coming in, which we're going to create right here. Is x is our batch, x of our sample, comma, and our y underscore is going to be our batch of our y sample. And so this goes through, and we've now hit the run button, and we've trained our session. We've trained this setup on here. And once we've trained it, then we need to go ahead and find out how good our accuracy was and actually start running some predictions through there. So we'll go ahead and create a correct prediction, and this is where our tf.equal, we'll use our argmax y of 1 and tf argmax of y of underscore of 1 to help us get the correct predictions on there. And then we want to use that to feed into an accuracy. And so our accuracy is going to be tf reduce mean, and we'll take that and we'll do a cast, and this is the correct prediction that we're sending in there, and it is a float value. Keep it simple, and let's go ahead and print this out so we can see what we're looking at. So what are we printing out? We need to do a session run. This session run is going to be on the accuracy. Where did accuracy comes from? This is we're casting our TF on there with the correct predictions on that. So here's our accuracy. Feed in, so it needs a dictionary for the data coming in. We're going to create our dictionary, and x is going to be our NIST test images, and y underscore there is going to be our NIST.test labels. Let me just double check and make sure I have that typed in there correctly. There we go, and let's go ahead and run that and see what comes up, and we end up with a 0.9165 for our accuracy, which means our trained neural network does a pretty good job letting us know what these different symbols are, and guessing that a 7 and a 3 and a 4, something that as humans we kind of take for granted. I even have trouble reading this, so I don't know if I would be able, like that first one, I would sit there for a long time figuring out that's a 7 versus a 2. That could have easily been a 2 to me. So you can see we do a pretty good job analyzing this data, and this is used to analyze something very complicated on these images, very different than just a straight value of cost of sales, and here's our return and our marketing. We can now create this nice neural network that does all kinds of cool things.
Do you know friends, that according to the lending statistics, the demand for AI and ML specialists is projected to surge by 40% between 2023 to 2027. And on an average, an ML engineer is expected to earn around $133 and $336 per year. So if you are an aspiring ML engineer and thinking about what innovative projects you can show in your portfolio, then your wait is over. Because in this video, I'll be covering 8 amazing ML projects that you can showcase in your resume. So guys, let's start first with a beginner level project. And the first project that we are going to encounter, that is home value prediction. So guys, this project aims to develop a predictive model to estimate the value of residential properties. The model will analyze various features such as location, square, footage, number of bedrooms and bathrooms, age of the property, and other relevant factors. By leveraging historical property data, the model will be able to provide accurate home value predictions, which can be useful for real estate agents, buyers, and sellers. So guys, the programming language that we are going to use all over here will be Python, and machine learning libraries that we will be using will be scikit-learn, TensorFlow, Keras, and for data handling libraries we have Pandas, NumPy, and for visualization we have to use Matplotlib and Seaborn. Now what will be the approach for this one, guys? So guys, the first one that we have a data collection. So here what is going to happen, guys? So first you have to collect the historical property data from the sources like Zillow, retailer.com. You can also get database from the public real estate databases like Kaggle datasets, where you have Zillow home value prediction. Ensure that the dataset include features like location, where you have latitude, longitude, square footage, number of rooms, year built, property type, and previous sales. The next step that comes is data cleaning. You have to handle the missing values by using imputation techniques or removing incomplete records, removing outliers that may skew the model's prediction, normalize or standardize the data to ensure consistency. The third one that we have is feature engineering. You have to create new features such as proximity to schools, crime rates, and access to the public transportation. Encode categorical variables, example property type, location, using techniques like one-hot encoding. Generate interaction features that capture relationship between existing features. The fourth one that we have is model selection. Use regression models like linear regression, random forest, gradient boosting, neural networks. Experiment with different models to identify the best performing one. Now, in the next phase, all you have to do, guys, is model training and evaluation. Split the data set into training and test sets. Train the model on the training set and evaluate their performance on the testing set using metrics like RSME, which means root mean squared error. You can use cross-validation to ensure the model's robustness and avoid overfitting. The sixth one that we have all over here is hyperparameter tuning. You can optimize the model's hyperparameter using techniques such as grid search or random search to improve accuracy. And if you're looking forward to deploy your model, then you can develop a web interface using Flask or Django to allow users to input property features and get predictions. You can deploy the model on the cloud platform like AWS for scalability. Now, if we talk about the complexity level of this, we all know that it is a beginner level project. Now let us move on to the one more set, that is music genre classification and generation. So guys, this is also one of the most beginner level project. This project aims to develop a system that can classify music tracks into different genres and generate new music composition within specified genre. The goal is to build a model that analyzes audio features to categorize music and uses deep learning techniques to create new music. This project introduces advanced concept of audio processing, deep learning, and generative models. So guys, what will be used in this? So we'll have programming language that will be Python. For audio processing, we'll be using Librosa. For machine learning libraries, we'll be using TensorFlow, Keras, PyTorch. For data handling libraries, we'll be using Pandas, NumPy. For visualization, we'll be using Matplotlib, Seaborn. For the dataset, guys, you can use GTZan music genre dataset, or you can get it from Free Music Archive. So guys, in the first phase, we are going to have data collection. You can obtain datasets containing music tracks and their corresponding genre from the sources, from GTZan music genre dataset and the Free Music Archive. Ensure that a dataset includes diverse genre and substantial number of tracks per genre. Next, we'll go for data preprocessing. Use library Librosa to load and preprocess audio files, including feature extractions such as mil frequency, cepstral coefficients, chroma features, and spectral contrast. You can normalize the extracted features to ensure consistent input for the given models. Now, if we talk about feature engineering, guys, you can extract additional features from the audio files such as tempo, beat, zero crossing rate, etc. Create a feature matrix that represents the extracted audio features. Then go for the model selection. Use convolutional neural network or recurrent neural networks for the music genre classification. Split the dataset into training and testing dataset. Now, if we talk about model training and evaluation, guys, then you can train the selected classification model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use confusion matrices to understand the classification performance across different genres. Now, if we talk about model selection and training for the music generation, what you will do, guys, you can use the generative adversarial networks or recurrent neural networks such as LSTM, long short-term memory for music generation. Train the generative model on the dataset to create new music sequences. Next, we have model training and evaluation. You can train the generative model on sequences of audio features. You can evaluate the generated music by listening tests and by objective metrics like inception score or Friese audio distance. If I talk about hyperparameter tuning, guys, you can optimize the model. You can use the hyperparameters using techniques like grid search or random search to improve performance. If I talk about deployment, guys, you can deploy these models on cloud platforms like AWS. Now, let us move on to our next project. So, guys, the complexity of this project is at the beginner level. Now, let us move to the intermediate level projects. Next project that we have all over here is sentiment analysis of Twitter data. This project aims to develop a sentiment analysis model that can classify tweets as positive, negative, or neutral. The goal is to analyze public sentiment on various topics or events using natural language techniques. So guys, what will be used all over here? So in this, we will have programming language like Python, okay, NLP libraries, NLTK Spacey. For machine learning libraries, you can use scikit-learn, TensorFlow, Keras. For data handling libraries, we have Pandas, NumPy. For visualization, we have Matplotlib, Seaborn, and we can use the API Twitter for data collection. Now, how you're going to work on it, guys? So guys, if I talk about the data collection, use a Twitter API to collect tweets based on specific hashtags like keywords or topics. Extract relevant fields like tweet text, user information, timestamp, etc. Then if I talk about data preprocessing, guys, clean the tweet text by removing special characters, links, mentions, hashtags, and stop words. Tokenize the text and perform lemmaization or stemming to reduce the words to their base form. Next, if we talk about feature engineering, guys, you convert the clean text data into numerical representation using TF-IDF, bag of words, or word embedding. Now, if I talk about model selection, guys, you can choose the classification algorithms such as logistic regression, Naive Bayes, or LSTM. Split the data set into training and testing data set. Now, if I talk about model training and evaluation, then you can train the selected model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use cross-validation to ensure the model's robustness. If I talk about hyperparameter tuning, guys, you can optimize the model's hyperparameters using grid search or random search to improve the performance. For deployment, which can be optional, you can deploy your model on AWS for real-time sentiment analysis. So if I talk about the complexity level, guys, its complexity is intermediate. So guys, our next project is customer segmentation using k-means clustering. This project aims to segment customers into distinct groups based on their purchasing behavior and demographic information. The objective is to understand customer segments and tailor marketing strategies accordingly. So guys, what programming languages we'll be using? So basically, we'll be using Python. For machine learning libraries, we'll have scikit-learn. For data handling libraries, we'll have Pandas, NumPy. For visualization libraries, we'll have Matplotlib, Seaborn. And the dataset source will be e-commerce transaction data. How we are going to work on this one? For data collection, we can obtain a dataset of e-commerce transactions that include customer demographics, purchase history, and product information. Next, we'll have data preprocessing. For data preprocessing, we are going to do the cleaning of the data by handling the missing values and outliers. Then, for feature engineering, we are going to create features like total purchase amount, purchase frequency, and recency of the purchases. Then we are going to proceed for the model selection. You can use k-means clustering to segment the customers into distinct groups. You can determine the optimal number of clusters using methods like elbow methods or Silhouette score. Now, if I talk about model training and evaluation, you can train the k-means model on the processed dataset. You can evaluate the quality of clusters by analyzing intra-cluster and inter-cluster distances. Next, we have the evaluation. You can visualize the clusters using techniques like PCA, principal component analysis, TSNE, etc. Next, we have the hyperparameter tuning. Now you can tune this model and interpret the characteristic of each segment. You can develop a target marketing strategies for each segment based on unique behavior and preferences. Now, deployment is optional. You can develop a dashboard using Flask or Django to visualize customer segments and track marketing campaigns. So guys, if I talk about the complexity of this project, so this is an intermediate level project. So guys, for dataset, you can use the Kaggle's customer segmentation dataset, which is available at the Kaggle's platform. Now, the third intermediate level project that we have all over here is building a chatbot with RASA. This project aims to build an intelligent chatbot using RASA framework. The chatbot will be capable of understanding user queries and providing appropriate responses, making it useful for customer support, personal assistance, or information retrieval. What languages we are going to use? So it will be Python based. We'll have the NLP libraries like RASA, NLTK, Spacy. For machine learning libraries, we are going to have scikit-learn, TensorFlow, Keras, etc. For data handling libraries, we are going to use Pandas, NumPy. So guys, this was what we are going to do it. And how you can work on this one? By collecting the data, collect the conversation data and FAQs from the target domain. Annotate the data to create training examples for the chatbot. Next comes is data pre-processing. Clean the text data by removing special characters and normalizing the text. You can tokenize and limitize the text to prepare for a training. The third one, we have the models training. You can use RASA's NLU's component to train a model for intent recognition and entity extraction. You can define the dialogue management policies to handle different conversation flows. Next guys, you can perform the feature engineering and integration. You can integrate the RASA's NLU and core components to build complete chatbot. You can connect the chatbot to messaging platform like Facebook, Messenger, etc. For model selection and testing, what you can do guys, you can test this chatbot with various inputs to ensure that it handles the scenarios appropriately. And you can also select the right model using this. Now, if I talk about model training guys, what do you have to do? You have to collect the user feedback and conversational logs to continuously work on training the model. Next, similarly, you have to retrain the model periodically with the new data to see how it is working. So that will be your evaluation. Now, for the hyperparameter tuning, what are you going to do guys? You have to check in those scenarios where it is able to tune up with those scenarios where it can handle the input appropriately. And next is deployment. So guys, for deploying it, you can use AWS. So guys, for a data set, you can use RASA's open source. So that's a very good data set for you to proceed. So guys, if you talk about difficulty of this project, this is an intermediate level project. Now let us move on to the advanced level projects. For advanced level projects, the first one that comes up to my mind is movie similarity from plot summaries. Now, this project aims to develop a system that can find out recommended movies similar to a given movie based on their plot summaries. By analyzing the textual content of the movie, plot summaries, the model will identify similarities and suggest movies with similar themes, storylines, or genres. This project introduces beginners to natural language processing, text similarly measures, and recommendation systems. What languages we are going to use guys? We'll be using Python, NLP libraries like NLTK, Spacy, machine learning libraries like scikit-learn, data handling libraries like Pandas, NumPy, visualization we can use NumPy, and dataset source will be IMDb or Kaggle. So guys, this process is also involving the data collection, then you have to go for data cleaning, then feature engineering, next model selection. So similar process as I have discussed in other projects, so you have to also go through the same one. Next, what do you have to do guys? Similarly, what do you have to do? You have to train the model, then evaluate the model, then hypertune it, and finally proceed for the deployment. So this is overall process of this project. Try to research on the website a lot, like how you can extract it. So guys, you can use Kaggle or Towards Data Science to research more about this project. Now guys, if I talk about the difficulty of this project, then this is an advanced level project. Now, let us move on to the next one that we have all over here. That is image segmentation project for brain tumor prognosis. This is a very amazing project and definitely you can put up on your portfolio. Basically guys, this project aims to develop an image segmentation model to identify and delineate brain tumors from MRI scans. The goal is to accurately segment the tumor regions, which can aid in prognosis, treatment planning, surgical interventions. This project introduces intermediate level concepts of computer vision, deep learning, and medical image analysis. So guys, what we'll be using all over here? For programming languages, we can use Python. For deep learning libraries, we can use TensorFlow, Keras, PyTorch. For image processing libraries, we can use OpenCV, Scikit-Image. For data handling libraries, we can use Pandas, NumPy. For visualization, we can use Matplotlib, Seaborn. Now, if I talk about what is the process of developing this project, the first step will be the same, data collection. So next step, you have to go for data pre-processing. Third step, you have to do the model selection, where you can use CNN models for image segmentation task. Then you go for model selection. Moving ahead, you're going to have the model training and evaluation. You have to split the data set into training and validation and testing data sets. Next, proceed for the evaluation phase. Okay, evaluate the model with certain metrics. So here I can give you certain idea, like you can use dice coefficient, intersection over union, or accuracy. Then go for hyperparameter tuning, where you have to optimize the model's hyperparameters. You can use grid search or random search, as we have discussed. And finally, you can deploy this model on AWS. Now guys, we have come to the final project. This is also a very amazing project, guys. So guys, the complexity level of this project is advanced level. Now, let us move on to our final project, that is the impact of climate change on birds. This is a very amazing project, and definitely you can add it on your resume. This project aims to analyze the impact of climate change on the bird population and migration patterns. By examining various climatic factors and their correlation with bird species data, the project seeks to predict how climate change might affect bird behavior and distribution. This project will introduce you some advanced level concepts like time series analysis, environmental data modeling, etc. So guys, what programming languages we'll be using? For data analysis, you can see we'll have Pandas, NumPy. For machine learning libraries, we are going to have Scikit-Learn, TensorFlow. For visualization, we are going to have Matplotlib, Plotly. For geospatial, we are going to have GeoPandas, Folium. For data source, we're going to have public data sets on bird observation and climate data sources from eBird. Now, what will the process flow for this one, guys? First, you have to proceed for data collection. Gather bird observation from the data like eBird, which provides extensive record of bird sightings. Okay, and for climate data, you can collect it from NOAA, including temperature, precipitation, and other relevant climatic factors over the time. Then similar next process will be the data pre-processing. Then you have to proceed for feature engineering. Then you have to go for model selection. Okay, moving ahead, you have to go for model training, then evaluation, then hyperparameter tuning, and finally, you have to deploy the model. So research about this project, see what models you are going to use. Suppose I can give you a hint about this. You can use time series analysis models like ARIMA, or ML models. You can also use random forest or gradient boosting for predicting impact on the bird population. So guys, use Google exhaustively to research about this project. This is also a very amazing project, and it's going to give you a lot of idea. Now, if I talk about the complexity level of this, it is an advanced level project.
Welcome to Deep Learning Interview Questions. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Today we're going to help you prepare for interview questions dealing with deep learning. And we're going to go from the very basics of neural networks and deep learning into some of the more commonly used models, so that you can have an understanding of what kind of questions are going to come up and what you need to know in interview questions. We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. And then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithm like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, it used the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, back propagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with 2 of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off. True, false, yes, no. First layer is the visible layer, and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts a weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. Formula for that line has a y coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time? We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU, it's pronounced like ray, the ray from the sun, and lu, like a name, so ReLU function. And we have the tangent H function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1, and in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data and your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or a straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool, but in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is what is a cost function that we're going to cover. This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is the measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function c equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error if we're training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it, because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training, and part of your data is for testing, and then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do your initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So, as we're looking at this, we have our squared error that we just figured out based on the cost function. It says, how bad is my model fitting the data I just put through it? And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. And this, of course, we mentioned it briefly about back propagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, back propagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on, in case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation, is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function, not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the convolutional neural network. Wonderful tutorial. Check that out and learn a lot more about the convolutional neural network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in what they call a time sequence. That's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L on the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they give us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Remember we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars. Might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for Rectified Linear Unit and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there, and if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we referenced the convolution neural network, the CNN, which you'd have to go to another video to review, the ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back one. We looked at that here where it transforms the numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units. How many hidden layers are you going to have, and how many nodes in each layer? Learning rate. Learning rate is usually multiplied once you've figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change, otherwise you're going to have a biased model. So you only take some little incremental changes, and that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low, and you can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago, that's what the learning rate was, training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned epoch, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one epoch run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have 2 new words there, converge and diverge, are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data, and then you'll randomly pick another 20 nodes the next time you go through an epoch data training. So each time you go through one epoch, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the sides and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of a neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization, it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epoch. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for a convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck or only Ford trucks because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data, and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN? Convolutional neural network. First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so we can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together. And then finally, the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you see here, they have a rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features. And it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with a 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8, pretty high label, and maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here as we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of t minus 1, and the hidden layer, that's what the H stands for, hidden layer of t, and the formula is going in. As we can see here, we have the hidden layers. We have t minus 1 and then h of t, where t stands for time. So this is a series. Remember, we're working with series, and we want to remember the past. And you can see you have your input of t, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent H activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your x of t plus 1. So when you have that coming in, then you have your h value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, it makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one tensor to the next, these layers might change. We might flatten them, might bring in numerous, in the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 d-type tf float 32, or b equals the tf variable minus 3 comma d-type float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf_placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run, b comma feed dictionary equals a 3.0, print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph, or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger, fake wine, shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are 2 main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image comes in, we have our Latin space representation, and then it goes back out reconstructing the image. It works by compressing the input to a Latin space representation and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data. Very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
So guys, that's a wrap up on our full course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply you as soon as possible. Thank you and keep learning with Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.